Okay, so this is the next topic that we're doing, trigonometry. The first thing that you need to know about this is reciprocal trigonometric functions. So in paper one, you've done sine, cos, tan. Now we've got three new functions: cosecant, secant, and cot. Cosecant is 1 over sine, secant is 1 over cos, cot is 1 over tan. Now, the way to remember these is sometimes cosecant and secant, they get mixed up. Look at third letters. Third letter for cosecant is S. That's the reciprocal of sine. Third letter for secant is C. That's the reciprocal of cos. Third letter of cot is T. That's the reciprocal of tan. That's one way that you can use to remember this in case you end up mixing them up sometimes. So these are three new functions that we've got. These are called reciprocal functions. Now, you need to be able to solve equations involving these functions. For example, if you have secant theta equal to, how would you solve this equation? Now, your calculator does not have a secant, cosecant, or cot button. So when you have reciprocal functions in an equation, you have to convert them to the base function. So secant can be written as 1 over cos, and that becomes cos theta equals 1 over 2. You find the basic angle, look at quadrants, and write down the answers based on that. Okay. In paper one, you had done these two identities: sine square theta plus cos square theta is identical to 1. 1 plus tan square theta is identical to secant square theta. Using these identities, we could just rearrange them and get sine square identical to 1 over cos square identical to 1 minus sine square. So you could convert sine square to cos square to sine square. Similarly, you had, this was the only one that you done. It was paper one, the other one. Okay, these two are the ones that you're done in paper one: sine square theta plus cos square theta equals 1, and tan theta equals sine theta over cos theta. These were two identities that you're done in paper one. Now, you could convert sine square to cos square or cos square to sine square using this. And using this other identity, you could say when you have sine over cos, that could be written as tan theta. Now, here we have some new identities. First of all, tan theta is sine over cos. We could take reciprocal on both sides to make it cot theta equal to cos theta over sine theta. We will be using this identity a lot of times, and it's not given in the formula sheet, so it helps to remember this. It's just the reciprocal of this. If tan is sine over cos, then cot is cos over sine. Okay, this is not given in the formula sheet, but we'll be using this a lot, so keep this in mind. But then you have two new identities which come from the reciprocal trigonometric functions. 1 plus tan square is secant square, 1 plus cot square is cosecant square. Now, using these identities, what you can do is you can convert tan square to secant square if you want, secant square to tan square. Similarly, you can convert cot square to secant square, cot square to secant square, cot square to cosecant square, and cosecant square to cot square. You can do these conversions using these identities. Okay. Now, even if you don't memorize these identities, the least that you need to remember is that tan square and secant square, they have some identity between them. Otherwise, you will not get ideas in the exam, how to solve equations or how to prove identities. The minimum that you need to remember is that tan square can be converted to secant square and secant square can be converted to tan square. And then for the exact identity, you can look at the formula sheet. But at least this much you need to remember. Similarly, that cot square and cosecant square, they are related to each other. One can be converted to the other. You should memorize that, at least that much, okay? Now, let's say you have an equation like this. How do you solve any trigonometric equation? You want only one type of function, sine, cos, tan, and only one type of angle. In this case, we've got secant square, and this is tan. How do we convert them to one function? We could say secant square can be written as 1 plus tan square. And then we simplify that. That gives us a quadratic equation in terms of tan. We solve the quadratic, find the basic angle, write down the final answers based on that. The interval that we were given in this case was from 0 to 2 pi. We got the basic angle for both of them. As in, we first of all got two values of tan theta, this and this. We find the basic angle, looked at the quadrants, and wrote down the answers based on that. Okay. So that's what you may have to do. Then we have some more identities. So first of all, we've got compound angle identities. Now, what are compound angles? Let's say you have an equation that looks like this. Sine of theta plus 60 plus cos theta equals 0. How do you solve this equation? These are two different angles. This is another angle. This is another angle. Using the earlier methods, we could not solve these equations. We have to expand this thing somehow. Now, this angle, theta plus 60, when you have two angles, two numbers or two expressions being added or subtracted, we call this a compound angle. We have identities for expanding them, and it's not this. Sine theta plus 60 is not the same as sine theta plus sine 60. That's not correct. We expand it using some identities, and they look like this. We have 6 identities, 2 for sine, 2 for cos, 2 for tan. Sine a plus b is sine a cos b plus cos a sine b. Sine a minus b is sine a cos b minus cos a sine b. Similarly, for cos and tan, you can look at these identities. Whenever you have these compound angles, we can expand them using these identities. All of them are given in the formula sheet, although they're written in a relatively more concise way. I'll show them how exactly. But using these identities now, what you can do is, for example, in this case, you had sine theta plus 60. You could expand sine theta plus 60 like this, sine theta into cos 60 plus cos theta into sine 60. And then cos 60 becomes 1 over 2, sine 60 is under root 3 over 2. And then you could simplify that further after that to solve that equation. This is what I've done that. So we first of all applied that identity to simplify that. And then we had sine in one term, cos in another term, cos in another term. To convert it to tan, we could just divide the whole equation by cos like this, right? We divide the whole equation by cos, it converts to tan, and then you can solve that equation in terms of tan, find the basic angle, and find the result from that. Then you have some double angle identities. What are double angles? When you have 2 times something, it could be 2x, it could be 2 theta. These are called double angles, okay? For expanding double angles as well, we've got some identities. They're given in the formula sheet as well. So this topic is more about application, as in these identities are all given in the formula sheet. We need to be able to use them. That's why we'll have a look at a number of examples. Sine 2a, that's 2 sine a cos a. Cos 2a is cos square a minus sine square a. 2 cos square a minus 1, 1 minus 2 sine square a. There are 3 different forms that we have for this. We can use any of them generally. If we know we have to convert something to cos, then we can use this one. If we know that we want sine in the final result, then we can use this. If we are not sure, then you can use any of them. It doesn't matter. But we have these 3 different forms. They're just coming from these identities that sine square is 1 minus cos square is 1 minus sine square. So from that, we can actually get these 3 different forms. Then we have a double angle identity for tan. That's 2 tan a divided by 1 minus tan square a. We've got these double angle identities. We can use these to expand these expressions. Expanding means you want to convert it to just angle x, this just angle theta. We want to get rid of that 2 times that. Okay, that's what it means to expand these expressions. These are double angle identities. Now you can use them, for example, to solve equations like these. Sine 2x minus cos x equals 0. How do you do that? Apply the double angle identity for sine, it becomes 2 sine x cos x minus cos x equals 0. And now you can take cos x common. That gives you 2 equations, cos x equals 0, 2 sine x minus 1 equals 0. You've got this interval given, solve these equations further, find the basic angle, use quadrants, and find the values of x that you get from them, right? This is how these identities are given in the formula sheet, right? So these are all the identities that are given in the formula sheet that I've showed you before. This one is not given, so you can remember that you just take reciprocal of this tan identity, and that will give you this. The compound angle identities that are written in a concise way like this. These are 2 identities in one single row. For example, for cos, you have plus written above here, minus written above here. So you can say the plus on the left side corresponds to minus on the right side. Similarly, if you have minus on the left side, then you have plus on the right side. For tan, for instance, this is tan of A plus B. That is identical to tan A plus tan B divided by 1 minus tan A tan B, right? So the sign that is written above, that corresponds to the sign that's written above on the other side as well. The sign that's written below, that corresponds to the sign that's written below on the other side as well. So tan A minus B, that is tan A minus tan B divided by 1 plus tan A tan B. And that's the result and that's the identity that you've got. So these are 6 identities written in 3 different lines like this. Then you've got these double angle identities. Cos 2a, it has 3 different forms. Sin 2a is only one form, and tan 2a. Okay. This is how these identities are given. Now, using these identities, you should be able to expand some other expressions as well. For example, what if you had sine of 4 theta? How would you expand that? Sine of 4 theta. You could expand sine of 4 theta like this. You could say sine 4 theta is the same thing as saying sine of 2 theta plus 2 theta. You could write that as a compound angle, right? Sine of 2 theta plus 2 theta. And then apply the compound angle identity for sine a cos b plus cos a sin b, and then simplify that, you end up getting this expression. And depending on what you want afterwards, you can convert it to that form, but that's what you get after simplification of this. You apply the double angle identity for this, double angle identity for this, simplify everything, and that gives you some result. Okay. An alternative for this could be using the double angle identity for sine of 4 theta. You could also do this. Since you have the double angle identity for sine, that's sine of 2a, that is identical to 2 sine a into cos of a. We could say whatever is the angle on the left side here, on the right side, the angle is half of that. So if we had 4 theta on the left side, on the right side, it would just be 2 theta and 2 theta, right? So we could do it directly like this as well, and then simplify it further, expand sine 2 theta, expand cos of 2 theta, and then that would give you the simplified form after that. Okay, so that's how you expand sine of 4 theta. Similarly for cos 4 theta and tan 4 theta as well, you can either use the double angle identity or the compound angle identity. Now, compound angle means 2 theta plus 2 theta. In this case, double angle, whatever is the angle on the left side and the right, it has to be half of that. So in this case, if the angle is 4 theta on the right side, it will be 2 theta and 2 theta. Right? It's the same for cos and tan as well, as in it works similarly to this. If you have 3 theta, in this case, you can't use double angle. You can only use compound angle. 3 theta, sine of 3 theta, cos of 3 theta, tan of 3 theta. This can be expanded using the compound angle identity. We'll say this is cos of 2 theta plus theta, right? Apply the identity for this. That will become cos 2 theta into cos theta minus sine 2 theta into sine theta. And then you simplify this further, apply the double angle identity for this, apply the double angle identity for this, and then that will simplify further to give you something like this. Now, depending on what you want at the end, you can convert it to either only sine or only cos. That would depend on the question, but that's the general method that would have to be applied when you have 3 times theta. Now, the double angle identities that we saw earlier, we could also come up with half angle identities from that. Now, what does that mean? If you have sine of 2a, that is 2 sine a cos a, we could also make an identity like this from that. That if the angle on the left side was theta, let's say it was sine theta, then on the right side, it should be half of that. So what's half of theta? That's half theta. So this identity, we could also say, this also tells us that sine of theta, that can be written as 2 sine of half theta into cos of half theta, right? So that's something that you'll have to do in some more complicated problems as well. Similarly, for cos 2a, we know that cos 2a is cos square a minus sine square a, right? We could say cos of theta, that could be cos square half theta minus sine square half theta. We could use this identity like this as well here. Okay. For example, this is an actual question. If I remember correctly, if you have sine theta minus 2 cos half theta equal to 0, and you want to solve this equation, how do you do that? You've got half theta angle here. One way to do this could be that since you want the same angle, right? For solving any equation, we want the same type of angle. Now, this is theta, this is half theta. So we either have to convert this half theta to theta, which is more complicated, or we convert theta to half theta. So that's what we do. We can say sine theta, using this double angle identity, we could write sine theta as 2 sine of half theta into cos of half theta. So it's written like this. And then you take cos half theta, 2 cos half theta common there. You get this equation, you get another equation, you solve these two separately, and you get the result from that. An alternative, relatively easier one, easier way of solving this could be to use a substitution in the very beginning, like this, that you say, let A equals some other letter, right? Let A equals half theta. If you were to do that in the very beginning, then this equation could actually be written like this. In this particular example, we could say, let's use a substitution A equals half theta, and then we could write this as sine of 2A minus 2 cos A equal 0. And then we could solve this equation in terms of A. At the end, put that substitution back. Put A equal to half theta, put half theta in place of A, and then find the values of theta from that. But when we do that, remember, we have to adjust the interval as well. For example, if the interval for theta, let's say that was given to be from 0 to pi, then the interval 0 to 2 pi, let's say, then the interval that we would have for A would be 0 to pi. Right? We learned this in paper 1, that we use a substitution. When we use a substitution, the interval gets changed as well. When we put 0 here, the lower limit will be 0. When we have 2 pi here, the upper limit becomes pi there. Okay. All right. So that's what you can do in some cases as well. You can use half angle identities like this, right? Similarly, as we will see later in integration, you can also use. Let me show that to you here as well. We will see this later. For example, for integrating sine squared theta, we have to use the double angle identity for that as well. How would we do that? We have this identity cos 2a, that is equal to 1 minus 2 sine square a. And then if you make sine square a the subject from this, that gives us 1 minus cos 2a divided by 2. And we make the sine square a the subject. Now, using this, we could say that sine square theta could be written as 1 minus cos 2 theta divided by 2. So in integration, we have to do this a lot. For integrating even powers of sine and cos, this is the identity that we use, the double angle identity for cos, like this, right? So we will be looking at this later on again in integration as well when we do that. Okay, let's move on. Then you have to prove identities, right? So just like in paper 1, you will have some identities. You'll have some identities that you would have to prove. For example, you have this identity. Now, how do we prove identities? You've done this in paper 1 as well. But in this case, you'll have more complicated identities. First of all, which side do you start from? Now, the way these are going to be formulated in your exam would be that the left side would almost always be more complex. So that is what you would start. That is where you would start from. So generally, they will write the identities like this, that you would start from the left side and equate that to the right side. However, you should still, uh, think about which side is going to be more efficient to start, because it can happen that starting from the right side in some rare case might be a better idea. So how do you decide which side to start from? You start from the more complex side. Now, how do you decide which side is more complex? The side that has compound angles, the side that has compound or double angles, we say that is more complex. So this will be the order of priority. We start from the first rule, compound and double angle. If we can differentiate based on that, just do that. So in this case, for example, the left side, it has double angles like this, right? So that is more complex. Even though the right side has power, that's not what introduces complexity. It's the multiple. If it's multiplying by something, or if something is being added or subtracted inside the angle, that is what makes the expression more complex. On the left side, you have double angles here. You can say that is more complex. So this is one thing that you need to that you decide on whether to start from the left side or left hand side or the right hand side. The second is different types of functions. If none of the sides has compound or double angles, you start from the side as that has more different functions. For example, if one side has sine and cos and the other side only has tan, then you start from the side that has sine and cos, right? And then if one side has fraction and the other does not have fraction, you start from the side that has fraction, because it's easier to convert fraction to a non-fraction as compared to the other way around. And if none of them help you differentiate between the two sides, then you see whichever side has more number of terms. So if one side has 3 terms and the other side only has 1 term, then converting 3 to 1 is easier as compared to the other way around. But mostly you'll be able to decide based on the first 2 in paper 3. Compound double angles, you start from that. Otherwise, the side that has more different types of functions, you start from that. In most cases, you will be starting from the left-hand side. They write them like this. However, you can work either way. You can start from the left-hand side, equate that equal to the right-hand side. You can start from the right-hand side, equate that equal to the left-hand side. Or this is also possible that you simplify both sides and separately. Simplify the left-hand side as well, simplify the right-hand side as well, and then you meet somewhere in the middle. This is something that we will be doing in some more complicated identities, in which on both sides we have double or compound angles. For example, on the left side, you might have, for instance, sine of 2 theta plus something. Let's say 2 theta plus pi over 3. On the right side, you might have cos of 3 theta, right? Let's suppose both sides have these compound angles. Now, what do you do in that case? In this case, when you have compound or double angles on both sides, it's a good idea to simplify both sides, right? That will make this simpler. You simplify both sides, and then somewhere in the middle, when both of them are equal to each other, you say the identity is proved. However, when you do that, you do not take terms from one side to the other. That is not allowed. While you are proving identities, you're not allowed to take take a term from one side to the other, because that will be assuming that the identity is true. But you have to prove that the identity is true. So while you're proving identities, you are not supposed to take terms from one side to the other. So if you're using this method, then you keep them separate. Keep the left-hand side separate, the right-hand side separate, and try to meet somewhere in the middle as you go along, where they become equal to each other. Now, these are not any standard rules, but some tips that you learn when you practice a lot, and they help you prove identities a bit more efficiently. First of all, you would find it helpful to keep the denominators unsimplified. That means keep them in factorized form, so that if there's any cancellation that's possible in a later step, you can do that. For example, if you have sine theta into 1 plus cos theta in the denominator, it's better to keep it like this rather than simplifying it in this form, because it is possible that in a later step in the numerator, you end up getting something that you can do some cancellation on. For example, you might have 1 plus cos theta whole square in the denominator, and you might be able to cancel out 1 power of 1 plus cos theta with 1 power of 1 plus cos theta in the denominator. And that would help. If you simplify that, then it becomes difficult for you to think of factorizing that again and then doing the cancellation. Okay, so it's helpful to keep the denominator unsimplified to see if any cancellation is possible. Then these identities are used a lot. This first identity in particular, the algebraic identity, a square minus b square, that is a plus b into a minus b. You have to use that a lot while proving identities. For example, if you have 1 minus tan square theta, you could write that as 1 square minus tan square theta, and that becomes 1 plus tan theta into 1 minus tan theta, right? So this is used a lot, so keep that in mind. If you had 9 minus 9 tan square theta, for instance, you could say that's 3 squared minus 3 tan theta whole squared, and then use that identity on that, and so on, right? So a square minus b square, this identity, to factorize something, that's used a lot, which can then help you do some cancellation in the next step as well when you factorize that. When you have tan on one side, the one that you're starting from, and there's no tan on the other side. For example, you're proving an identity. On the left side of the identity, you have tan, and that's what you're starting from. On the other side, there's no tan. Then it's more efficient to convert tan to sine over cos right away. And when you look at some examples, you'd find that this is very helpful. Convert tan to sine over cos in the very beginning rather than doing that at the end. That will simplify things for you. Okay, if you have tan, convert that to sine over cos. If you have cot, convert that to cos over sine. So work with work in sine and cos instead of tan and cot, because the identities for sine and cos, they don't have fractions in them. Tan's identities, it has fractions, so it's easier to avoid it. If there's no tan on the other side, if you want tan in the final result, then of course you can keep it in that form. But if on the other side there's no tan involved, then convert it to sine over cos right away and convert cot to cos over sine right away. That will simplify things for you. If you have double angles in secant, cosecant, and cot, again, since there are no double angle identities that we have written for the reciprocal trigonometric functions, you will convert them to sine, cos, tan. Their base functions. Secant 2 theta is 1 over cos 2 theta. Cosecant is 1 over sine 2 theta. Cot, you could write that as either 1 over tan 2 theta or cos 2 theta over sine 2 theta, and then simplify that further. This is an example. We have seen how to deal with this already before. We have to prove this identity. Now we start from the left-hand side. If we start from the left-hand side, we've got cos 4 theta here, right? How do you expand cos 4 theta? We know that cos 2 theta is 2 cos squared theta minus 1. What about cos 4 theta? If you want to use the double angle identity, we can say whatever is the angle on the left side, what happens on the right side is it becomes half of that. So it becomes cos of 4 theta equals 2 cos squared 2 theta minus 1. Now here it's very important to understand the notation that we employed. Sine square x is just a short way of writing sine of x whole squared. The actual function is sine of x whole squared. Sine square x is just a short form of writing that. Cos square x, again, it's this short way of writing cos of x whole squared. The actual mathematical form is this. So when you have cos square 2 theta here, what does that really mean? Cos square 2 theta basically means it's cos 2 theta whole square, right? So we have a whole square like that. And now you can expand cos 2 theta using the double angle identity for cos again. So we've applied the double angle identity once, and that gave us 2 cos squared 2 theta minus 1 here. But then we have to apply the double angle identity once more to simplify cos 2 theta, and that gives us 2 cos squared theta minus 1 inside the square here. And we simplify that further, and that gives us this for cos 4 theta. And look at the working for that. We input that here now in place of cos 4 theta, simplify everything, and that identity gets proved. Okay. Now, this is another concept that we have here, and that is that they ask you to convert something. They ask you to convert expressions to a form like this: r sine theta plus alpha, r sine theta minus alpha, r cos theta plus alpha, r cos theta minus alpha. Now, how would this work? For example, you have this expression 4 sine theta minus 3 cos theta. That's identical to r sine of theta minus alpha. Now, there's a background of this, where this comes from. You can have a look at this. We want to convert it to r sine of theta minus alpha. We can simplify the right-hand side here and simplify that. From that, we get this expression on the left side, this expression on the right side. We do comparison on both sides. We get two equations from that, and we find the values of r and alpha from that. However, from this process, we end up getting some formulas that we will be using directly. We will not be using this method. This is the logic behind the formulas that we will be using. What we'll actually do is, there are 4 different forms that are possible. That they can ask you to convert something to. They can ask you to convert something to r sine of theta plus alpha, r sine of theta minus alpha, r cos of theta minus alpha, r cos of theta plus alpha. These are the 4 different forms in which they can ask you to convert something. Now, the expression that you would have to convert to that, it would have 2 terms, one sine term and one cos term, right? One sine term and one cos term. If you want to convert to sine, the first term here has to be sine. Okay, so the first term has to be sine. So when you want to convert to sine, you can see the first term is sine here, it's being converted to sine. The first term is sine here, it's being converted to sine. When it's being converted to cos, the first term is cos here, right? When it's being converted to cos, the first term is cos here. So that's important, that the first term has to be the one to which that you want to convert it to. And then inside, It'll either be plus alpha or minus alpha. In case of the sine function, if you have plus here, you have plus here as well. If you have minus here, you've got minus here as well, because these identities come from the compound, and these formulas come from, or these forms come from the compound angle identities for sine and cos. If you remember the sine angle identity for the compound angle identity for sine, it has the same signs on both sides. So sine of a plus b, that is sine a cos b plus cos a sine b. For cos, however, the signs are different. When you have plus on the left side, you have minus on the right. When you have minus on the left side, you have plus on the right. So in these forms that you see here, in case of sine function, plus is plus, minus corresponds to minus. In case of the cos function, it's the opposite. When you have plus on the left side, you have minus here. When you have minus on the left side, you have plus here. Okay. But normally you would not have to think about the sign yourself. But this is important, that whatever is the first function, that is what you should have here that you want to convert it to. Now, once that is the case, you can use the formulas. You can use these formulas to find the values of r and alpha directly. What formulas? R is equal to square root of a squared plus b squared, and tan alpha is equal to b over a. You can use these formulas to find the values of r and alpha when you have these standard forms like this. Okay, r equals square root of a squared plus b squared. A is the coefficient of the first term here. B is the coefficient of the second term here. Just the positive values. We do not consider the sign in that. That's not required. Just these numbers, right? The coefficient outside, the magnitude of the coefficient, they are a and b. The first number is a, the second is b. Okay, and we can just use these formulas to find the values of r and alpha. For example, if you had 4 sine theta minus 3 cos theta, we wanted to convert that to r sine of theta minus alpha. All we have to do is we say a is equal to 4 and b is equal to 3. Use the formulas to find the values of r and alpha, and you get them like this. If they had 8 sine theta plus 6 cos theta, and you wanted to convert that to r cos of theta minus alpha. Now, in this case, you see, you have to be careful. They have sine here. They want you to convert it to cos. You cannot do it directly. You have to first rearrange it such that cos becomes the first term, right? So you write it as 6 cos theta plus 8 sine theta like this, okay? And now this number is a and this number is b. Now you can use the formulas, otherwise a and b will switch and the value of alpha would end up being wrong. So you have to make sure that you write cos as the first term in this case, because that's what you want to convert it to. So this number would be a, this number would be b. Use the formulas and you get that form for that. This is the result that we get. Okay, so they can, now why is that important? They can you will have to solve equations like this using this particular form. So for example, they're saying by expressing this thing in the form r sine of theta minus alpha, solve this equation. Now we cannot solve this equation directly. If we had 0 on the other side, then we could solve it. We could convert it to tan, right? By taking cos to the other side and then dividing by tan. If the number is something else, we've got 7 here. We do not know how to do that using the P1 methods that we know earlier. How do we do this? How do we solve this equation? We first of all convert the left-hand side to this form, r sine of theta minus alpha. These are two different functions, right? We want to convert them to a single function. For that, we convert it to this form. So let's do that. 8 sine theta minus 6 cos theta, that has to be converted to this form. R sine of theta minus alpha. Now the first term is the same. Yes, that is the same. So that means it is the standard form. You can find the values of r and alpha from this. And it turns out to be tan sine of theta minus tan sine of theta minus 36.87. So the left-hand side converts to this form. So now that equation can be written like this: tan sine of theta minus 36.87 equals 7. And that's the result that we've got. And now, after this is just paper 1 trigonometry, you can solve it further using substitution. So whatever is inside, you substitute that with another letter. Let a equals this, and then you adjust the interval accordingly as well. When theta is 0, the value for a is minus 36.87. When theta is 360, the value for a is 323.13. And then you solve this equation in terms of a, find all the possible values of a, inside this interval, and then put that substitution back to find the corresponding values of theta like this. This is something that you should have done in paper 1. If you do not remember this, have a look at P1 trigonometry revision video. P1 trigonometry revision video. You will find this explained in a bit more detail there. You can have a look at that P1 trigonometry revision video, okay? Yeah, so it's going to take around, I think, 15-20 more minutes, okay? So we'll end around 12, hopefully. Why is it important to adjust the interval? Because, why is it important? Because that we adjust the interval. Because the interval that's given is for theta, right? Theta is from 0 to 360. When we convert it to A, now the angle here was A. We are finding the values of A. So in order to look at the possible values of A, in order to find the possible values of A, we need to know what the minimum value of A can be and what the maximum value of A can be. Because the angle is A, the angle is not theta, right? This is the angle. They gave us the interval for theta. So we have to find the corresponding interval for A, right? If we don't do that, we can sometimes end up missing a possible answer. In this case, that's not happening, but you will see in a lot of cases, you will end up missing out on a possible solution if you do not adjust the interval. So that's important, okay? If you want to understand this in detail, how this process works, P1 revision, P1 trigonometry revision video. Okay, you can have a look at that, and it's explained in a bit more detail there. So let's have a look at this. Express 4 sine theta minus 3 cos theta in this form, r sine of theta minus alpha, where r is greater than 0 and alpha is between 0 and 90 degrees. Now, the first part is straightforward. Let's say we've done that. The second part as well, it's an equation that we've got to solve. We use a substitution again, use the substitution, find the possible values of A, and in this case, you find the values of A and then find the corresponding values of theta, and you get this result. So the first two parts are relatively straightforward. Let's have a look at the last part. Sometimes they end up, sometimes they give you something like this. To find the greatest value of something, least value of something. I've seen such questions, at least one question in one of the recent papers as well. They're asking you to find the greatest possible value of this fraction. Now, how do you find that? Remember, sine and cos, both of them, they are between -1 and 1. But the problem is, we've got both of these functions. We can't input individual values for them as 1 and -1. We need to convert them to a single function, first of all. If you remember in paper 1 functions, to be able to find range of a function, range of a trigonometric function, we first needed to convert everything to only one type of function. This is two functions, sine and cos. So we first of all have to convert it to one function. We have done that in the first part. In the first part, what we've done is we have converted 4 sine theta minus 3 cos theta to this form, r sine of theta minus alpha. So what we can do is we can write it in that form so that it becomes 1 over 5 sine of theta minus 36.87. This thing can be replaced with 5 sine of 36.8, 5 sine of theta minus 36.87 plus 6 is outside as it is. Now, once we have it converted to this form, what's the greatest possible value for this? Now, for sine function, we know sine function is always between -1 and +1. So from this function, we consider the extreme possible values. What are the extreme possible values of sine? It's 1 and -1. So we see what happens when sine is 1, and we see what happens when sine is -1. We input 1 in place of that once, we input -1 in place of that once. When we input 1, we get a result that is 1 over 11 from that. When we input -1, we get 1 from that. Now, the smaller value is going to be the least value of this fraction. The greater value is going to be the greatest possible value of this fraction. We were looking for the greatest value, and that's 1. That's the solution that we've got for this, right? So it's similar to the range questions in paper 1 functions. We had to find the range of this trigonometry. We had to find the maximum possible value of this function. We look at the extreme values of sine. We input 1 in that once, we input -1 in that once, and then that gives us the result. Okay, so sometimes it can be something more complicated like this. So this is another relatively complicated example. I'll just show this to you. You can have a look at this in your own time. Then in the first part, they are just asking you to convert this expression to r cos of theta minus alpha. How do we do that? Is it the standard form? Yes, cos, it is the standard form. Use the formulas, and that gives you the values of r and alpha. And the second part they're saying, hence in each of the following cases, find the smallest positive angle theta which satisfies this equation and this equation. Now, how do we do that? Smallest positive angle theta. We're looking for positive angle theta. So that means theta has to be greater than 0, right? That's the condition that we've got. Theta is greater than 0. How do we solve these equations now? Now, for the first part, okay, let's explain this. For the first part, and the left side, you've already converted it to this form, 4 cos of theta minus 52.24 degrees. So you replace it with that. And now we have to solve this equation. Theta is greater than 0. How do we solve such equation? We can use a substitution. We can say let A equals theta minus 52.24 degrees, right? Now the interval that we had was for theta. Theta was greater than 0. What about A? If we input theta equal to 0 here, A is going to be greater than minus 52.4 degrees, 52.24 degrees. So when we look for the values of A, they have to be greater than minus 52.24 degrees, right? Theta was greater than 0, but A corresponding to that turns out to be this. Now from this we get cos A equals minus 1. When is cos minus 1? In this interval, well, it first happens at 180 degrees. If you think about the graph, so the graph looks like it happens at 180 degrees. That cos function reaches minus 1. So the value for A that we're getting is 180. We put that substitution back and we get that value of theta from this. Theta minus 52.24 equals 180. That gives us the value for theta. But now if you look at the next part, they have changed it slightly. They have under root 6 cos of half theta plus under root 10 sine of half theta, that equals 3. Now, instead of theta here, they have half theta. So what happens in this case? The form that we had there, in the first part, what we did was under root 6 cos theta plus under root 10 sine theta. We converted that to this form, right? Now, in this equation, instead of theta, they have half theta. So we can say, in this form, we would just replace theta with half theta. So it becomes 4 cos of half theta minus 52.24 degrees. That equals 3. This is the equation that we end up getting from this. Again, use a substitution. Let A equals half theta minus 52.24 degrees. If theta is greater than 0, find the corresponding value for A. That again turns out to be that A greater than minus 52.24 degrees. Now, it becomes cos A equals 3 over 4. We find the basic angle. The basic angle turns out to be 41.41 degrees. Now, in this case, you have to be a bit careful. The basic angle is 41.41. Cos is positive. Cos can be positive in the first quadrant or in the fourth quadrant. What do we want? What are we looking for? We were looking for the smallest positive angle theta, the smallest value in this interval when theta is greater than 0. When theta is greater than 0, A is greater than minus 52.24 degrees. That means A could be negative as well. So in the fourth quadrant, we also have to see if there's any negative value that falls in this interval. In the previous case, it did not. We had 180 degrees as the basic angle. So 180 degrees as a possible value of minus 1. On the left side, it was actually minus 180. That is outside the interval, so we did not consider that. But in this case, the basic angle is 52.24 degrees. The basic angle is 52.24 degrees. No, I'm sorry. The basic angle is 41.41 degrees. And the interval is that A is greater than minus 52.24 degrees. Now, if you look at the fourth quadrant here, this angle minus 41.41 degrees, this actually falls in this interval. So A equals 41.41 degrees. That is the smallest value of A that we have in this interval. We want the smallest value of theta in this interval, right? So that means we want the smallest value of A in this interval. The smallest value of A that we're getting is not 41.41 in the first quadrant. There's another value that's even smaller, and that's negative 41.41. That's what we use here because we wanted the smallest value in this interval. And now we put that substitution back, half theta minus 2.24 degrees, that equals this. The value of theta that we get from that is 21.7. And that's the smallest positive value of theta that we have as the solution of this equation. Okay. Make sense? This is quite complicated. I'll just leave it here, as in if you do not remember this concept from paper one, especially of how we have to adjust this, how we have to use the substitution, then adjust that interval, and then find the values in that particular interval. You can have a look at this again in your own time. Let's move on. Sometimes you have to solve simultaneous equations as well. For example, you're given two equations. One is this, another is this, and they want you to find the exact value of tan of a minus b without a calculator. The calculator is not going to give you exact value for this. Tan of a minus b. Now, how do you find that? Tan of a minus b is actually the same thing as tan a minus tan b divided by 1 plus tan a tan b. So the problem is we want to find out the values of tan a and tan b, and then we can just input them in this identity and we would get the result from that. How do we do that? We've got these two equations. Sine of a plus 45, that equals 2 under root 2 cos of a. We want tan a and tan b, right? This is the compound angle. We can expand this first of all. After expanding, we've got sine here, cos here, cos here. We can convert it to tan, right? Dividing by cos, that converts to tan, and we get tan a equals 3. Similarly, in the other equation, now we've got secant square. Now you need to remember secant square and tan square, they are connected to each other. So secant square can be converted to 1 plus tan square like this. And then you solve this equation, it's a quadratic equation, and that gives you tan b equal to 3 over 2. Once you have tan a and tan b, you just input them in that identity, tan a minus tan b divided by 1 plus tan a tan b, and that will give you the exact value for that. So sometimes you can have something like this as well, in which you have to solve simultaneous equations, okay, to find the exact value of something here. Now, some examples from some recent papers. You have to express this thing in the form r sine of x plus alpha. Now, how would that be done? This is not the standard form, right? We want to convert it to sine. The first term is indeed sine, but the problem is this is sine x, this is cos of x plus pi over 4. This is some different angle. So before we can convert it to r sine of x plus alpha, we first need to simplify this thing, right? How do we do that? Using the compound angle identity for cos. Cos of a plus b is cos a cos b minus sine a sine b. We use that identity to expand this thing. And then we simplify this. Cos of pi over 4, we can evaluate this on the calculator, under root 2 over 2. This is also under root 2 over 2. Then you simplify this further and you end up getting sine x plus 2 cos x after simplification. Once you've got this, then after that, now you can say it is the standard form. You want to convert it to r sine of x plus alpha. Now you can use the formulas. R is equal to square root of a squared plus b squared. Tan alpha is b over a. And then that gives you that form that you wanted there. Okay. Then in the next part, they're saying, hence solve this equation. Now, in the first part, what we've done is, in the first part, we have written this expression in this form, under root 5 into sine of x plus 1.107. Okay, that's what we've done in the first part. Now, is that related to that somehow? On the left side, you can have a look at this. Is it connected? In place of x, we've got half theta. In place of x, we've got half theta. That's one thing that is changing. But also, the numbers that you had there were 3 and 2 under root 2. This is 6 and 4 under root 2. So it's also being multiplied by 2. So one thing is that x is being replaced with half theta, and the whole expression is being multiplied by 2. So if this is equivalent to under root 5 into sine of x plus 1.107, then 2 times this should be equal to 2 times that. We can multiply both of them by 2. This is 2 times that, right? So we could say this left-hand side, therefore, this can be written as 2 under root 5 into sine of that. And then we also replace x with half theta here, right? Because in place of x, we've got half theta. So that's the tricky part here. Once you've done that, the rest is standard process as before, although that's pretty long. What do we do after this? You've got this angle, you use a substitution with this. You say let a equals half theta plus 1.107. Then you adjust the interval. Theta is given to be between minus 4 pi and plus 4 pi. You adjust the interval for that. If a is equal to this, we input theta equal to minus 4 pi here, and theta equal to 4 pi here. That gives us the corresponding values for a. Their turn out to be this. A is supposed to be within this interval. And then 2 under root 5 into sine of a, that equals 3. Sine of a equals 3 over 2 under root 5. We find the basic angle. And then we find the values of a from that. A is supposed to be within this interval. Sine is positive, that's the first quadrant or the second quadrant. Now inside this interval, we actually end up getting 4 possible values of a. First quadrant, that's this. Then second quadrant, that's this. But then the interval is going beyond 2 pi. So if we complete one full circle, we can come back here again. That's this angle, another possible value of a. And then the interval is going in the negative direction as well. So we can go like this as well. And that gives you another possible angle. That is this one. Right? So you're getting 4 possible values of a. Then you put that substitution back and you get the corresponding values of theta from that. I'll leave this here for a few seconds. Have a look at this again later on. Slow down a little and you would understand this. Okay? You can go through this again in your own time. Okay, let's move on. This is another question from a recent paper. They are saying by first expanding this thing or otherwise show that cos raised to power 6 plus sine raised to power 6, that is equal to this. Now, how do we do that? They have given you a hint that you have to expand this thing, cos square x plus sine square x whole cube. Now, how do you do this expansion? This is cube, right? You can use binomial expansion, or you could do it like this, a plus b into a plus b whole squared. You could say a plus b into a plus b whole squared. You could do it like that as well. Although it's simpler to use the binomial expansion. Power 3, that becomes 3c1 here, which is 3, 3c1, 3c2 here, which is also 3, and you end up getting this expression. It helps to remember this as well. It's helpful in complex numbers later on as well. Sometimes they ask you to evaluate cubes like this. I would recommend that you remember this identity or just use binomial. A plus b whole cube is a cube plus 3a squared b plus 3ab squared plus b cube. We use that to expand this thing. So cos square x plus sine square x cube, that expands to this. Okay, that's what they hinted towards. They said by first expanding this thing, okay, we've done that expansion. Then we simplify this. Now, what do we want at the end? We want cos raised to power 6x plus sine raised to power 6x equals 1 minus this. Okay, so when we expand this, we are getting this thing after simplification. Now, on the left side, we've got cos square x plus sine square x whole cube. Since we don't want that in the final result anywhere, we can say cos square plus sine square is 1. Just replace that with 1. So that gives us 1 on the left side. We want this 1 here, right? And then on the right side, now we have this. We want to keep this thing on one side, take everything else to the other side. This is the other thing that we're left with. So now think of these two terms. How can you simplify this? You can take 3 cos square x sine square x common from this. That leaves you with cos square x plus sine square x inside, which becomes 1. And then you have 3 cos square x into sine square x. You have to find a way to convert it to this form. How do you do that? This is a double angle. You have the double angle identity for sine. Sine 2 is 2 sine a cos a. If you square that, because you want to square here, you can square that. Squaring that gives you sine square 2a equals 4 sine square a into cos square a. And then you could say this is cos square sine square. If you want to replace it with the double angle, you can divide by 4 on the other side. This 4 can go to the other side and you get sine square a cos square a that is identical to this. And now You can replace cos square into sine square with 1 over 4 sine square 2x, rearrange that, and you get that form that was required. A lot of thinking for 4 marks. Sometimes it can get as complicated as this. Again, I'm leaving this here. You can have a look at this a bit slowly later on as well. This is another example. We have to solve this equation, tan cube plus 2 tan 2x minus tan x equals 0. We have to show that it can be expressed in this way. Now, the first part is not that difficult because we just have to apply the double angle identity for tan here. This is tan of 2x, right? So apply the double angle identity for that. Simplify that. You're getting tan raised to power 5x here. You can take tan common outside. If you take tan common outside, you get tan x equal to 0 from that. The question tells you that tan x is not equal to 0. So that does not give you anything. The other equation, when simplified, that gives you that form that they wanted. So the first part is fairly straightforward. But then they say, hence solve this equation, tan cube 2 theta plus 2 tan 4 theta minus tan 2 theta is equal to 0. Now, in the first part, what we did was we started from an equation like this, tan cube x plus 2 tan 2x minus tan x equal to 0, and we showed that that could be written in this form. Okay, now compare with that. In place of x, we've got 2 theta, and that's it. That's the only thing that has changed, right? In place of x, we've got 2 theta. So in this form as well, what we do is we replace x with 2 theta, and then we solve it further. Now it's a quartic equation, right? Power 4 equation. We can use substitution to make it a quadratic. It's a disguised quadratic, right? Power 4, power 2. We could treat it as a disguised quadratic, hidden quadratic equation, solve it as that quadratic at the end. You put that substitution back, tan square 2 theta is equal to that or equal to this. Tan square cannot be negative, right? A square number cannot be negative, so we don't get anything from this. For the other one, we take square root. We get plus minus square root of 3. Do not forget plus minus whenever we take square root. For any even root, sometimes you have to take fourth root, sixth root, square root, all of these, they will always have plus minus with them. Any even root will have plus minus. So then we use a substitution. This is 2 theta. We could, since theta is given to be between 0 to pi, if a is equal to 2 theta, then a is between 0 to 2 pi. You solve this equation in terms of a. Tan could either be positive or negative. That means all the 4 quadrants are possible, right? Plus minus, that means all the 4 quadrants are possible. You write down the values of a in all 4 quadrants. You get this value, this value, this value, this value. Put that substitution back. A is equal to 2 theta. And that gives you the corresponding values of theta. So sometimes the trigonometry questions, they end up becoming quite long like this. It was only a 3-mark question. A lot of work for that, right? Yeah, okay. Let's move on. No, that's it. That's all that we had to do today on trigonometry. Have a look at these examples that I showed you at the end. These are some of the more complicated questions from recent papers. But that's it for today. I hope this was helpful. We end this here. If you have any quick questions, you can let me know. Okay, let's begin then. Differentiation, this is the next topic that we have. Now, first of all, this is P3 differentiation, right? So you need to know some concepts from paper 1 as well. They are prerequisite for paper 3. For example, you need to know the power rule of differentiation that you did in paper 1, finding equations of tangents and normals, increasing, decreasing functions, stationary points and their nature, first derivative, second derivative, and chain rule. These are concepts that you need to know from paper 1 as well, right? These are the major concepts that you had in paper 1. This was one rule that you did in differentiation in paper 1, and that was if you have anything raised to power n, the derivative of that is given by the power multiplied here, and then you subtract 1 from the power, and then you multiply by the derivative of the base derivative of what is inside the power, right? That was the power rule that we had there. Multiply by the power, subtract 1 from the power, and multiply by the derivative of the base. Base means whatever is inside the power here, right? That was one rule, the power rule of differentiation that you did in paper 1. If you have any constant multiplying outside, that remains as it is, that remains unchanged. You will have n multiplied with that, but no rule will be applied to k here, right? This box here that you see, that represents any expression in terms of x. So inside this box, you could have any expression in terms of x, any kind of function, linear, non-linear, doesn't matter. And this dash that you see on the box, that basically means the derivative of whatever that expression is, right? This is a notation that we will be using for the other rules now as well. So keep this in mind. Whenever you see a box there, that means you can have anything in terms of x in this in this box. Okay. Now this was one rule that you did in paper one. In the formula sheet, it's written like this. In the formula sheet, it says x raised to power n. The derivative of that is nx raised to power n minus 1. That's what the formula sheet says. Okay, this is, I've copied this from the formula sheet. It's written like this there. Nx raised to power n minus 1. But then this x could be replaced with anything else as well, any other expression in terms of x. So when we generalize this rule, we get something like this, that if we have anything raised to power n, the derivative of that, what is that? You multiply by n, subtract 1 from n, then you multiply by the derivative of the box here outside, right? Now, this is a pattern that we will follow for a lot of other functions like this as well. These are the different types of functions for which you need to know the derivatives for ln of x, e raised to power x, sine x, cos x, tan x, secant x, cosecant x, cot x, and tan inverse of x. In the formula sheet, you see that you have the derivatives of these functions written like this. On the right side here, these are the derivatives. If you have ln x, the derivative of that is 1 over x. If you have sine of x, derivative of that is cos x. If you have secant x, derivative of that is secant x tan x, and so on. You can see all of these rules here. If x is replaced with anything else, any other expression, there's one additional step that you have to do, and that is that you multiply by the derivative of that thing. So if you have ln of anything else, you multiply by the derivative of that outside as well, right? You apply that rule, ln of something, that is 1 over that thing multiplied by the derivative of that. And similarly for all the other rules as well, what we do is we multiply by the derivative of whatever is coming in place of x. So if you have sine of x, derivative of that is cos x. If you have sine of anything else, derivative of that is cos of that thing into the derivative of that. So whatever x is replaced with in these rules, you have to always multiply by the derivative of that outside as well. Now, in these rules, since you have x, derivative of x is 1. So here as well, we actually do have 1 multiplying outside as well. But since it's 1, it doesn't make any difference, so we don't write that. But if there happens to be anything else apart from x, in that case, the derivative of that thing would not be 1. So you have to explicitly multiply that outside like this. Okay, so these are some standard rules that you have. You can have a look at them. I'll just go through them quickly. E power x, that derivative of that is e power x, sine x, derivative of that is cos x, derivative of cos is minus sine, derivative of tan is secant square, derivative of secant x is secant x tan x, for cosecant x it's minus cosecant x cot x, for cot it's minus cosecant square x, and for tan inverse it's 1 over 1 plus x squared. You have all of these rules given. If x is replaced with anything else, you multiply by the derivative of that. Let's take an example. If you have 5 into ln of 3x squared, what's the derivative of that going to be? The 5, that's a number that's multiplying outside, that remains as it is. And then you say 1 over that, because that's what the rule for ln says. Whatever is inside that goes to the denominator, and you get 1 over 3x squared. But then you have to multiply by the derivative of 3x squared, which is 6x. You multiply that here, simplify everything, and that gives you 10 over x as the final result. If you have minus 3 over 5 into e raised to power 4x, minus 3 over 5, that's a constant that's multiplying, that remains as it is. Then you apply the rule for e power 4x. What's the rule for e power 4x? E raised to power something, the derivative of that is e power that remains as it is. But you have to multiply by the derivative of 4x, which is 4. So you multiply by 4 here outside. And then you simplify that gives you the derivative. Keep in mind, this is not the power function. This is not the power function. In functions like these, you do not apply power rule. You don't say you subtract 1 from the power, you multiply by the power. That does not work here. The difference between the power function and the exponential function is, in the power function, you have x raised to power something. X is in the base, and the power is some number. In exponential function, e is the base and x itself is in the power. This is different. This is not the power function. We apply the rule for e in this case. Let's take some other examples. If you had 4 into tan of 2x plus 1, what's the derivative of that? What's the derivative of 4 tan of 2x plus 1? This derivative is 4 secant square into 2x plus 1. The derivative of tan is secant square, and then you multiply by the derivative of 2x plus 1, which is 2, and that is what you have outside here. Derivatives of secant, cosecant, and cot, they are part of your syllabus. They are part of your syllabus. You have to know them. They're given in the formula sheet as well. I've copied this from the formula sheet. You need to know them. You do need to use them in the exam. Okay. Then you have minus 5 over 3 into cosecant of x cubed. What's the derivative of this now? Minus 5 over 3, that remains as it is. Derivative of cosecant. What's the derivative of cosecant? Minus cosecant into cot. Minus cosecant into cot. So we multiply that by minus cosecant into x cube into cot of x cube. But then you have to multiply by the derivative of x cube as well, which is 3x squared. You multiply that outside like this. And then you can simplify that to see the result. Now, in this case, when you find the derivative of cosecant, it's minus cosecant into that expression into cot of that expression, minus cosecant of that expression and cot of that expression. X cube is coming twice here, but the derivative is just going to be multiplied once here. We don't multiply the derivative twice because we are multiplying by the derivative of this thing. That's only appearing twice. We multiply with the derivative of that. That's 3x squared. That's only multiplied once like this. And then you simplify it afterwards. Let's take another example. Tan inverse of 4x. The two number that's multiplying outside, that remains as it is. Now the rule that we've got for tan inverse, that says derivative of tan inverse is 1 over 1 plus x squared. Whatever is coming in place of x, that will go to the denominator and it becomes like this. 2 remains outside as it is. We have 1 over 1 plus 4x whole squared times the derivative of 4x, which is 4. That gets multiplied there. Okay, and then you simplify that, you get the result. Similarly, you can look at these other examples. Derivative of minus 4 over 5 into tan inverse of 2x cubed. You can see that evaluated here on the right side. If you have 4 sine of x squared, derivative of sine is cos. So you have cos of x squared times the derivative of x squared outside, which is 2x. But then think about 3 sine square x. Think about this now. Derivative of 3 sine square x. How do you do that? Derivative of 3 sine square x. Now, what function is this? This is actually a power function. Sine square x, we talked about this in trigonometry earlier as well. It's actually just a short way of writing sine of x whole squared. The actual function is this, sine of x whole squared. Now, the main function that you have here is the power function. It's power 2 outside, right? So in this case, you don't apply the rule for cos first, you apply the power rule first. You always start differentiating from the outermost function. The outer function in this case is the square function. You will have to apply the rule for the power function here. What's that rule? You multiply by the power, you subtract 1 from the power, you multiply by the derivative of sine outside, which is cos, and that gets multiplied here. Then you simplify this, you get your result from that. Similarly, if you had secant square of 2x plus 1, what about this? The proper way of writing this is secant of 2x plus 1 whole squared, right? And now that is a power function, right? The outer function is the power function. So the power rule will apply here. 8 outside remains as it is. You apply the power rule, you multiply by the power, subtract 1 from the power, keeping that expression inside as it is. And then you have to multiply by the derivative of secant into 2x plus 1, secant of 2x plus 1. What's the derivative of secant? Derivative of secant is secant x tan x. Derivative of secant is secant x tan x. So what's the derivative of secant of 2x plus 1 going to be? Secant of 2x plus 1 into tan of 2x plus 1 multiplied by the derivative of 2x plus 1, which is 2. And that's the result that you get from this. Okay, then you simplify this and you get your final result. That's the derivative. That's how you differentiate this. If you have ln of sine of 2x, what about this now? The outer function is the log function. So it will become 1 over sine 2x, right? We have to apply the rule for log. The rule for log says ln of something, the derivative of that is 1 over that thing, times the derivative of that. So it becomes 1 over sine 2x, but then you multiply with the derivative of sine 2x, which is cos 2x times 2. And then you simplify that, you get a result. You can write that in terms of cot as well, because that becomes cos over sine, and that gives you the result. Have a look at this example. Now, in this case, the outer function is the power function, right? We've got whole squared, so we apply the power rule, and then we multiply with the derivative of what is inside here. That becomes 1 over 4x times 4, and then you simplify that to get the result, right? That's how differentiation works. When you have one function inside another function, so if you have just a single function, then you just apply those rules that I showed you in the beginning. If you have one function inside another function, you always start differentiating from the outermost function. You always start differentiating from the outermost function. Okay? The rule will be applied for the outer function. So in this case, the power function is the outer function. That's what the rule, that's the rule that we apply here. In this case, log is the outer function, you apply the rule for log here, and so on. In previous examples, in this case, for instance, sine was the outer function, we applied the rule for sine. This was power as the outer function, we applied the power rule here. So we start differentiating from the outermost function in this. Okay, all right. Now, so we talked about simple functions, and we talked about the case when you have one function inside another function. Then what happens when you have products? Let's think about this example. If you had just x squared plus sine x, if you had plus or minus, you could just differentiate each term separately. You could differentiate x squared separately, that gives you 2x, sine x separately, that gives you cos x, and you just add them up together, and that gives you the result. However, if you have a product, x squared into sine x, you cannot just differentiate this separately and differentiate this separately and write it as 2x into cos x. That's not correct, because this whole thing is a single term. This whole thing is a single term. It's not multiple terms. You can't differentiate every single element of that separately. That's not going to work. We have to use something that we call the product rule for differentiating something like this. If you have two things multiplying u into v, the derivative of that, as given in the formula sheet, is this: u into dv over dx plus v into du over dx. In short form, we can write it like this and remember it like this. It's uv dash plus vu dash, right? Where u is the first expression that you have, v is the second expression that you have. They're anything in terms of x. They're expressions in terms of x. Okay, any expressions in terms of x. Now, of course, the variable could be different as well. Sometimes you can have y as well or some other variable. That's also possible. But in this case, the variable is x. So u and v are any expressions in terms of x. For example, if you have y equals x squared into sine x, how do you find the derivative of this? We can say x squared is u, sine x is v. The derivative would be uv dash plus vu dash. So u as it is, first of all, that means x squared as it is, into derivative of sine, which is cos, plus v as it is, that means sine x as it is, into derivative of x squared, which is 2x, and that gives you the derivative. Similarly, you can look at these other examples. Ln of 2x into tan inverse of 4x, you apply that product rule on this, uv dash plus vu dash, and that gives you the result. You can have a look at this. We're just using those same rules that we talked about above. Ln 2x remains as it is, into tan inverse of 4x. What's the derivative of that? That's 1 over 1 plus 4x whole squared times 4, and that simplifies to this. If you want, you can write this separately first like this, like I've written here. Write down u there, v there, u dash, v dash, and just input values in the formula. Or once you've done some practice, and hopefully you have done that practice, it's not very difficult to just do it directly here and then simplify that. This is the result that you get from this. Okay. It doesn't matter. It doesn't matter which one you do first. So uv dash plus vu dash or vu dash plus uv dash, since we are adding them, it doesn't make any difference which term you write first. I think in the formula sheet, they write it as vu dash plus uv dash. Doesn't matter. They're just getting added. It would not make any difference. Moise will talk about that in integration. We'll do integration next. Your question will be answered there. Okay. All right. So that's what we get. Let's move on. When we have a quotient, when we have a fraction, one thing divided by another fraction, divided by another expression, how do you differentiate this now? For this, we have something that's called the quotient rule. We say that's u over v. The derivative of u over v, as given in the formula sheet, is this: v into du over dx minus u into dv over dx divided by v squared. You can remember it like this in short form: vu dash minus uv dash divided by v squared, right? U dash means the derivative of u, v dash means the derivative of v. So vu dash minus uv dash divided by v squared. In this case, order matters. In this case, it has to be vu dash minus uv dash. It can't be the other way around, because in case of minus, it does make a difference which term you write first, which term you write second. So it has to be exactly like this: vu dash minus uv dash. You cannot interchange those terms. For example, if you have sine x over 3x squared, how do you differentiate that? You just input values in the formula. U is sine x, u dash will be cos x, then v is 3x squared, v dash would be 6x. Just input values in the formula, vu dash minus uv dash divided by v squared, and simplify that, you get this result. Okay. This is another example. You can have a look at this. The same thing. We have two expressions. We call one of them u, the other v. Find their derivatives and put them in this rule and simplify that. Okay. All right. Next thing we have is implicit differentiation. Implicit differentiation. Now, what's that? So we talked about what happens with products, what happens with quotients. Sometimes the derivative that you have is a bit more complicated. So all the examples that we've done until now, in all of them, y used to be the subject, right? Y was the subject. We could just differentiate that directly, dy over dx, and that gives you something. For example, the derivative of tan x is secant square x, so it becomes 3 tan x becomes 3 secant square x when we differentiate that. However, sometimes you end up getting functions like these or equations like these in which y is not the subject, Now, one idea could be that you could try making y the subject, but that's also not going to be possible generally. And when you do not have y as the subject, the expectation would be that you would have to use implicit differentiation there. Okay, so that's what you would do. Now, what is implicit differentiation? When y is not the subject, that is when we use this. For example, if we have an equation like this and we want to find dy over dx. Now, what does it mean, dy over dx? Derivative of y with respect to x, right? That's what you want to find out. We want to find the derivative of y with respect to x. To find this, what we do is we differentiate this whole equation with respect to x, right? We differentiate this whole thing with respect to x. Now, how does that work? 3 remains as it is. You apply the power rule on this, right? X squared, apply the power rule, you multiply by 2, subtract 1 from the power, but then you have to multiply with the derivative of the base, right? What's the base? Base is x. Derivative of x is just 1. So if we wanted to, we could write that it's multiplying by 1 here, right? However, we generally don't write that because it doesn't make any difference, because it's just 1. Derivative of x with respect to x is 1, so that will remain as it is. However, when you apply the power rule in this case now, you've got -2, that's a constant. You multiply by, you apply the power rule in this now, you multiply by the power, multiply by 2, subtract 1 from the power becomes 1, y power 1, but then you have to multiply by the derivative of the base. Derivative of y with respect to x, what's that? That's not 1, that's dy over dx. That's actually what we're looking for in the first place. Dy over dx, we want to find that. Derivative of x with respect to x, if we do that, derivative of x with respect to x, that equals 1, right? Dx over dx, that's 1. But dy over dx, we don't know what that is. We just write that as dy over dx. We have to find that out. Okay. So whenever in implicit differentiation you have a term that has y in it, remember it'll always get multiplied by dy over dx. You'll always have dy over dx there because derivative of y is given by dy over dx. Now on the right side, since you're applying this operation on both sides, on the right side, we have 6. What's the derivative of 6? That's 0. 7y, what's the derivative of 7y? 7 remains as it is. Derivative of y is dy over dx. So we multiplied by dy over dx. That's how implicit differentiation works. Okay. Now this is one step. Mostly that one step is going to get you 2 marks if you've done correctly. differentiation part is done in this step. Now what you have to do is, since you're looking for dy over dx, you just have to make dy over dx the subject. How do you do that? You bring all dy over dx terms to one side, like I've done here. I've taken everything to the right side, all the dy over dx terms to the right side, take dy over dx common and divide whatever is inside the bracket on the other side, and you get the derivative from that. In this case, that turns out to be this. And in most cases, in implicit differentiation, the derivative will have both x and y in it, right? So we have both x and y in the derivative here. In most cases, that's what happens. You get both x and y in the derivative, and when you do implicit differentiation. Okay. This is another example. You can have a look at this. You can have products here as well. For example, in this case, you've got x, y. What's the derivative of x, y? It's a product, two things multiplying. So we'll have to apply a product rule in this case. We can say x is u. We can say y is v. What's the derivative of x, y? It's uv dash plus vu dash, right? Now, how do you apply that? X as it is into derivative of y. What's that? That's dy over dx plus y as it is into derivative of x with respect to x. That's just 1. So that's the differentiation that we've got for that product, first of all. Now, once that is done, what about this? Derivative of 4 sine y minus 4 sine y. Minus 4 is a constant that remains as it is. Derivative of sine is cos, so it becomes cos of y. But then you have to multiply by the derivative of this thing. What's the derivative of y? That is dy over dx. If we just had 4 sine x here, in that case, we would have written it as 4 cos x and not multiplied by anything, because derivative of x with respect to x is actually 1. But derivative of y with respect to x is not 1, that's dy over dx. So we have to multiply that explicitly on the side. On the right side, we have 7. Derivative of 7, that's just a constant, that's 0. Derivative of minus 5 secant x, that's secant x tan x. Minus 5 secant x tan x. Again, you just make dy over dx the subject after this, and you get the derivative. That's your final result. Okay, that's how this implicit differentiation works. ILATE, where does that come from? That is for integration. ILATE is for integration. That's not for differentiation. Okay. Now, when you do implicit differentiation, you often get questions like these. They'll ask you for stationary points. They'll ask you for the points where tangent is parallel to x-axis, for instance. Whenever they say tangent is parallel to x-axis, or they say we have a stationary point, both of these mean that the derivative is going to be equal to 0. So whenever you're looking for stationary points, you've done that in paper 1, dy over dx is supposed to be 0, right? Dy over dx represents the gradient of a function. So at the turning point, the gradient is supposed to be 0. That's why dy over dx is equal to 0. Similarly, if they say at a particular point, the tangent to the curve is parallel to x-axis. Parallel to x-axis, what does that mean? It's a horizontal tangent like this. And if the tangent is horizontal, that means the gradient of the tangent would be 0. And whatever is the gradient of the curve of the tangent, it will be the same as the gradient of the curve as well. That would also be 0. So in both of these cases, what you would do would be you would find the derivative for that equal to 0. Okay. Then sometimes they would say the tangent is parallel to y-axis. What happens in that case? Tangent parallel to y-axis, what does that mean? You've got something like this. You've got a curve, right? And at some point, the tangent is parallel to y-axis. It's a vertical tangent. What's the gradient of vertical lines? Gradient of vertical lines is undefined. It's undefined gradient. How do you get something that's undefined? You have 0 in the denominator. You're dividing by 0, basically. So in this case, if you think about the gradient formula, change in y over change in x, for a vertical line, there's no change in x. So denominator becomes 0 for that reason. What happens in such cases is we would have the derivative in the form of a fraction. For example, we could have something like this, 2x minus y over x squared plus y. Let's say we apply differentiation and we get this as the result. If they say tangent is parallel to y-axis, what we would do would be, we would put the denominator of that derivative equal to 0. Not the whole thing, only the denominator equal to 0. So x squared plus y, we would say that is equal to 0. And that gives you y equals minus x squared. That will be one equation that you have. You will solve this simultaneously with the equation of the original curve that would be given. We'll have a look at a couple of examples, and then you'll get that point that you're looking for. Okay, so when you have tangent parallel to y-axis, what you do is you put the denominator of the derivative equal to 0, only the denominator equal to 0. Okay, like this. This is an example. You have a function here like this. You want to find the derivative of that in the first part. You've done that here using implicit differentiation. You can have a look at this working. It's not that complicated. on the right side, we have to apply a product rule in this, right? Because that's a product. I've taken 3 common outside and then applied the product rule on x, y. So that becomes x dy over dx plus y into 1, and then just made dy over dx the subject, rearrange that, and that got me this. Now, sometimes in problems like these, if they ask you to prove this thing, y minus x squared over 2y squared minus x, sometimes what happens is you end up getting something slightly different. You might end up getting x squared minus y over x minus 2y squared as your final result. Now, how do you go from this form to this form? What's the difference between the two? You've got y minus x squared. This is x squared minus y. So the terms are interchanged, right? And they're negative of each other. Similarly, in the denominator as well, the terms are, the signs are switched. It was supposed to be 2y squared minus x, and you're getting x minus 2y squared. If that's the case with both the numerator and the denominator, what you can do is you can say, let's multiply and divide by -1. We can multiply and divide by the same number, right? It does not change the fraction. So if you multiply and divide by -1, what happens in the numerator is you end up getting y minus x squared, and in the denominator you get 2y squared minus x, and that's the result that you wanted, right? Sometimes when you want to prove something, you end up getting this other expression. You would multiply and divide by -1, and that will be the result. If they had asked you to just find the derivative, in that case, this would be correct, this would also be correct. If they want you to prove something, like in this case, they want you to prove that the derivative is this, then you have to make sure that you convert it to this form somehow. And you have to show the process of how it is going to that form. Okay, so in that case, this is what you can show. You can multiply and divide by -1, and that will give you this result. It's important that you show the exact form that they want in the question in this case. If they're just asked to define the derivative, in that case, both of them will be acceptable. Otherwise, in this case, it's not. Okay, now, in the second part, they say, find the coordinates of the point other than the origin, where the curve has a tangent which is parallel to x-axis. Parallel to x-axis, what does that mean? Dy over dx, that should be equal to 0. So whatever dy over dx you found in the first part, you put that equal to 0. Okay, so that gives you y equals x squared eventually. Now, you've got two unknowns, y and x, only one equation. How do you find the values of y and x from this? You want another equation that connects x and y. Now, this point lies on the original curve, right? This point also lies in the curve. It's a point on the curve. So it should satisfy the equation of the curve as well. So we say we've got this equation. This is one equation. This is another equation. We solve them simultaneously. Generally, this will be done using substitution. In fact, always it will be done using substitution. You'll put this in the other equation, solve that equation, find the values of x from that, put them back in the first equation, find the corresponding value of y, and you get that point from that. We were getting 2 points here. For one, x was 0. For the other, x was equal to 1. In the question, they said that we wanted the point other than the origin. That way, we ignored the point that had x equals 0. If they're not specified that, then we would also consider the origin as a possible point. In this case, we just consider 1, x equals 1, and y equals 1 in this case as well. That's the point that we were looking for. Similarly, they could say the tangent is parallel to y-axis as well. This is an example of that. In the first part, they want you to find that derivative. You can look at the working for that using implicit differentiation. In this case, you see, when I did this the first time, I ended up getting minus y over x into 1 minus 3y cubed. They wanted a slightly different form. They wanted 3y cubed minus 1 in the denominator, and I was getting 1 minus 3y cubed. So in order to go from this form to the form that they want, we could just multiply and divide by -1, right? And then that will change it to that form that they want. Now, the first part is done. The second part says, find the coordinates of the point where the tangent is parallel to y-axis. Now, this is the derivative that we got. What we do is we put the denominator equal to 0. Denominator equal to 0, right? We put the denominator equal to 0. That gives us values of x and y. X equals 0, y equals this. Now, this is not these are not the coordinates of one single point. It's either x equals 0 or y equals this. These are two separate points. You have to input them in the other equation now, which is the equation of the curve, to find their corresponding y and x values. You input x equal to 0 here, you get the corresponding y value, which is not possible in this case because you get something negative. Yeah, you get 0 inside log here. That's not possible. So you don't get anything useful from that. For the other value, when y is equal to 0.69336, you input that here, and that gives you a corresponding value for x, and that's the point that we wanted. You can find that by solving these two equations simultaneously like this. Okay. Then you've got parametric differentiation. Parametric differentiation. What is parametric differentiation? In this case, you would have two equations given. You'll have x and y defined in terms of a third variable. In this case, that third variable is t. Mostly that's what it is. These are called parametric equations when x and y are defined in terms of a third variable. Okay. To find dy over dx from these two equations, this process is called parametric differentiation. This process is called parametric differentiation. Okay. Now, how does this work? How does this process work? Y equals 4 sine t, x equals minus 3t squared. We differentiate each of these two functions separately. Derivative of 4 sine t, what's that? That's 4 cos t. Derivative of x equals minus 3t squared. So we are differentiating both of them with respect to t here, right? So this is y equals this. Y equals 4 sine t. We differentiate that with respect to t. That turns out to be 4 cos t. X equals minus 3t squared. We differentiate that with respect to t, and that turns out to be minus 6t. Now we've got dy over dt and dx over dt. What we want to find out is dy over dx. Now, how do you find dy over dx? That should remind you of something. Chain rule that we did in paper 1. Dy over dx, we could write that as a product of two fractions. We write it like this. We want dy over dx. That means it's going to be a product of two fractions. In the first fraction, the numerator is going to be dy. In the second fraction, the denominator is going to be dx. And then in these remaining places, you've got whatever the third variable is. The third variable is dt. In this case, you write dt here and dt here. Dy over dt into dt over dx. That's the chain rule that you get. You input values in this, and that will give you dy over dx. So 4 cos t into 1 over minus 6t. Why 1 over minus 6t? We had dx over dt here. We take reciprocal of that because we've got dt over dx and input that here to get dy over dx from this. And that's the derivative. Now, in this case, you see the derivative is going to be in terms of t, not in terms of x and y. In parametric differentiation, the derivative that you get eventually, that is going to be in terms of t like this. Okay, that's the result that we get. Okay. Okay, so if you have specific questions, we could discuss them at the end, right? So once we're done with the topic, we would discuss them then. Otherwise, it'll slow down things a lot. So there are going to be some questions which are quite difficult. You'll have to go through them in your own time again, because the idea of these sessions is I'm just going to quickly, tell you that these are the different types of questions that you would see. If you want to understand them in a bit more detail, you will need, if you have not done these questions before or similar questions before, you'll need to spend a bit more time trying to understand them. We could discuss them toward once we're done with the topic, or you could have a look at the notes again as well, and that will, when you think of it slowly in your own time, hopefully that will make a bit more sense as well. Okay, let's just move on. I'll take your questions, the bigger questions at the end. The parametric equations of a curve are these. You've got these parametric equations. They want you to find dy over dx. How do you do that? We've got x equals ln of tan t. You find dx over dt from that, right? So you apply the rule of ln here. That becomes 1 over tan t into derivative of tan, which is secant square. That's dx over dt. Similarly, you find dy over dt here. Remember, this is the power function, sine square t. So it's sine t whole squared. That's the actual form that we've got for this. The outer function is the power function. We apply the power rule on that. And then we have dy over dt and dx over dt. We can just input them in the chain rule, simplify that, do some cancellation. This is what you end up getting. 2 sine square t into cos square t, because we had tan there. We could write tan as sine over cos. Secant square, reciprocal of secant is reciprocal of cos. So if you bring that to the numerator, that becomes cos, and it simplifies like that. Now, once we've got dy over dx, they're saying find the equation of the tangent to the curve at the point where x is equal to 0. But how do you find equations of any line? You want two things, gradient and a point. Now, do you have the gradient? No. Do you have a point? You know the x coordinate of the point. So you need the point and the gradient to be able to write down the equation using y minus y1 equals m into x minus x1. Now, how would that work? You have x equal to 0. You have to find the corresponding value of y from this. How do you do that? You would first have to find the value of t that corresponds to this value of x. Once you have that value of t, you would input that value of t in the other function to get the corresponding value for y. Now, x equals ln of tan t, that's what we're given. And we're given that we want the equation of the tangent when x is equal to 0. So we put x equal to 0 here, solve this equation, find the value of t that we get from this. Once we've got that value of t, we input that in the other equation, y equals sine square t. That gives us the corresponding y value. So now we've got a point. That point is x equal to 0 and y equal to 1 over 2. That's the point that we've got 0, 1 over 2. Then we have to find the derivative. Once we have the value for t, we know that dy over dx is this. We can input that value of t there and then just simplify that. If you have sine square t, in the calculator, you would have to input it like this, sine t whole square like this, right? So you input that in the calculator, simplify this, and that gives you the gradient of the tangent. That's 1 over 2. You have a point that's 0 and 1 over 2. You can write down the equation that turns out to be this, y equals half x plus 1 over 2. Okay. Now, in this case, you were given a value for x like this, right? For which you could find the corresponding value for y and then write down the equation of the tangent. Sometimes what happens is they say something like this. So in the first part, it's just parametric differentiation. Again, you've got x equals this, you've got y equals this. You have to find dy over dx in the first part. Now, is there a lag? Is there any lag? No? Which question? This one, Imani? Is there something wrong here? Okay. No, that's correct. There's no problem there. So 1 over secant square. When you have 1 over secant square, that becomes cos square t, right? So it's the reciprocal. We don't have to put power -2 there. It's just the reciprocal, right? So when it goes to the numerator, it becomes cos. If we had cos in the denominator, and if we had to take that to the numerator, that will become cos power negative. But when you have secant in the denominator, that becomes cos when it goes to the numerator. Okay, let's come to this now. And now again, in the first part, they wanted to find dy over dx in terms of t. How do you do that? You find dx over dt. That turns out to be this. Dy over dt, that turns out to be this. And then use the chain rule to find dy over dx from that. Okay. Now, they are asking us to show that the equation of the tangent to the curve at the point with parameter t is this. Now, what does that mean? At a point with parameter t. In the previous question, they told you a specific point when x was equal to 0. Here they're saying at a point with parameter t. All that means is your equation of tangent is going to be in terms of t, right? We don't have a value given. It will be in terms of t, okay? And you can see that here as well, the equation that they've given us, that is in terms of t. So you would say x is equal to a cos cube t, that's given in the question. Y is equal to a sine cube t, that's given in the question. So any point on this curve is going to be of this form. X coordinate would be this, y coordinate would be this. So we could say this is a point on the curve. We could say this is x1, this is y1, right? This is x coordinate of a point, this is y coordinate of the point. And then what about the gradient? Gradient is what we found in the first part, that's minus tan t. Again, that's also in terms of t. So this could be the value for m. And then all we have to do is input this inside y minus y1 equals m into x minus x1. Simplify that and try to convert it to the form that they wanted. They wanted something like this. So in that form, you have sine and cos on one side and sine t cos t multiplying on the other side. What you have here is tan. So first of all, you convert tan to sine over cos and then simplify things, use some trigonometry, take a sine t cos t at this point, in the brackets, it becomes cos square t plus sine square t, which is 1, and that simplifies to that form that you want. Okay, so sometimes you have to do something like this as well. You can have a look at this working in your own time. That's how you would work with this. So when they ask you to find something in terms of t, what that means is, if they want you to find the equation of a tangent with parameter t, you just have to find that equation in terms of t, right? In terms of t. So the equation would have t here as well. Okay, that's what you have to do in this part. You can have a look at this working in your own time. As I said, just show that to you here. Okay. Then they're saying hence, so that if this tangent meets the x-axis at x and the y-axis at y, then the length of xy is always equal to a. Now, don't get worried by this statement that it's always equal to a. It'll automatically turn out to be that. They're saying the tangent, that the equation of tangent that we found here, that was this. It meets the x-axis at x and the y-axis at y. That means its x-intercept is x, the y-intercept is y. Then the distance between x and y, that is supposed to be a. You have to show that. Now, you've got the equation of the tangent that looks like this. This is the equation of the tangent. In that equation, you put x equal to 0, that gives you the y-intercept. You put y equal to 0, and that gives you the x-intercept. Find those points, x and y, and then input them in the distance formula. X2 minus x1 whole squared plus y2 minus y1 whole squared, square root of that, simplify that, and you get that result that the distance turns out to be a. Okay. Now, in a lot of questions involving differentiation, you will find that you'll have to take something common to simplify things. In the previous example, for instance, in fact, in the same question in part B, we had to take sine t cos t common here. That left us with cos square t plus sine square t inside, which simplifies to 1, and that just left us with a sine t cos t. While we are solving equations or proving something like this, a lot of times you need to take things common outside to simplify things. In this case as well, you see, we had to prove that this distance turns out to be a. Now, inside the square root, when we took a squared common, that left us with a cos square t plus sine square t inside, and that becomes 1, and it just simplifies to a eventually. Right? Again, have a look at this working again. You'll have these notes available. Okay, now sometimes what happens is, this is something that you should know from paper 1 as well, but just as a reminder, remember, how do you find maximum or minimum point of any function? For example, if you had a function y and they wanted you to find the turning point of y, that means the maximum point of y or the minimum point of y, or they said stationary value of y. How do we do that generally? We find dy over dx and put that equal to 0, right? That's what we do. If you're looking for the minimum or maximum value of a function, that's what we do. We find the derivative, put that equal to 0. But sometimes what happens is, they will not ask you for the maximum minimum value of a function, but instead of that, they would say, find the maximum or minimum value of the gradient. Not the original function, but the maximum or minimum value of the gradient of a function. For example, if we have a function that looks like this, y equals this, and they want the maximum value or minimum value of the gradient. Now, you're not just going to say that find the derivative and put that equal to 0. No, that is actually going to give you the maximum minimum of the function. That's not what we are looking for here. We are looking for the maximum minimum value of the gradient. Now, for a curve, the gradient is given by its derivative. So what you would do would be, you would find the derivative and you would treat that as a new function. You would say dy over dx is equal to this. Let's call this the gradient function. So what I've done is I've represented it with another letter. So forget about the original function now. This is the gradient function. 10 cos 2x plus 3 sin x. That is what we're talking about. This represents the gradient of the graph. I've represented this using the letter G, the gradient function G of x, for instance. You could use any other letter for this. It doesn't really matter. But the idea is, the maximum or minimum value that we're looking for now is the maximum or minimum of the gradient. So how do you find maximum or minimum of any function? You find the derivative, you put that equal to 0. So what you would do would be, for this gradient function, you would find the derivative, put that equal to 0, and then you simplify that, solve that equation, and that gives you the result. Okay, so you don't put dy over dx equal to 0, but you find the derivative of the gradient, as in you find the derivative first of the original function. That turns out to be this. You treat that as a new function. That becomes the gradient function. You find the derivative of that, put that equal to 0, and that will give you the turning point, the maximum or minimum point of this. Okay, basically double derivative, but it's a bit confusing sometimes to say second derivative is equal to 0. And then if you had to find the nature of this, you'll find third derivative for that. A lot of people get confused by that why are we putting second derivative equal to 0? Why are we finding the third derivative in that case? That's a bit confusing. So for that reason, this is what I recommend. Whatever function you have, you find the derivative. If you're looking for the turning point of the gradient, you treat this as a new function. This is the gradient function. Find the derivative of that, put that equal to 0. Okay, but find the derivative of the gradient and put that equal to 0. Because we put first derivative equal to 0 for finding the maximum or minimum value. So we have to put the first derivative of the gradient in this case equal to 0. Let's look at this example. The diagram shows this y equals square root of 1 minus x over 1 plus x. It says by first differentiating this thing, obtain an expression for dy over dx in terms of x. Now, that's the first part. You just have to use the quotient rule here first. So you differentiate this using the quotient rule. You can have a look at this working. I've done that here. Then they want you to find the derivative of this. Okay. How do you do that? It's a square root function. You treat that as the power function like this. First of all, 1 minus x over 1 plus x whole raised to power 1 over 2. It's a power function. You multiply by the power, subtract 1 from the power, multiply by the derivative of the base of the power. That's what you end up getting. Then you simplify this and you get that derivative that you were looking for. Dy over dx turns out to be this. And then they're saying, hence show that the gradient of the normal to the curve, at the point xy is this. Now, how do you do that? Gradient of normal. You have gradient of the curve, dy over dx, that's the gradient of the curve. Gradient of normal is negative reciprocal of the gradient of the curve. So what you would do in this case would be, you would take negative reciprocal of this, change the sign, take reciprocal, and you end up getting this. That's the gradient of the normal. And then you have to somehow convert it to this. That's some algebra. You can have a look at this working, a bit complicated. You can try to understand this in your own time later. You will have to use the a square minus b square identity here. That's what I've done here. First of all, I split this into two parts. This is power 3 over 2. I split that into two parts, power 1 and power 1 over 2, because that's what they wanted here. 1 plus x separate. So we have 1 plus x separate here. And then on this other part, since the powers are the same, we could multiply the bases, a plus b into a minus b, that becomes a square minus b square, and you get that form that they wanted. So if you want the gradient of the normal, what you do is you find negative reciprocal of this, and that gives you the result. Okay, but then they're saying the gradient of the normal has its maximum value at the point P. What has its maximum value? The gradient of the normal, not the original, not the function, gradient of the normal. This is the point P. You can see that that's not the maximum point of this curve, right? It's something else. It's actually the point at which the normal is steepest, right? The normal at this point would be the steepest on this curve. It'll have the highest gradient. So they're saying gradient of the normal has its maximum value at the point P. Find by differentiation the x coordinate of P. Now, what are we looking for? We are looking for the maximum value of the gradient of the normal. Now, what's the gradient of the normal? We found that here. This is what represents the gradient of the normal. If we want to find the maximum value for this, how do you do that? This is the function. You treat this as a new function now. This is the gradient of the normal. This is not going to be the second derivative of the original function now, because we have taken negative reciprocal of that as well first. So it would not work that way. So you have to think of it as something, some new function now, right? Find the maximum value of this function. How do you do that? Like you do for any function, you find the derivative of this. That turns out to be this using the product rule. Put this equal to 0 and try to solve that equation. That requires some complex algebra here. You can have a look at this here. So this is actually something that will help you a lot in a lot of questions like these. When you do differentiation, sometimes you end up getting very complicated algebraic expressions. One thing that you should always do is whenever you have something that has a negative power, take that to the denominator. That will simplify things for you. This is power minus 1 over 2. You take that to the denominator and it becomes power 1 over 2. And now this is 1 minus x squared power 1 over 2. This is 1 minus x squared power 1 over 2. You multiply the whole equation by this denominator so that the fraction gets eliminated. So the powers get added here, 1 over 2 plus 1 over 2. And it becomes 1 as the power, and that simplifies things. You solve that further, find that x coordinate that you were looking for from that. Okay, so for finding the maximum or minimum point of anything, you find the first derivative of that, put that equal to 0. Now it depends on what that thing is. If it's the original function, you put the derivative of the original function equal to 0. If they're talking about gradient of the tangent or the norm, gradient of the tangent or gradient of the curve being maximum, then you have to find the derivative, treat that as the new function, and find the derivative of that new function and put that equal to 0. In this case, we had to find the maximum value of the gradient of the normal. For that, we put the derivative of this equal to 0. That gave us a value for x. Once we got that value for x, what did they want us to find out? The x coordinate of p, and that gave us the x coordinate of p. That turns out to be 1 over 2. We got two values here, 1 over 2 and minus 1. But on the diagram, we could see that the x coordinate of p was supposed to be something positive, not negative. So it had to be the positive value then. That's 1 over 2. Quite tricky question. You can have a look at this again as well to understand that better. Now, sometimes what happens is in the equations that you get, you end up getting letters like this, right? But they specify here as well. They specify here as well. They specified here as well that a is a positive constant, right? A is a positive constant. Now, a will be treated as a constant. A will be treated as a constant. Do not get confused by this. It's just like any number. So when you differentiate it, when you find the derivative of this using, implicit differentiation, you would treat a as a constant, right? So it will remain as it is in your working. The rules will not apply on this. For example, here you have ay squared. A remains as it is, and the rule for differentiation only applies in this 2y into dy over dx, right? And similarly here, minus 3ax squared, minus 3a remains the same. You multiply by the derivative, that is 2x, and that's the result that you get. You put that on the right side, you just have 0. Simplify this, find the value of dy over dx. They want you to find the x coordinate of m. M is the maximum point of the curve. Now, a very important and useful trick here that you can use, and that is when they do not ask you for dy over dx. In this case, they're not asking you for dy over dx. They're just asking you to find the point m, which is the turning point of this function. So in this case, as soon as you differentiate it once, you have done that differentiation step, it's not necessary here to make dy over dx the subject. They've not asked you for dy over dx. So rather than making that the subject, you can simplify things by putting dy over dx equal to 0 directly here. Because we're looking for the stationary point, at the stationary point, dy over dx is supposed to be equal to 0. So rather than doing all of that working of making dy over dx the subject first and then putting that equal to 0, it's much quicker and simpler that you put dy over dx equal to 0 right away here. that will eliminate some of those terms for you, and it will become much simpler. You get this equation from that: y squared equals 6ax minus 3x squared. That has two unknowns, y and x, and of course the answer has to be in terms of a, right? So that's another unknown as well. But that's one equation that you're getting. It has both x and y. We did one other equation. That's the equation of the curve. We solve these two simultaneously, and that gives us the values of x and y. This is y squared equal this. And the equation that's given here, we have y squared only. So we could just replace y squared with that expression, simplify that, find the value of x from that. They only wanted the value for x. That turns out to be square root of 3 times a, right? Sometimes it can get a bit complicated like this as well when they introduce letters like this. So this example was just to show you again that when you have differentiated, you would end up getting equations that look like this. For instance, you put this equal to 0. How would you solve such equations? They look very complicated at first. However, you would try taking whatever you can common outside, right? So after you've differentiated this and put that equal to 0, now you think of what you can take common from this. So in this case, e raised to power minus 3x is common in both of them. So we take that common outside. So it's factorized now. If two things are multiplying, that means either the first one is equal to 0 or the second one is equal to 0. So we get two equations from them. And now those two separate equations are much simpler to solve. You can convert secant square to tan square here and then solve that further after that. So once you have found an equation like this, try to see if there's anything that you can take common outside to make that simpler. So once you factorize that, you can put each of those expressions equal to 0 separately. This is another problem that I would, say that you can have a look at in your own time. We're done with all the major concepts. I've just added some difficult problems to the notes now that you can have a look at. For example, I'll just quickly tell you about what is being done in each of these questions, but you'll go through them in your own time later. In this question, for instance, they wanted you to find the first two turning points. So we found the derivative. We wanted this turning point and this turning point. We found the derivative, put that equal to 0 because that's how we find turning points. But since we were looking only for the first two turning points, we said, first of all, since x is greater than or equal to 0, we only consider values in that interval, positive interval, but we only want the first two. So when we solve that, we just stop at the first two values that we get. One value of x that we get is this, another is this, and that these are the x coordinates of those two turning points that we were looking for. You can have a look at this working. A bit complicated in the beginning. So you have to make sure that you understand how to factorize this. First of all, as I just showed you, you would have to look for what you can take common here, right? So in this case, you could take 10 e raised to power minus half x common outside and then split that into two equations like this. And then in the next part, they say it's like a one-off question that you'll find in past papers. It says it's given that the x coordinate of Tn, so some turning point at some point later on, is greater than 25, find the least possible value of n. So in this case, we had to look at a pattern in these turning points. So we had T1, the first turning point, that was this, T2 was this, T3 was this, and there was a pattern amongst these turning points that they were following an arithmetic progression. So the distance between these turning points, so this turning point, this turning point, this turning point, this turning point, they were at the same distance from each other, right? So we could make an arithmetic progression from that nth term formula, put that greater than 25 because that's the condition that they had there, that Tn x coordinate should be greater than 25. And then we find the value of n from that using that. Quite tricky, but it's a one-off. You can have a look at this and try to understand what's going on. Okay. Yes, it is a bit scary. It's okay. Don't worry. These are not very common questions. Okay, this is important. Equation of a curve is this. Equation of a curve is this. And in the first part, they say find the gradient of the curve at the point 2 minus 3. Okay, how do you do that? You've got this curve. You've got this curve. This is something in which y is not the subject. So you use implicit differentiation. Use implicit differentiation to find dy over dx. Now, what are they saying? Find the gradient. Gradient is given by dy over dx at the point 2 and minus 3. So once you find the derivative, all you have to do is put x equal to y equal to minus 3 in that, and you get the gradient from that. So that's pretty straightforward. Now, in the second part, it says, show that there are no points on the curve where the gradient is equal to 1. Now, what does that mean? How do you show this? There are no points on the curve at which the gradient is 1. Now, we have already found the derivative in the first part. That's the derivative. They are saying there should be no points where the gradient is 1. So that means if we were to try and put the gradient equal to 1, that means the derivative equal to 1, we should get no solutions from that. Okay, and that's what we do. We say, let's put the derivative equal to 1. Let's put the gradient equal to 1 and see what we get from that. When we put that equal to 1, we get x equals y from that. That's one equation that we have. Then we have the original curve, the original equation. We put this in that original equation. We get an equation that looks like this. When we simplify that, x terms, all of them, they get cancelled, and we're just left with 0 over 45, which is absurd. That's not true. So that means this equation has no solutions. If it has no solutions, that means there's no point on the curve at which the gradient is 1. So when they want you to show something that this is not true, or there are no points at which something is happening, what you do is you just input that thing and show that you get no solutions from that when you do that. So in this case, they were saying there should be no points when the gradient is 1. You put the gradient equal to 1, and you show that you get no solutions from that, and that will prove that there are no points that satisfy that condition. Okay, I'll come back to this example later. There was another very similar to that. Okay, I've got too many examples here. Okay, what I'll do is I will be skipping some of them now. You can have a look at them. These are just some difficult questions that I've lined up that I've copied here from recent papers and from other topical past papers. Okay, now this is something that I did want to show. The first part of this. So in the first part, they're saying, show that dy over dx is equal to minus y over x squared in this. Okay, minus y over x squared. We have to show that dy over dx is equal to minus y over x squared. Now, how do we do that? This is the function that we've got. Xl and y equals 2x plus 1. Xl and y equals 2x plus 1. Now, that's the equation that we've got. Now, one idea could be that we differentiated both sides. When we differentiate both sides, like we do in implicit differentiation, we get something like this. Now, what we're getting has ln y in this as well. The form that we want at the end, that does not have ln y in it. We want to show that the derivative turns out to be this. Now, when we try doing it the normal way, what happens is when we apply implicit differentiation, we end up getting ln y like this. Now, how do you get rid of that? You want to get rid of ln y. This was the equation that you had given in the question. You make ln y the subject here. Ln y equals 2x plus 1 over x. You replace it with that, and then you simplify that further, and eventually at some point you get that result minus y over x squared. That could be one way of doing this. But there could be a more efficient way of doing this as well. When we differentiate it directly like this, what happens is, we can see, since it's a product, x into ln y is a product, right? When we apply uv dash plus vu dash, we know when we have vu dash, we would end up getting ln y in the final result there. And that's not what we want. We do not want ln y in the final result. When we apply a product rule like this here, the ln y is going to remain there. So before differentiating, you could, if you end up being successful in thinking about this in an exam situation, what you could do to make it more efficient could be to avoid getting an ln y here. You could take this x to the other side first of all, so that it becomes 2 plus 1 over x, like this, for instance. And then you differentiate both sides after that. Now, when you do that, there's no product on the left side anymore. It's just x into ln y. It's just ln y that is left there. There's no product anymore. So now when you differentiate L and Y, you just get 1 over Y into dy over dx, and there's no L and Y in this case. Differentiate the right side as well, that gives you this. You make dy over dx the subject, and you get that result right away without that complication that we had at the end. So sometimes when they want you to show something, try to think about how exactly you could get to that form that they want quicker. So keep the end in mind. In this case, we were getting L and Y. In order to avoid getting L and Y, we could first take X to the other side and then differentiate it like this. Okay. This is another example. So what you had to do was you had to show that dy over dx equals this. Okay. Now you found the derivative. The derivative turned out to be, you can see the working for that. What I've done is I've evaluated dx over dt and evaluated dy over dt like this, right? Dx over dt and dy over dt. Then we find dy over dx from that. That turns out to be this. Okay, this is dy over dx. And now what I'll do is I'll get rid of this for you. Okay, so when we applied dy over dx, we got this thing as the result. Now we had to prove that the derivative is actually tan of t minus pi over 4. So we are getting this derivative. They want us to show this. We have sine and cos, and they have tan and then a compound angle there. Now the problem is, how do you go from this form to the form that they want? Now that's pretty complicated. If you do it directly like this, it's very unlikely that you get to that result directly. There's an alternative that you could use for this, and that would be, you found the derivative here. Now you just need to show that this derivative can be written in that form as well. So just like you can do in trigonometric identities, what you do is you start from the other side now. You say, okay, this is the derivative that they want. Instead of going from our form to the form that they gave us, let's simplify their form, right? Because it's difficult to convert this to a compound angle like this, as compared to going the other way around, that we simplify this compound angle. Apply the compound angle identity for tan. That gives us this. Simplify this. We get tan t minus 1 over this. Convert tan to sine over cos. Take LCM, simplify things, and you end up getting this result. And then you say that this is what we're getting here as well. Since both of these are equal, that means that is proof that the derivative turns out to be this and turns out to be that. So sometimes in more complicated questions, if they want you to prove something, you could work a bit backwards like this as well. The form that you were getting was this. It did not have any compound angles. In the form that they wanted, they had compound angles. It's much more difficult to go from this form to that form as compared to going the other way around. So what we do is, instead of trying to go from this to that, we go the other way around. We simplify that given form and convert it to the form that we are getting. And then we say they're both identical. So that means that's the dy over dx that we had. Okay. So sometimes you have to do it like this as well. Now, this is another problem. In the first part, they wanted us to find dy over dx and convert it to this form. You can see the working for that using the product rule of differentiation and then simplifying things. That's 5 marks for some reason. Fairly straightforward. But the next part says these two parts now. What are they saying? First of all, it says explain why the gradient of the curve is never negative. Why the gradient of the curve is never negative. Now, how do we explain that? This is the gradient that we're getting. This is the derivative, right? The gradient. E raised to power minus 2x into tan of x minus 1 whole squared. How is that never negative? This is a square. A square can never be negative, right? It has to be at least 0. It can't be less than 0. And this is e raised to power minus 2x. E is a positive number, 2.7128. A positive number any power of that can never be 0 as well. That always has to be positive as well. So you say this first expression has to be greater than 0. because e is a positive number. Positive number, any power is always positive. This is a square which has to be greater than or equal to 0. So that means the product, the overall expression dy over dx, that is also going to be greater than or equal to 0. It cannot be negative, right? Then they say, find the value of x for which the gradient is least. Gradient is least. Does that remind you of something? We want to find the turning point of the gradient, the turning point of the gradient. How do you find that? Turning point of the gradient. Now, what does that mean? One idea could be that we could find the derivative of this gradient, right? This is the gradient. Find the derivative of this, put that equal to 0. But how many marks is that? This is one. That's just 1 mark, right? That will be a lot of work for that. That could be possible, but that's a lot of work. Can we do it a bit more efficiently somehow? It says find the value of x for which the gradient is least. Now, we already proved in the previous part that the gradient is greater than or equal to 0. So the least value it could have could be 0. And when would that be? When would you have 0? When this expression tan x minus 1 is equal to 0. So for the gradient to be least, this expression inside that has to be 0, because this cannot be 0, right? E raised to power minus 2x, you can try taking log, that does not give you anything, you get an error. The other expression has to be 0, and from that you get x equals pi over 4. So the least value of the gradient, which is 0, that would be when x is equal to pi over 4. Okay. All right, just a couple of more examples. I feel like I'm scaring you at this point now. Maybe we could just, I could leave these questions with you as notes, and those of you who want to go through them, you could go through them. These are like the hardest questions that you would find. These are like the hardest questions you would find in past papers. I think it was probably not a good idea to expose you to them at this point, because it's not always like this. Like, you've got average questions, you've got easy questions, you've got difficult questions. Okay, so what would you suggest, by the way? What do you want me to? What do you want me to? Okay, so what's yes for here? As in, what was that in response to? That I'm scaring you guys? Okay. Yeah. Okay. Okay. So what we can do is, I will leave these questions for you to have a look at, and these are not that old. These are not that old. 2010s, and you've got the others coming now, which are more recent, 2020s. Okay, so I'll try to go through them quickly then. I'll try to go through them quickly, and then for those of you who are interested, you can, have a look at them again as well. Of course, if I don't expect you to be able to understand them in the 2 minutes that we spend on them, right? These are hard questions. When you're doing them, it'll take you like, if it's an 11-mark question, that'll take you like 15, 18 minutes to figure this out, to actually solve this. So in a couple of minutes, it's hard to understand them. So don't get scared because of that. When you read this slowly, what they're trying to ask, in these questions, they will not be as difficult as they probably seem at this point. Okay. Now we have this curve. It says find the x coordinate of the point P at which the tangent to the curve passes through the origin. Tangent to the curve, it passes through the origin. Now this is another kind of different type of question that you have. So you have a point P here on the diagram. The last part, that's what I'm talking about. They have this point P. At this point P, the tangent is passing through the origin. So if you draw that tangent, it's passing through the origin. Given this, we have to find the x coordinate of that point P. Now the point P lies on this curve. So we could say the coordinates of point P, they could be like this, x and x squared e raised to power minus x, right? If the x coordinate is x, the y coordinate would be this, x squared into e power minus x. Then at this particular point, the tangent passes through the origin. The tangent to the curve, it passes through the origin. What does that mean? If you were to draw this tangent like this, it passes through 0, 0. So can we find the gradient of this tangent somehow? y2 minus y1 equals y2 minus y1 over x2 minus x1, right? We could say the gradient of the tangent, that is this, y2 minus y1 x squared into e power minus x minus 0 divided by this. So that tangent should have this gradient using that gradient formula. And we have the derivative of the curve from the previous part. The derivative of the curve is this. At this particular point, when we have this tangent which passes through the origin, since the gradient of the curve and the gradient of the tangent, they're supposed to be equal to each other, we could say this is the gradient of that tangent, this is the gradient of that curve. They should both be equal to each other. So we equate them, and that gives us some value of x. That's how we could find that point P at which the tangent was passing through the origin. So given that it passed through the origin, we use the gradient formula to find the gradient of that tangent, y2 minus y1 over x2 minus x1. And then we use the derivative of the curve to find the gradient of the curve at that point, equate both of them, solve that equation, and get that value for x. Okay? We will be ending in a few minutes now. Equation of a curve is this. Find the gradient of the curve at which the y value is equal to 1. How do you do that? You find the derivative of this first of all. We're looking for gradient, right? That means the derivative. Find the derivative using implicit differentiation, and this is what we end up getting from that. This is the derivative. Now, the derivative has both y and x. The derivative has both y and x. Okay? We are only given the y coordinate. That's 1. So what about the x coordinate? We'd have to input y equal to 1 in this original function to find the corresponding value of x. So when we do that, when we put y equal to 1 there, we get an equation that looks like this. E raised to power 2x plus e raised to power x minus 6 equal to 0. And then you use logs to solve this equation. It's a substitution that you do. First of all, it's a disguised quadratic. You can write e power 2x as e power x whole squared. And then it's a quadratic. You solve it as a quadratic. And then you put that substitution back and apply logs to find the value for x corresponding to that value of y. And that value of x turns out to be ln2. So that means at that particular point, when y is equal to 1, the value for x is supposed to be ln2. You input that in this derivative now. Input the values of x and y in this derivative. Simplify that, and that gives you the result. That turns out to be minus 5/4. They did not ask us for an exact answer as such. So you could just put this whole thing on a calculator directly, and that would give you the result. That's minus 5/4. So when you have both x and y in the derivative and they just give you one value, you have to input that in the original function to get the corresponding y value. If they give you the x value, you have to find the corresponding y value. If they give you y, you have to find corresponding x, and then input that in the derivative like this. This is just again to show that in the functions you can have some, you can sometimes have something in terms of a like this as well. You can have a constant introduced. That should not scare you. That is just like any other constant, like 2, 3, 4, right? Just treat it like a constant. This is a. Find the derivative using the product rule. Equate that to 0 because we're looking for the turning point. And then you can find the value of x from that. Once you have the value for x, put that back in the original function to get the corresponding value for y, and that gives you that turning point that you're looking for. So when you have a like this in an equation, and they say it's a constant, just treat it as any other constant like you have numbers, right? Okay, now this is a curve for which you had to find the derivative. We found the derivative using implicit differentiation in the first part. In the second part, they say, hence show that the curve does not have a tangent that is parallel to x-axis. Now, how do you show that? That the curve does not have a tangent that's parallel to x-axis. We try to find that tangent that is parallel to x-axis. How do you do that? You put the derivative equal to 0. You try to solve that equation, and then you show that that is not solvable. You don't get any point from that, right? So you put the derivative equal to 0. That gives you this equation. You had the equation of the curve. You solve them simultaneously. That gives you an equation in terms of x here. And this quadratic that you get, this cannot be solved. Since it cannot be solved, that means there is no tangent that exists that is parallel to x-axis. And that's what you had to show. So when they ask you to show something is not true, then that means that you try solving for that and show that there's no solution that you get from that. Okay. Try making x the subject. Okay, so while you're solving this equation, yes, of course, you could do that. So in this case, while you're solving simultaneous equations, it is, of course, possible to make x the subject here, put that in the other equation, and then you'll get a quadratic equation in terms of y in that case, and that would also not be solvable. That will also not be solvable. Either of them works, it doesn't matter. Then you have this curve. You had to find the derivative of this. You found this derivative, and it turned out that we got that result. In the second part, they said, find the exact coordinates of the 2 points at which the tangent is parallel to y plus 2x equal to 0. So instead of saying that the tangent is parallel to x-axis or to y-axis, they're saying it's parallel to y plus 2x equal to 0. Now, what does that mean? What's the derivative of this equation? Y plus 2x equal to 0. What's the gradient of this straight line? It's a straight line like this. Y equals minus 2x. Y equals minus 2x. The gradient of that line is minus 2. So what you do is you find the derivative, which you've already found in the previous part, and put that equal to minus 2 in this case, right? Because if the tangent is parallel to that line, that means the gradient of the curve at that point should be equal to minus 2. So you put the derivative equal to minus 2 in this case. You get an equation from that, solve that simultaneously with the equation of the curve, and that would give you the value of x and y, the values of x and y from that. These are the 2 points that you end up getting. Why is it not ending? So we have another curve. In the first part, we just try to find dy over dx. Again, that's pretty straightforward. Use implicit differentiation. Find this derivative. In the second part, they say the tangent to the curve at the point where x is equal to 0 and at the point where y is equal to 0, they intersect at the acute angle alpha. Find the value of tan alpha. How do you do that? Now, in paper 1, you study angle between two lines. There's a formula that we got for this. Tan of alpha that equals tan theta equals m1 minus m2 over 1 plus m1 into m2. You need to memorize this formula for angle between two lines. This is something that you study in paper 1. Now, if the tangents meet at the acute angle alpha, what we can do is to find the angle between them, we can find the gradients of these tangents. How do you do that? You have the derivative. Derivative has both x and y, so we want both the x and y coordinates of these points. So one point is x equal to 0. We put that in the original curve, find the corresponding value of y from that. This turns out to be the point 0 minus 2. For the other point, we know that y is equal to 0. We put y equal to 0 in that curve, and that gives us the corresponding value for x. And we get another point here that's minus 2, 0. These are 2 points that we've got. At both of these points, we find the gradient of the curve. using the derivative. We had this derivative. In that derivative, you once put one of these points, then you put the other point, you get the two gradients of the curve at those 2 points. Gradients of the tangents are also going to be the same as these. So now we just use that formula. Tan of alpha, in this case, they're calling that angle alpha, is equal to m1 minus m2 divided by 1 plus m1 into m2. Input values in the formula and you get the result from that. Since the angle is acute, they mentioned that here. That's in the first quadrant. In the first quadrant, tan is supposed to be positive. So it has to be a positive result at the end. So you should choose M1 as the value that's bigger out of these two and M2 as the value that's smaller so that you end up getting a positive result out of that, right? The end result has to be positive because the angle that we want is an acute angle, right? So use this formula to find that angle. Okay, so those are pretty much all the different types of questions that you would see in differentiation. The last few questions that I showed you, they were from the last 2-3 years. And the others were 2010s, as in 2010 to 20. Some of the more difficult ones that I showed you. I hope that makes sense. If you have any questions now, let me know. All right, so the next topic is integration. Integration is part of paper 1 as well, and there are some concepts that you need to know about integration from P1. For instance, how to integrate expressions like this, mx plus c whole raised to power n. We could use the power rule of integration for this. We add 1 to the power, divide by the new power, and also divide by the derivative of the base, right? There was a condition here that the expression inside it had to be linear, right? This rule only used to work when the expression inside was linear, right? This was one integration rule that you studied in paper 1, and then you need to be able to find equation of a curve from its derivative. You integrate that and put a plus c. Whenever you integrate, you have a plus c, right? And to find the value of c, you can use a point that is given for that function. That's what you did in paper 1. And then there were area and volume formulas. You also need to use them in paper 3 sometimes. Area between a graph and x-axis, area between a graph and y-axis, volume of revolution about x-axis, volume of revolution about y-axis. You guys can see my screen, right? Anyone not able to see my screen? Okay, all right. So you need to know the area and volume formulas. Area and volume formulas from paper 1, area between graph and x-axis, y-axis, volume of revolution about x-axis, volume of revolution about y-axis. These are not given in the formula sheet. You need to remember them. In the x-axis formulas, you've got y and y square. In the y-axis formulas, you have x here and x square here. Limits are values of y in the second case. And for volume, do not forget the pi outside. Okay, these are the formulas that we've got. You need to use them here as well. Now, what's new in P3 integration? You need to be able to integrate a number of different types of functions. Now, this is one rule that you did in paper 1, x raised to power n. That integrates to x raised to power n plus 1 divided by n plus 1. Now, in integration, in the formula, in the general rule that you have, this x can be replaced with any other linear expression, and only linear expression. It can't be a non-linear expression. Okay, so if you were to generalize this, you could have something like this. If you have mx plus c or ax plus b, any of them, it doesn't matter. Mx plus c whole raised to power n. Integration of that would be mx plus c power n plus 1 divided by n plus 1 and divided by the derivative of the part that is inside. The expression that x is replaced with, whatever expression x is replaced with, that expression has to be a linear expression. Only then this rule would work. And then we have a number of other rules that are given in the formula sheet First of all, we've got e raised to power x. E raised to power x, that integrates to e power x. Integration of sine x is minus cos x. Integration of cos is sine. Integration of secant square is tan. These are functions that can be integrated directly. Okay. If x is replaced with any other linear expression in these, then the rule remains the same as before. There's one additional step, and that is that you also have to divide by the derivative of that expression. That will be m, so you divide by that. And again, expression. For using these rules, you can only you can only have a linear expression in place of x. If it's something else, then you cannot apply these rules. Okay. Now, these are some rules that are given in the formula sheet directly. You need to be able to use them. For instance, if you had minus 3 over 4, minus 3 over 5 into sine of 4x plus 1, minus 3 over 5 is a constant that remains as it is. Integration of sine is minus cos, so it becomes minus cos of 4x plus 1 divided by 4. Similarly, if you had e raised to power minus 2x plus 5, integration of e power something remains the same, but you have to divide by the derivative of this expression, that's minus 2, and that becomes your integration. So these are some functions that can be integrated directly. Then there are some more functions that can be integrated directly, and they come from the differentiation page on the formula sheet. We learned in differentiation that the derivative of secant x is secant x tan x. Derivative of cosecant x is minus cosecant x cot x, and derivative of cot x is minus cosecant square x. Now, these rules are not given in the formula sheet for integration. On the page for integration, you don't see these rules. However, you sometimes need to use them as well. So you'll make them yourself. Just reverse the rules that you had on the differentiation page of the formula sheet. So let me show that to you. We looked at them when we did differentiation just now. Differentiation of secant x was secant x tan x. This was minus cosecant x cot x. This was minus cosecant square x. Now, integration is just the opposite of differentiation. So for integration, we can have the opposite rules. These would be the rules for integration. So that's where these come from. You need to be able to use them as well. Integration of secant x tan x is secant x. Integration of cosecant x into cot x is minus cosecant x. And integration of cosecant square x is minus cot x. And again, x could be replaced with any other linear expression as well. So in general, you could say, if you have secant of mx plus c into tan of mx plus c, that integrates to secant of mx plus c divided by m. If you have cosecant square of mx plus c, for instance, that integrates to minus cot of mx plus c divided by m, and so on. So these are expressions, these are functions that you should be able to integrate directly. You should be able to integrate these directly. Okay. Integration of secant x, that's not part of our syllabus. Integration of secant x is not part of our syllabus. That will become 1 over cos x. We don't need to be able to integrate that. Okay. So these are functions that can be integrated directly. All right. And x can be replaced with any other linear expression in these. In that case, we would divide by m as well. M would be the derivative of that linear expression. These are used very rarely, but you need to know them. I've seen them tested at least once in recent papers, maybe twice. I'm forgetting about the second instant, but definitely once. So in very recent papers. So you need to use these rules. You need to remember these rules or be able to make these rules using the differentiation formula sheet. So if you have minus 3 over 5 into secant square of minus 4x plus 1, integration of secant square, what's that? That is tan. Integration of secant square is tan, so that minus 3 over 5 remains as it is. Tan of minus 4x plus 1 divided by minus 4, that's the result that you get from this. Minus 5 into cosecant of 2x into cot of 2x. What about this? This is given in the formula sheet directly. If you do not remember them, if you do not remember that there's a rule that exists for this directly, then you would think of integrating this by parts and you would get stuck. You would not be able to do it. Okay. This can be integrated directly. Even though it's a product, we know the integration for this directly from here. Cosecant x cot x, that integrates to this. Unless you remember this, you'll not be able to do this in the exam then. So you have to remember that a rule exists for this. At least that much you need to remember. Then you can have a look at the formula sheet and see. what exactly that rule is. So cosecant into cot, that integrates to minus cosecant. Okay. So you'll say minus cosecant of 2x divided by 2, minus 5 outside remains as it is. You simplify this and that gives you the integration. Now this is from an actual paper. 5 tan of 2x over cos of 2x. How would we integrate this? Now looking at this, it looks fairly complicated, right? It's a fraction. You think of all the fraction rules that you would apply on this. You think of bringing this to the numerator and then applying integration by parts, but it turns out tan of 2x over cos of x, if you bring cos 2x to the numerator, it actually becomes secant, right? Cos, when you bring that to the numerator, that will become secant, and you end up getting secant into tan, and for that, we know that a direct integral exists. We can integrate it to secant directly. So we bring cos to the numerator. When we bring cos to the numerator, that becomes secant, and we get this expression, integration of secant 2x into tan of 2x, that's secant 2x divided by 2. The 5 remains outside as it is, and you get that integration directly. Okay, so you don't have to use integration by parts or any other rule in this case. It's given in the formula sheet directly. You just have to, change this slightly, change cos to secant, and then integrate that. If we have this, if we have a non-linear expression in any of those functions, you cannot integrate it like this. For example, if you had this 3x squared plus 1 whole squared and you wanted to integrate this, you cannot use the power rule on this. Why? Because this expression is non-linear. In this case, you could still integrate it by expanding this first. So this is a square. You could use a plus b whole squared to expand this, and then integrate one term at a time. But if you had, for instance, something like this, if you wanted to integrate, for instance, sine of x squared plus 2, we can't do that. This is not the same. This is not going to be minus cos of x squared plus 2 over 2x. That would be wrong. Why? Because this rule does not apply, because this thing is non-linear. This expression has to be linear for this to work. Okay. All right. We cannot do this by substitution as well. We would need something else outside. If we had an x multiplying outside, then they would give you a substitution themselves that you could use to integrate it. But if it's just this, then this cannot be integrated using the rules that we know until now, know in A levels. Okay, so these are some standard rules that we saw earlier. Now we've got some rules that we will be using to integrating for integrating fractions. Okay, so we have a number of rules for integrating fractions. The first of them is what we will be calling the ln rule. Now, what's the ln rule? This is a simple example of that. 1 over x, that integrates to ln x. That comes up a lot, so you need to just remember this. It's given in the formula sheet as well. 1 over x, that integrates to ln x. But in general, whenever you have an expression like this, in the formula sheet, it says something like this: f dash of x divided by f of x, that integrates to ln of f of x. In simple terms, what that means is, if you have a numerator, that is the derivative of the denominator. If numerator is the derivative of the denominator, integration of that fraction is log of the denominator. It's ln of the denominator. That's the integration. If numerator is the derivative of the denominator, that integrates to log of denominator. That's the rule. We call this the ln rule. Whenever you have a format like this, where numerator is derivative of denominator, we integrate it using this rule. For example, if you had minus 4 over minus 4x plus 1, now what's the derivative of denominator? That's minus 4. We have minus 4 in the numerator. So we can say the integration of that is just ln of minus 4x plus 1 plus some constant. If you have this fraction, look at this. What's the derivative of the denominator? 10x plus 3. We have that in the numerator. So that integrates directly to ln of 5x squared plus 3x minus 2. And both of these examples, we already had that exact form that we wanted. Numerator was the derivative of denominator. So we can integrate them. We could integrate them directly. But sometimes you end up getting something like this, in which it is not exactly that form already, but you have to change something in that to make it that form. For example, if you have 10 over 5x minus 3, what's the derivative of the denominator? The derivative of denominator is 5. We want 5 in the numerator, but we have 10 instead. What we can do is we could say, let's take 2 common out of 10. So that gives you 2 into 5. Now, 2 is just a constant. We could write that outside the integral as well, because a constant that's multiplying, that does not change due to integration. So this constant can just be written outside the integral as well. So we write 2 outside, and then inside we just have 5 over 5x minus 3. That is exactly the form that we wanted. Numerator is the derivative of denominator. The integral becomes ln of 5x minus 3. Another way of thinking about this could be that that's a more general way that will work in most of such examples when integration using ln is possible. If you have 10 over 5x minus 3, you could say whatever is the number in the numerator, just write that outside. Just write that number outside. So you write 10 outside. If you write 10 outside, what are we left with inside? 1. Now, we want 5, so we multiply by 5, and to balance that, we divide by 5. Now, actually, we would be multiplying and dividing by 5 inside, right? So logically, we multiply here, and to balance that, we divide here as well. But since it's just a constant, it's our choice to write that inside or outside, and we choose to write that outside so that the inner part, that just becomes that ends up becoming that format that we want, in which numerator is the derivative of the denominator. So we have 5 over 5x plus minus 3 inside. Numerator is the derivative of the denominator, and that gives us the result. Now, that method becomes much more helpful when you have something like this, in which it's not easy to figure out what we would have to take common to make it that number. For example, if we had 7 over 5x minus 3, what we want in the numerator is 5. How can we have 5 in the numerator? You could say, let's write 7 outside. Inside, you would just be left with 1 in that case, right? When you write 7, when you take 7 common outside. Now, we want 5 instead of 1. So what we do is we say, let's put 5 here, and to balance that, let's divide by 5 outside. And now we've got 7 over 5 outside. This is the log form. It can be integrated to ln of 5x minus 3, and that's the result. Let's take this example. You have minus 4x squared plus 6x minus 7. What's the derivative of the denominator? The derivative of the denominator is minus 8x plus 6. So we want minus 8x plus 6 in the numerator. Can we have that somehow by multiplying or dividing by some constant? We have minus 4x plus 3 right now. Can we make it minus 8x plus 6 somehow? We could multiply by 2. We could multiply by 2, and that will make it minus 8x plus 6. But to balance that, then we divide by 2 outside. And now inside the integral, we have that form where numerator is the derivative of denominator. So the integration becomes ln of the denominator, and that's our result. Now, if we had 2 over x squared plus 9, what's the derivative of the denominator? The derivative of the denominator is 2x. So we want 2x in the numerator. We already have a 2 there. So we could think of multiplying by x and then dividing by x outside, but that does not work. We can only multiply and divide by constants, not by x. Because if you were multiplying and dividing by x, that multiplication division is actually happening inside. So x over x like this, for instance. Now we can't bring this x outside. That only is possible for constants. We can only write constants that are multiplying outside the integral. We can't pick up x from there and write that outside. That would not make sense, right? So this multiplication and division that we're doing, that is only possible with constants, not with x. You're not allowed to write x outside. Okay, multiply or divide by x. You can only multiply and divide by constants to convert it to that form. So this thing cannot be integrated using the ln rule. And as we will see later, this would actually be integrated using the tan inverse rule. Okay, we will see that. Now, you need to remember that 2 specific functions, tan x and cot x, they are integrated using the ln rule. You need to memorize this. Otherwise, you would not be able to figure this out in the exam yourself. You need to memorize that tan and cot, they are integrated they are integrated using the ln rule. Tan can be written as sine over cos, right? So if you have tan of x, you can write that as sine over cos. And now, what's the derivative of cos? Derivative of cos is sine, is minus sine. Right now, we've got sine over cos. We want minus sine in the numerator. So we can put a minus here, and to balance that, put a minus outside. And now the inner part that follows that rule, numerator is the derivative of denominator. So the integration becomes log of the denominator, and we have a minus sign outside. And that's the integration. You can leave it like this, and that's perfectly okay. Another way to write this could be that you could take this minus 1 to the power. So it becomes cos of x power minus 1, which is 1 over cos x. And then you could write that as secant x as well. So this is also another way of writing the integration of tan. Integration of tan is done using the ln rule like this. Similarly for cot as well. Cot is also integrated using the ln rule. What we do is we write cot as cos over sine. Now it could be some other expression in place of x here as well. It does not necessarily have to be x. It could be something else as well. For example, in this case, we got 3x. We could write cot of 3x as cos 3x over sine 3x, right? Now, when we do that, what's the derivative of sine 3x? Derivative of sine 3x is actually 3 cos 3x. We only had cos 3x in the numerator. To make that 3 cos 3x, what we do is we multiply by 3 inside, and to balance that, we divide by 3 outside. And now the inner part, this follows that condition where numerator is the derivative of denominator. So integration of this is going to be just log of sine of 3x, and we have this 1 over 3 outside as it is. That's what the integration becomes. This is something that you need to remember. Tan and cot, they are integrated using the ln rule. Okay, you need to memorize this. Okay, this is just an example here. You can have a look at this in your own time. 2 over x minus 2, for instance, both of these methods for integrating it are correct. One way is that you write 2 outside, and then that form becomes the ln form inside, and that becomes 2 ln of x minus 2. Another possibility could be that you could multiply the denominator by 2, which is kind of a weird way of doing this. But if you end up doing something like this, then you have 2 outside as it is, and this is now the log form, and that might turn out to be this. Both of these are acceptable, right? So sometimes you end up getting a slightly different form than the marking scheme, but that might be equivalent in some cases. In this case, the C's would be different for both of them, but both of these are acceptable integrals. Okay, even though they are not identical to each other, they are still equivalent because the difference is only of a constant. So the C's will be different and it will be the same expression. Okay, some people just get confused. Sometimes they end up getting a different answer slightly from the marking scheme. And a lot of times it is the case that it is equivalent to what they have in the marking scheme. So this is also acceptable. Okay, let's move on. Let's have a look at the next rule now. That's tan inverse rule. Now, what is tan inverse rule? This is how it's given in the formula sheet. 1 over x squared plus a squared. If you have an expression of this form, that is integrated to 1 over a into tan inverse of x over a. Right? That's the rule that we've got. For instance, if you have something like this, 1 over x squared plus 4, the rule is 1 over x squared plus a squared. That has to integrate to 1 over a into tan inverse of x over a. So we could write this like this, 1 over x squared plus 4. We could say it's x squared plus 2 squared. And then the value for a is 2. We just apply that rule. It becomes 1 over 2 into tan inverse of x over 2. Okay. And that gives you the results. That gives you the result. Okay. Similarly, you could have something like this, minus 5 over x squared plus 36. How do we use that rule here? The rule is if you have 1 over x squared plus a squared, that integrates to 1 over a into tan inverse of x over a. Now, in this case, we've got minus 5 in the numerator. If you want, you can write minus 5 outside, and that just leaves you with 1 inside. So that becomes that form. In the denominator, you have x squared plus 36. You could say that x squared plus 6 squared. And then that integrates using the tan inverse rule, minus 5 remains as it is, 1 over a into tan inverse of x over a. Simplify that, and that gives you the final integral. The value for a in this case is 6. Now, how would you know that something can be integrated using tan inverse? How do you figure that out? The standard form that you would have for that, remember for ln, numerator should be the derivative of denominator, or you should be able to make it that by multiplying or dividing by some constant. For tan inverse, how do you figure out that something can be integrated using tan inverse? This is the form that you would need for that. The numerator should have some constant. It should be a constant, only a constant. And the denominator should have an x squared term plus some constant term. Okay. Numerator should just be a constant. Denominator should be x squared term plus some constant. That's what the denominator should be. Okay. If it is this form, then we can use the tan inverse form. However, for using the tan inverse form, for applying this formula, we would first need to make the coefficient of x square 1. If it is not already 1, we would have to make it 1 first of all, and then apply that formula. Okay, so this coefficient will have to be made 1 first of all. It could be something else originally. Before we apply this rule, we should make that 1 and then apply this rule. Only then this rule would work like this. Now, let's have a look at some examples of that. If you had 4 over x squared plus 3, for instance. Now, in this case, we have a problem that this number is not a perfect square. Okay, 3 is not a perfect square, so it does not necessarily have to be a perfect square. We could write, first of all, 4 outside. If you write 4 outside, inside we're left with 1 over x squared plus 3. Now, how do we write this in square form? Because we want a squared there. Now, it's not perfect square. We could write it like this. We could say that's the same thing as saying under root 3 whole squared, right? So the value of a that you have here is under root 3. Now we can apply that rule. It becomes 1 over under root 3 into tan inverse of x over under root 3. You have 4 outside multiplying, and you can simplify that to get the result. If we have something like this, minus 5 over 3x squared plus 48, what about this now? We could take minus 5 common outside, write it outside so that we have 1 left inside. However, in the denominator, now we have a coefficient of x squared, that is 3. Now, we want this coefficient to be 1 to be able to use this rule. So what we do is we take 3 common from the denominator as well. When we do that, inside we're just left with x squared plus 16. And then we could write that as x squared plus 4 squared. And then on this part, we could apply that tan inverse rule, 1 over a into tan inverse of x over a, 1 over 4 into tan inverse of x over 4. Okay, and then you simplify that, you get the integral. This is as complicated as it could get sometimes, that you have something like this. If you take 7 common outside, that leaves you with 1 inside. In the denominator, you have 2x squared plus 5. You take 2 common outside, that leaves you with x squared plus 5 over 2 inside. Now, it's a fraction that you have. How do we deal with this now? We could write 5 over 2 as square root of 5 over 2 whole squared, and then apply that rule now. 1 over a, that's the value for a that we've got now. The integration becomes 1 over that into tan inverse of x over that, right? And then you simplify this, you can just put this on your calculator, put this thing on your calculator, and that will simplify to this, okay? And then inside tan inverse, this 2 will go to the numerator, and it becomes under root 2 over 5 times x, which is outside the square root, and that's your integration. Right? This is as complicated as it could get sometimes in case of tan inverse rule. So that's the second rule that we've got. ln rule, tan inverse rule. The next is integration using partial fractions. What can also happen is none of those rules might work, the ones that we discussed earlier. And instead, you could have some factors in the denominator. So for instance, let's say you have minus 20 divided by x plus 2 into 2x minus 6, right? That's the fraction that you've got. Minus 20 over x plus 2 into 2x minus 6. Now, how would you integrate this thing? How do you integrate this thing? In the denominator, you have two factors. You will find partial fractions of this. You'll break it into two parts. Using the partial fractions method, you just apply that whole method, break it like this, and then you integrate those two fractions separately. So you integrate these two separately. Now, in this case, they can both be integrated using the ln rule. In the first fraction, you could write 2 outside, so you have 1 over x plus 2 left. That's the standard ln form. In the second case, you want 2 in the numerator. One way to do that could be that you take -4, that you write -4 outside, and then you multiply by 2 inside, and to balance that, you divide by 2 outside. And now the inner part becomes the ln form. You can integrate that directly and you get the result from that. Okay. All right, so sometimes you could have an expression like this, 15 over 2x squared minus 14x plus 24. Now, this is not factorized. This form is not factorized. Now, since this form is not factorized, you can first think of whether the ln rule works. Does that work? The ln rule requires the numerator to be 4x minus 14. Now, we can't have an x in the numerator. We can't bring x ourselves. So ln rule will not work. It's not tan inverse form. In tan inverse form, we just want an x squared term plus some constant. Now, in this case, we have an x term as well. So that would not work. It's not tan inverse form. Can we factorize this? Sometimes you have to factorize the denominator yourself, first of all. So in this case, the denominator can be factorized. It can be factorized to x minus 3 into x minus 4. And you have 2 taking common outside here in this case. And then once you have this form, then you find partial fractions for that and then integrate both of them yourself, right? So sometimes you may have to factorize the denominator yourself as well. That is also possible. And then find partial fractions and integrate those fractions separately. Let's take this example. If you have 24 over x squared minus 9, this is, again, not a factorized form, but you could factorize this yourself. So it becomes x plus 3 into x minus 3. You could find partial fractions for that, integrate those two separately, and you get the result from that. In the previous example, it's not necessary that you take 2 common outside. It could be done without that as well. In this case, it just simplifies things. You could take that common outside, but if you don't, then you could have that in one of these factors, and that's perfectly okay. That would also work. Okay, now, if you had something like this, 24 over x squared minus 9, for instance, we saw that we could factorize the denominator using a squared minus b squared. That will be a plus b into a minus b. A squared b a plus b into a minus b, it could be factorized like this. And then we could use partial fractions in this. Tan inverse form cannot be used here because tan inverse form requires x squared plus some constant. This is minus. We want x squared plus some constant. Having a perfect square is not a condition. Even if this was not a perfect square, we could write that in square root form and then whole squared. The problem is this minus sign. Tan inverse requires a plus sign. You can't have a minus for that. When you have minus, you can factorize this and then break it in partial fractions and then integrate those two separately. However, this whole working is not required because the form that you have here, it is actually a standard form that is given in the formula sheet directly as well. If you look at the formula sheet, you would find that you have the tan inverse rule written here, 1 over x squared plus a squared. That is 1 over a into tan inverse of x over a. And along with that, you've got 2 other forms written. That's 1 over x squared minus a squared and 1 over a squared minus x squared. You have these integrals written directly in the formula sheet. If you have x squared minus a squared in the denominator with a constant in the numerator, that integrates to this. And similarly, a squared minus x squared, that integrates to this. So the form that we had here that I showed you earlier, although the logical way of doing this is using partial fractions, however, if we give you this question, that will only be like 2 marks. So this will be a lot of working for that. It will be 2 marks because they have given this rule directly in the formula sheet. You should be able to use that directly. It's the form that's similar to tan inverse. The only difference is there's a minus in the denominator instead of plus. In that case, you can use these rules directly. So we can say that these are two specific cases, special cases of partial fractions that we directly know the formulas for. So if you have 24 over x squared minus 9, you could say that can be written like this: 24 outside over into integration of 1 over x squared minus 3 squared. A is 3. A is 3, so it becomes 1 over 2 times 3 into ln of x minus 3 divided by x plus 3. That's what the integration becomes. That's what we got after so much working earlier using partial fractions. Since it's given in the formula sheet directly, we can just use that like this and get the result. Similarly, if you had 25 minus x squared in the denominator like this, for instance. Now this is this lost form that's given, constant minus x squared. We could use this rule like this here as well. We could write minus 4 outside, and then inside we have 1 over 5 squared minus x squared, and it becomes exactly this form, which can be integrated using this rule directly, and we get this result from that. Okay, so what are the rules that we've discussed for partial fractions and discussed for fractions until now? ln rule, tan inverse, partial fractions. For partial fractions, sometimes you'll have the factorized form given already, or you would have to make it that yourself. The question will not always tell you to use partial fractions. Sometimes they would, sometimes they won't. So you would have to do that thinking yourself if you can factorize that or not. Another possibility is, it's not a rule as such, but just a trick that you need to keep in mind that will help you integrate some fractions when one of those rules does not directly work. If you have 5x minus 9 over x squared plus 16, now ln rule does not work here because that requires 2x as the numerator. We've got this constant as well. We can't make it just 2x. We'll have a constant as well. So we can't, this is not ln form. This is not tan inverse because tan inverse requires only a constant in the numerator. We have an x term as well. So if we just had this, we could use the ln rule. If we just had this, we could use the tan inverse rule. So what we do in some cases like this is that we split the fraction, we split the numerator. So we write this fraction as 5x over x squared plus 16. We write that separately, and we write minus 9 over x squared plus 16 separately. We break it into two fractions because if you have something like this, a plus b over c, that can be written as a over c plus b over c. They are equivalent to each other. That's not the same as splitting the denominators. That's not possible. That would be incorrect. You can't split the denominator like that, but the numerators can be split like that. So we can just split the numerator this way. And then the first fraction that can be integrated using the ln rule. We want 2x in the numerator. We will write 5 outside, multiply by 2 inside. To balance that, divide by 2 outside. And here we could use the tan inverse rule, and that would give us the result. This is something that we can call integration by splitting the numerator. Splitting works when you have to think of it that after splitting, would you get something that you can integrate then? So you have to think of that first. So when you split this in this case, you can think of this in your head that yes, this is something that you can integrate using ln, and this is something that you can integrate using tan inverse, right? So you'll have to think of whether that's going to be of any benefit or not. So in this case, that is of benefit, and we could do it like this. All right. In this case, in these cases as well, if a is not a perfect square, for example, if it's 3, you could write that as square root of 3 whole square, just like we could do that for tan inverse form. We could do that in this form as well. We could write that in square root form, and that will work. Okay. Similarly, we could have an example like this: 7x minus 5 divided by 2x. If you want to integrate this, again, we could split it into two parts. We could say, let's write 7x over 2x separately, 5 over 2x separately. Now the first one, that just becomes a constant, which can be integrated to 7 over 2 times x. The second one can be integrated using the ln rule. Then if we write 5 into outside, we have 1 over x left, and that's 1 ln of x, and that's your final result. That's how you could integrate. Sometimes you can simplify your integral by splitting the numerator like this as well. The denominator in this case cannot be factorized. That's a very common error that ends up happening sometimes. This is a squared plus b squared. There's no factorization that you can do for that. A squared minus b squared can be factorized. A squared plus b squared can. You can't factorize this. Okay. Then another possible form is when you have improper fractions. Improper fractions. How do you integrate improper fractions? Improper fractions in this case would be when the numerator, the degree of the numerator is greater than or equal to the degree of the denominator, right? When numerator's degree is greater than or equal to the denominator's degrees. For example, in this case, this is an improper fraction. For improper fractions, the process for integrating is this, that we break them into two parts, quotient plus remainder over divisor. We apply the division process. Find the quotient, find the remainder, and then that fraction that we had, we break it into two parts, quotient plus remainder over divisor. And then after breaking it into two parts, we integrate those two parts separately. This could be integrated separately. This could be integrated separately. The first one using simple power rule, the second one using tan inverse, as you can see here, and that gives you the result. Okay, so these are all the different ways that you have for integrating fractions. ln rule, tan inverse rule, partial fractions, then two specific forms of partial fractions that are written directly in the formula sheet, 1 over x squared plus x squared minus a squared, 1 over a squared minus x squared. And then you could split the numerator or you could have an improper fraction, right? So you need to remember all of these rules. Okay, now next, we see what happens when we have products. When we have two things that are multiplying, that's a product. We can integrate that using something that we call integration by parts. Okay, it's the product rule of integration. When two things are multiplying, one way to integrate them is using integration by parts. If the question does not give you any other idea, for example, substitution, this is what you would be doing in most cases. Now, how does integration by parts work? If you want to integrate something like this, x into sine x, for instance, the formula that's written for that's given for integration by parts in the formula sheet looks like this: u into dv over dx, integration of that is uv minus integration of v into du over dx. We'll write that in a relatively simpler form. We'll say it's u into dv over dx, that's just v dash. So integration of u into v dash, dx just means it's with respect to x, right? So that's understood. We'll ignore that. That is given by u into v minus integration of u dash, right? That's how we will write that formula. That will simplify things for you. Integration of uv dash, that is uv minus integration of u dash, right? That's the formula that we'll be using. Now, for example, if you had x into sine x, you can say x is u, sine x is v dash. Now, in the formula, you want uv minus integration of u dash. So you want the value of u, you want the value of v, you want the value of u dash and v dash. Now you have u equal to x, you've got v dash equal to sine x. From u, you can find u dash by differentiating. The derivative of x is 1, so u dash equals 1. V dash is sine of x, integration of sine x is minus cos x, so v turns out to be minus cos x. Now, once we've got these four values, u dash, v dash, we can just input them in this formula and then simplify that. That gives us the result, u into v minus integration of v into u dash. Simplify this and that gives you the result. You can see what that turns out to be. That's how this integration by parts formula works. This is another example. You can have a look at that. U is x here, v dash is e power 3x. All you have to do is find the derivative of u to give you u dash, find the integration of v dash to give you v, input values in this formula and simplify that. That will give you the result. Now, the choice of u and v dash is important here. You can't just randomly take one of them as u and the other v dash, because sometimes otherwise you would not be able to find the integral. For example, in this case, if you take sine x as u and x as v dash, then you end up getting stuck, because when you apply the integration by parts formula once, in the second step, you end up getting a product again. Getting a product again is not an issue, but this product that you're getting is actually more complicated than what you started from. You started from sine x into x. That's what you started from. In the next step, you're getting x squared into cos x. So the power of x is actually increasing. The integral is becoming more complicated. So that means you're not going in the right direction. There's something wrong. So in such cases, it's important to know which one you should be taking as u, which one you should be taking as v dash. In fact, we've done this example before, x into sine x. I wrote that as x sine x earlier. In that case, we took u as x, and that worked. Taking u as sine x does not work. So how do we decide what to take as u and what to take as v dash? The logic behind this is that, first of all, v dash should be something that you are able to integrate directly, because v dash has to become v. If you don't know how to integrate something, then taking that as v dash would not work. For example, if you had ln x somewhere, you don't know what the integration of ln x is. If you take that as v dash, then what would v be? You would not be able to find that. So v dash should be something that you can integrate directly. For example, it could be some algebraic expression, x raised to power something. It could be sine cos. It could be exponential. You know how to integrate them. If both the expressions can be integrated, then what we do is we take u as the one that becomes simpler after differentiation. For example, if you have x cubed, after differentiation, or let's actually take x squared, for instance, after differentiation, it becomes 2x. It's becoming simpler after differentiation. So u should be something that becomes simpler. Sine, for instance, that does not become simple. Sine becomes cos. After differentiation, that's not becoming simple. Ln x does become simple. It becomes 1 over x, right? So u should be something that becomes simpler after differentiation. Now, that's the logic, but eventually, the result that we get from that is, this is a rule that we would remember to decide what to take as u and what to take as v dash. We can remember this as I late. We use this for integration by parts for deciding between u and v dash. Remember these initials, ILATE, I late. I stands for inverse trigonometric function. In your syllabus, there's only one, that's tan inverse. L stands for log, and again, in your syllabus, it's only ln, for which you have to do the integration or differentiation. A means algebraic. Algebraic means powers of x, x raised to power something. It includes constant as well, right? So constant could be thought of as x power 0. So we would include constant in algebraic expression as well. T stands for trigonometric, sine, cos. E stands for exponential, e raised to power something. Now, in I late, whatever is on the, so you'll have two expressions, right? Out of those two expressions that you have, whichever is to the left side, you would take that as u. Whichever is on the right side, you will take that as v dash. For example, if you had something like this, that one expression was trigonometric and another was algebraic. Now, algebraic and trigonometric, out of these two, algebraic is on the left side, you take that as u. Trigonometric is on the right, you take that as v dash. If you had algebraic and, for instance, log, what would happen in that case? Amongst these two, algebraic is on the right, we take that as v dash. Log is on the left, we take that as u. So in I late, whatever is on the left side, you take that as u. In I late, whatever is on the right side, take that as v dash. For example, if you have cos of 3x into x, we want to integrate this. We've got two types of functions. One is trigonometric, the other is algebraic. Trigonometric is on the right, we take that as v dash. Algebraic, we take that as u equals x, v dash equals this, and then we just input values in the formula, and that gives us the result. Okay, so that's how we decide between u and v dash, which variable to take as u and which one to take as v dash. Sometimes you may have to do integration by parts multiple times as well. So for instance, if you have x squared into e raised to power 4x and you want to integrate this, how would you do that? If you were to do integration of this, first of all, you have to decide between u and v dash. What do you take as u and what do you take as v dash? X squared is algebraic. X squared is algebraic. And e raised to power 4x is exponential. Amongst these two, a is on the left side, that is u. E is on the right, that is v dash. Okay. So we take u equal to x squared, v dash equals e power 4x. Apply integration by parts. But in this case, what happens is we end up getting a product inside the integral again. When we apply this process, this is what we end up getting, e power 4x divided by 4 into 2x. Now, I would generally recommend that you write down any constants that are multiplying outside. That will simplify things for you. So for example, in this case, you have 2 in the denominator. You can write that outside like this, 1 over 2. And inside, you're just left with this. Now, e power 4x into x. Now, we again are getting a product. How do we integrate this product? We would have to apply integration by parts again in this case. Now, this can happen sometimes as well, that you have to apply integration by parts multiple times. But make sure that you're going in the right direction by checking that the integration is becoming simpler than before. So you started from x squared into e power 4x. Now you've got x into e power 4x. So the power of x is decreasing. So it is becoming simpler. That means you are going in the right direction. You apply the integration by parts process once more, and then you would be able to get something simpler like this, which can be integrated directly, simplify everything, and you get the result from that. So sometimes you may have to apply integration by parts twice as well. Not more than twice, at least until now, they've not asked you to do this more than twice. But twice is very common. You may have to do this. Okay. This is another example, x cubed into ln of 2x. You can integrate it using integration by parts. It's also a product. In this case, one is algebraic, the other is logarithmic. You'll take the logarithmic as u, right? Because that's on the left side there, and algebraic as v dash. Find u dash and v, input them in the formula, and you get the result from that. You can have a look at this working. Now, for ln rule, we remembered that whenever we have tan of something or cot of something, we would always be using the ln rule for that. Here as well, you need to remember two functions that will be integrated using integration by parts. Sometimes they will give you a hint in the question. They will tell you to use integration by parts. Sometimes they won't. You need to remember that they're integrated like this. The first one is ln of x. So integrating ln x, the process works like this. We write it as 1 into ln x. We don't know the integration of ln x directly, right? It's not given in the formula sheet. Ln x, derivative of ln x is 1 over x, but integration of ln x, we don't know. So integration of this function works like this. We write it as a product, 1 into ln x. Now it becomes a product. And then we apply integration by parts in this. Remember, we said constants will be treated as algebraic. So we treat this as algebraic. 1 is algebraic. Ln x is logarithmic. So u equals ln x and v dash equals 1 according to IL8. So in IL8, on the left side, you'll have u. On the right side, you would have v dash, right? So log is on the left side. Algebraic is on the right amongst these two. So you would take log as u. Apply integration by parts, you get the result. Similarly, the other function is tan inverse. Tan inverse is also integrated using integration by parts. You need to remember that as well. Tan inverse is integrated using integration by parts. Okay, you write this as 1 into that as well. So tan inverse of 4x, we could say that's 1 into tan inverse of 4x. And then we apply integration by parts. U equals tan inverse of 4x, v dash equals 1. Find u dash and v, input them in the formula. When you do that, the integration that you get in the next step, that's going to be a fraction. And this fraction in this case can be integrated using the ln rule, right? We've got x over 1 plus 16x squared. The derivative of the denominator is 32x. So we wanted 32 in the numerator. We could multiply 32 in here and divide by 32 outside to balance that. And then it becomes the ln rule. We integrate it like that, and that gives us the result. So you need to remember ln of something and tan inverse of something. They are integrated using integration by parts. We write them as 1 into that function and then integrate them. Okay. This is another method that's used very rarely, but it's good to know. If we have to integrate, for instance, in sine x into cos x. Now, there are multiple other ways of integrating this as well, but this is one way of doing this, integration of sine x cos x. But this method works for some other kinds of problems which are a bit more complicated. But let's understand it using this example. Sine x into cos x, if you were to use integration by parts on this, since it's a product, you could say u is equal to sine x, v dash equals cos x. Both are trigonometric. It doesn't matter which one you take as u, which one you take as v dash, because both are trigonometric, right? Both are t's in isolate, so it doesn't matter. You can take any of them as u, any of them as v dash. If I take this, then what happens is in the next step I get sine x into sine x minus integration of this thing, and this is actually the same thing that we started from. So it's not becoming any simpler. It's a loop that is started, and this will just continue like this forever. If I keep doing this, I'll keep getting integration of sine x into cos x. So that's a loop that's appearing here. What we can do in this case is we could say this integration, let's call this something, let's denote it by some letter. Let's call this I, for instance, or any letter for that matter. It doesn't really matter. You could say this is I. That's what we want to evaluate. So I equals this thing. Now we are getting that same thing here. So this is also I. So we could replace this with I here now. So we have I equal to sine square x minus I. What were we trying to find out? We were trying to evaluate I here. So what we do now is we make I the subject. So it becomes 2I into sine square x, and then I equals half sine square x. And that means integration of sine x into cos x, that is half sine square x. Okay, we can call this the loop method. And that is used when you apply integration by parts and you get a cyclic expression that, you get the same thing back again that you started from. It's not getting any simpler. It's just giving the same thing again. In this case, you can make a loop like this. When you have this same thing again that you had initially, you can replace that with that expression, for instance, just that letter, call it I, for instance, and then just make I the subject, and that gives the result. Okay, this is going on here. We have a 1 minute break. I'll show you a more complicated example of this. You can have a look at this, try to understand what's going on, and then I'll explain that. Just 1 minute. I'm back. I'll be back in a minute. Okay, so this is another example of that loop method. So you've got an exponential function, and you've got sine of 4x. You've got these two functions. Now, both of these functions do not get any simpler, right? E raised to power x into sine of 4x, they both don't get any simpler. When you apply integration by parts once, you get this e raised to power x into 4 into cos of 4x, and then this is not getting any simpler, right? It's the same difficulty level as same complication level as before. One exponential function, one trigonometric function, but it's not the same thing as well. It's something different, right? So it's not becoming a loop yet. However, when you apply integration by parts once more on this, what happens is, in the next step, you do end up getting something like this: e raised to power x into sine of 4x, right? So if you look at this working again a bit slowly later, I've just taken the constant outside. And then inside you're left with e raised to power x into sine of 4x. And that's exactly the same thing that we started from. So we have a loop now. We could say that original thing is I, right? Then this could also be replaced with I. So we've got I here, we could make I the subject now, and that would give us the integration. Okay, so that's a method that you can sometimes use in integrals like this that do not become any simpler, but when you integrate them, you end up getting the same thing from that again. It's very rare. You would just find 1 or 2% at max in this in past papers, and all that those two in some older papers. But it's good to know. There's always a chance that they end up giving something like this. So you should be aware of this. Okay. All right. Then you have this rule that we call the extended power rule. Now, this is not part of your syllabus explicitly, but it simplifies some integrals. Okay, you can do everything without it as well. There are other methods that you've done, they will work, and you would be able to integrate such functions using those methods. However, this rule will simplify some integrations. I'm calling this the extended power rule. It's the power rule, but it's the extension of that rule. So earlier we said the power rule, we would only be applying that on these expressions. A plus b whole raised to power x whole raised to power n. Integration of that, that's ax plus b whole raised to power n plus 1 divided by n plus 1, right? However, we could generalize that rule like this. We can actually do this for other functions as well, but only this one is what you would need to use sometimes, or would help you in some cases, in case of power rule. And it looks like this. If you have an expression and you have a power on top of that, and the derivative of this expression that is inside is multiplying outside. The derivative of the expression inside is multiplying outside. Then the integration of this whole thing is just going to be that expression power n plus 1 divided by n plus 1. We'll just add 1 to the power, divide by the new power. We could think of this in terms of the box notation, in case that f of x notation is confusing. So in place of this box, you could have anything, okay? Any expression in terms of x. If we have a power on top of that, and the derivative of this thing is multiplying outside, then the integration of this whole expression can be directly written as that expression power n plus 1 divided by n plus 1. Let me give an example of that. For instance, sine x into cos x. We could think of it as sine of x power 1 and then cos x outside. So we could say we have sine x. The derivative of that is multiplying outside. So using that rule, we could just say it's going to be sine square x divided by 2. Add 1 to the power, divide by the new power. And that gives you the result directly. Okay. Take another example. In this case, you could try something like this as well. If you had, for instance, sine cube x into cos x with respect to x, you could say that is sine of x whole cube into cos x. If you want to integrate this, the derivative of this thing is multiplying outside. The integration is going to be sine raised to power 4x divided by 4, and that's your integration. Now, in such cases, they often will give you a substitution. They will often give you a substitution in this case. But if they don't give you that substitution, this is often a very efficient way of doing this, that we think of it like this. If the derivative of the inner part is multiplying outside, you add 1 to the power and divide by that new power. Let me give you another example. Let's say you have 5x cubed plus 7 whole raised to power 4 into 15x squared. Now you see, the derivative of the part that is inside, that is multiplying outside, you could integrate it directly like this. You could say add 1 to the power, divide by the new power, and that gives you the result. Take another example. If you have sine of 2x whole squared into cos of 2x, you could think of it like this. You've got something inside the power. What's the derivative of this? Derivative of this is 2 cos 2x. Now we have just cos 2x outside. Can we make it 2 cos 2x somehow? We could say, let's multiply by 2. But to balance that, we'll have to divide by 2 outside. And now this follows that form. So integration of this is just going to be sine 2x power 2 plus 1 divided by 2 plus 1. And that's the integration, right? You can do everything without this as well. It's possible. There will be other methods to be able to do them. But if you know this, in some cases, it becomes very efficient. If you had cos cube theta, we will see later how to do it using substitution. But you could do it using this extended power rule as well. Cos cube theta, we could break that into two parts as cos square theta into cos theta, right? And then we could say it's 1 minus sine square theta into cos theta. And then you break it into two parts, cos theta minus sine theta whole squared into cos theta. Now, cos theta can be integrated directly to sine theta. And what about this? We can apply the extended power rule on this. And that is, you've got sine theta, the derivative of that is multiplying outside. Just add 1 to the power, divide by the new power, you get sine cube theta over 3. And that's the integration. We could do the same for tan cube as well. We could break that into two parts. We often do this using substitution, but this is an alternative. Tan square x into tan x. Then replace tan square with secant square x minus 1 using this identity. And then you break it into two parts. You've got secant square into tan x. Now, think of it like this. Is derivative of secant tan? No. The other way around is true. The derivative of tan is secant square. So we could write tan x inside the brackets and say it has power 1. And it has the derivative multiplying outside. That's secant square. We just add 1 to the power, divide by the new power. That's the integration of this. Integration of tan, that we know how to do using the ln rule. We write that as sine over cos, and then integrate it using ln. And that's how we could integrate tan cube x. Make sense? So that's called extended power rule. Then finally, we've got integration by substitution. Not finally, but this is another method that we've got. We have some more to go. Integration by substitution. Now, whenever you have substitution, except for a couple of cases that we'll talk about, they will always tell you what substitution to use. They will always tell you what substitution to use. Okay. For example, let's look at the same integral again. If we had to integrate this, they might give you a substitution, u equals sine x. Now, this will be given. They will tell you use this substitution in this case, if they ask you to do it by substitution. U equals sine x, let's say they've given you this substitution. Now, how do you use that here? If you replace sine x with u here, you get u into cos x into dx. Now, you also need to get rid of the other x from here. How would you do that? Whatever substitution you're given, you always will first of all differentiate that. So u equals sine x, you find the derivative of that. That gives you du over dx, which is cos x. And then you would make dx the subject so that you can replace this dx with du as well. Because when you convert things to something that's in terms of u, then you want to integrate them in terms of u as well with respect to u. This is with respect to x. We want to integrate with respect to u. So we want to change this to du as well. How would that happen? Whatever substitution you're given, you would always, first of all, differentiate that. Find the derivative of that, make dx the subject, and then in that integral, you input u equals sine x equal to u, and in place of dx, you put du over cos x. Now, in this case, what's happening is cos x and cos x, they get cancelled, and that just simplifies to this. What's the integration of u? That's u square over 2. Now, you could replace that back and write it as sine square x over 2 plus c. That's the result. If you had limits given, we'll talk about what to do in that case. But if you just try to find the integration, you would find this integration like this and then put that substitution back, and that gives you the result. Whenever you have a substitution, the first thing you do is you find the derivative of that so that you can replace this with the other variable as well. So in this example, for instance, this is the substitution, u equals x square minus 2. What you do is you find the derivative of this, du over dx, that's 2x. Make dx the subject, that becomes du over 2x. Put that here. It becomes du over 2x. And put that substitution here as well. That's x square minus 2. Replace that with u. So you have e raised to power u and this thing written here. And now you still have an x left there. This x gets cancelled with this x that you had from there. And we have everything converted to u. And now we can integrate this 4e raised to power u. What's the integration of that? This is 4e raised to power u. We'll put that substitution back and you get the result for that. In these examples, you saw that x was getting cancelled itself. Sometimes that's not what happens. For example, in this case, you were given the substitution, u equals 2x plus 1. Let's say you were given the substitution. And when you apply that substitution here, first of all, what you have to do is you have to find the derivative of this. Du over dx, what's that? That's 2. Then make dx the subject, that gives you du over 2. And now you put that substitution there, replace 2x plus 1 with u, and replace dx with this. When you do those two substitutions, you get u inside the square root and you have du over 2. But the problem is this x is still there and it's not getting cancelled. How do we get rid of this x now? We had u equals 2x plus 1. We could make x the subject from here. And that gives us that x is equal to u minus 1 over 2. So now we can replace that x here. We can replace that here. Replace x with u minus 1 over 2. And now we've got everything in terms of u, and now we should be able to integrate it. We can only integrate once we have everything converted to the other variable. So now we've got everything converted to u. We've got this product. We don't have to use integration by parts here because it can actually be simplified. You can just multiply this inside and it simplifies to u power 3 over 2 minus u power 1 over 2. Apply power rule on both of them individually, integrate them, put that substitution back, and you get that result. Now, in this case, we also had the limits. The lower limit was 2 and the upper limit was 5. Now, the limits are values of x in this case. The original integral is in terms of x. So we had to integrate this in terms of x. Now, when we convert it to u, the limits would also change because these values are values of x. We can't input those same limits there. So you would also change the limits. How would you do that? You would clearly write down what the lower limit is and what the upper limit is. This is very important that you clearly write down the lower and the upper limit separately. What's the lower limit? Lower limit is x equals 2. Upper limit is x equals 5. Use that substitution now. U equals 2x plus 1 to find the corresponding u values. And u turns out to be 5 for the lower limit, 11 for the upper limit. Input those values in that integral now. 5 to 11, these are the limits that we've got. After converting to u, integrate that, input those limits, and you would get the result. And that's the final result that we wanted there. Okay, so that's how substitution works. Whatever substitution is given, you find the derivative of that. Put those two things in that expression. If there's any x that is left still, you replace that as well by rearranging this and inputting that in that integral, and you also change the limits. When you change the limits, it's very important that you clearly write down what the lower limit is and what the upper limit is. I will talk about that in a moment, because sometimes what happens is when you change the limits, the lower limit might end up being a bigger value and the upper limit might end up being a smaller value. So that is something that can happen sometimes. If you don't write it clearly, you would mistakenly write the upper limit as the bigger value and the lower limit as the smaller value. But sometimes it might be reversed. We'll have a look at an example for that. So let's say you've got something like this. T equals integration of 10 over 5 minus square root of h. You want to integrate this, limits are from 0 to 4. Now, we have to use the substitution u equals 5 minus square root of h to find the value for t. Now, how do we do that? This is the integral that we're given. We apply that substitution. We find the derivative of that, replace dh with this thing, and replace this denominator with u. Once we do that, we've got this expression. We still have an h there. To get rid of that, we make h power 1 over to the subject here. That gives us 5 minus u. And we also replace this h power 1 over 2 with 5 minus u now. And we end up getting an integral like this. What about the limits now? What are the limits? The lower limit is 0 and the upper limit is 4, right? These are the limits. These are the values of h. What are the corresponding values of u going to be? U turns out to be 5 here and u turns out to be 3 here. And you see the lower limit is 5 and the upper limit is 3. Lower limit is a bigger value. Upper limit is a smaller value. Now when you write that there, you have to be careful. The upper limit is 3. Do not write 5 there for now. And the lower limit is 5. That's not 3. That's what it is. If you just want to find the value of t, then you could just do it like this, and that's perfectly okay. Input, integrate it. After integrating, you input 3 in that. Subtract from that the case when you input 5, and you would get the correct result from that, and that's perfectly okay. That will work for you. Okay. Sometimes in the question, they will ask you to show something. So they might give you this integral and want you to first of all show that t can be written in this form. They might ask you to show that using this substitution, t can be written like this. Now, when they will ask you to show something, they will write the bigger number on top and the smaller number at the bottom, because that's the conventional way of writing limits, that we write the bigger number up above and the lower limit, the smaller number below. Now, how is that possible? How do you change the limits? We were getting 3 here and 5 as the lower limit. They ask us to show this. If that happens, you can change the limits by multiplying the function by -1. So we had -20 here. If we remove minus from there, if we multiply the whole expression by minus, we could switch the limits, and that would give us this expression that they wanted. So in general, you can remember, if you have any limits for an integral, let's say they're a and b, if you want to switch those limits, you want to make them ba, you multiply the function by minus, and then you can switch the limits, right? And if you have, for instance, integration of p minus q with limits a to b, you can switch the limits by writing them as q minus b. Okay, multiply by minus and switch the limits, and that gives you the result. Okay, so you can switch the limits like this. It's not always necessary to do that. Only when they ask you to show something like this, you can do that by multiplying by minus and then converting to that form. The next thing is you need to be able to integrate powers of sine, cos, and tan. Powers of sine, cos, and tan. First of all, we've got odd powers. In odd power, it's only cube that you need to be able to integrate: sine cube, cos cube, and tan cube. How do you integrate sine cube? Integration of sine cube can be done using substitution. So we looked at one method for this, and that was using extended power rule. More often, they will ask you to do this by a substitution. You should remember these substitutions. These are the substitutions that you should memorize, because this is explicitly part of the syllabus, that you need to be able to integrate powers of sine, cos, and tan. So sine cube, cos cube, and tan cube, you should remember their integration. Sine cube is integrated using the substitution u equals cos x. Cos cube is integrated using substitution u equals sine x. And tan cube is integrated using substitution u equals tan x. You need to remember these substitutions. For sine, we use substitution cos. For cos, we use substitution sine, and for tan, we use tan. Okay. Now, how exactly does it work? If we have integration of sine cube, and we want to use the substitution u equals cos x, first of all, we find the derivative of that. The derivative turns out to be this minus du over sine x. Now, when you do this, you would actually, since you want to put u equal to cos x here, there's no cos there. How do you get cos? You could break sine cube into two parts. You could say that's sine squared x into sine x. You could break it into two parts. And when you do that, you can write sine squared as 1 minus cos square. And now this cos square can be replaced with u squared. And then you replace dx with this expression as well. Simplify that, and you get a simple integral from that, which is just 1 minus minus into 1 minus u squared, which becomes u square minus 1. What's the integration of u square minus 1? U cube over 3 minus u. And then you can put that substitution back. If there are limits, you can change the limits and input those limits here as well. But that's how it would work. For sine cube, use the substitution u equals cos x. Similarly, for cos cube, use integration sine. In this case, we have cos cube of 2x. So the substitution would be u equals sine 2x. Okay. Then you use the standard process. You find the derivative of that. This is again a cube. You want to use the substitution for sine. How do you convert cos to sine? You break it into two parts, cos square into cos square into cos power 1. You break it into two parts like that. And then you apply that substitution. It becomes 1 minus u squared with du outside and 1 over 2 dividing outside like this. That's coming from here, this 2. Integrate it, input those substitutions back, and you get the result from that. Okay. So for cos cube, we use substitution sine. Similarly, for tan we use this. For tan cube, we use the substitution u equals tan x. Now, how would that work? We have to find the derivative of that. Derivative of tan is secant square, and then we make dx the subject, which gives us du over secant square x. Put these two things there, u cube, and then dx can be replaced with du over secant square x. All right. Now, how do you integrate this further? There's still an x there. How do we get rid of this x? We can use the identity for this. 1 plus tan square is secant square. So it can be written as 1 plus tan square. U is tan x, so it becomes 1 plus u squared. Now it's an improper fraction. Integrate it like an improper fraction, quotient plus remainder over divisor, and then put that substitution back, and you get the result from that. Again, this is one way of doing this. The other way is using that extended power rule. This is how you could do this integration of odd powers. For sine cube, cos cube, and tan cube, you either have to memorize these substitutions because sometimes they would not tell you these substitutions. Okay, you either have to memorize these substitutions. For sine cube, you use cos. For cos cube, we use sine. For tan cube, we use tan. You either use these or you remember that extended power rule that we discussed. One of these two methods, you either have to memorize these substitutions or use that extended power rule, right? So they can be integrated both ways. It's your choice now, whichever of them you want to use, but you have to be able to integrate them without any help from the examiner. So they might not tell you the substitution and you still might have to do it. You can do that substitution yourself or use extended power rule. That's your choice. Okay, make sense? All right, then we have even powers of sine, cos, and tan. Even powers include square and power 4, power 2 and power 4. Now for sine and cos, the even powers are integrated using the double angle identity for cos. So sine square, how is that integrated? Using the double angle identity for cos 2a is identical to 1 minus 2 sine square a. We will be using that identity for this. Make sine square the subject, and that gives you sine square a identical to 1 minus cos 2a over 2. So that means sine square x therefore can be written as 1 minus cos 2x over 2, and then it can be integrated directly. We could write that 2 outside from the denominator, and we just have this left, 1 minus cos 2x, that we know how to integrate. Integration of 1 is just x, integration of cos 2x is sine 2x over 2, and that gives us the result from that. Okay, so for sine square, we use this double angle identity. These are even powers are integrated using identities like this. We cannot use the power rule on either this or the previous examples for odd powers, because for power rule, remember we had the condition. For the previous case, we could use the extended power rule as we discussed. But in this case, we can't even use that because we can't write it in that form such that we have the derivative of one multiplying outside. We have to use identities for this. We can't use the simple power rule on this like this, that sine cube x is sine cube x divided by 3 and divided by the derivative of sine x, which is cos x. That would be wrong, because remember that rule only used to work for linear expressions. Sine of x whole squared, this expression inside is not linear. Linear is just mx plus c, right? The straight line, that's linear. Sine is a curve like this. That's not linear. You cannot use the simple power rule in this. That would not work. So you have to somehow get rid of this power. So this double angle identity helps us get rid of that power, so that we just have cos of 2x, and then we can integrate that directly like this. So even powers are integrated using they're integrated using the trigonometric identities. Yes, if we had cos of 4x, integration of cos 4x will be sine 4x divided by 4. That's correct. Okay, now let's move on. What about cos square x? For cos square x as well, we use the double angle identity for cos. But the other form now, cos 2a is identical to 2 cos square a minus 1. This is another form for that identity. Make cos square a the subject here, and that gives you this 1 plus cos 2a divided by 2. Put that here, and then you can integrate this separately, and that gives you the result. If you had sine square of 2x, what about this now? Sine square of 2x, how would you integrate this? Again, using the double angle identity for cos 2a is 1 minus 2 sine square a. We can make sine square a the subject here. When we do that, when we make sine square the subject, that leaves us with 1 minus cos 2a divided by 2, right? Now, we don't just have x here, we have 2x. Now we have to think about this identity. When we have sine square a here, on the right side, it's becoming 2a. So whatever is the angle on the left side in this identity, in this form, on the right side, it's double that. When we have 2x here, on the right side, we'll have 2 times that. That becomes 4x. So sine square 2x can be written as 1 minus cos 4x divided by 2. And then we just integrate it like before. Integrate 1 separately, cos 4x separately, and then simplify that further. Similarly, you could have cos square of half x, for instance. What about this now? Again, we could do it the same way. The double angle identity for cos. For square even powers, we'll be using the double angle identity for cos. That's the standard. Cos 2a, that is 2 cos square a minus 1. Again, we can make cos square a the subject. Cos square a equals this. And now we think about this. Whatever is the angle here, that's a. On the right side, it becomes 2 times that. If we have half x here, on the right side, 2 times half x, what would that become? That will become x. So this could be replaced with 1 plus cos x over 2. We could write 2 outside and integrate this 1 plus cos x. That can be done directly, and that gives us the integration, right? So that's how we integrate even powers of sine and cos. What about tan square? That's straightforward. Tan square can be written as secant square x minus 1 using this identity. Using this identity, you could write that as secant square x minus 1, and then integration of secant square is tan, integration of 1 is x, and that gives you the result, right? So tan square is pretty straightforward. What about power 4? Now, when you have power 4, generally they will make you do it in multiple parts. In the first part, they will ask you to prove some kind of an identity. And then in the next part, they would want you to integrate this. So you would be able to use the identity from the first part to integrate this in the next part then. But if you had to do it directly, how would you think about it? You'll have to apply the double angle identity twice. So think about this. Sine raised to power 4x. This is what you have initially. Now, how do we get rid of this power, right? That's the idea. We want to get rid of the power so that we can integrate it like before. Now, this is power 4. We could write sine raised to power 4 as sine square x and sine square x whole squared. And then sine square x, it could be replaced with this. just like before, the double angle identity for cos, sine square A turns out to be this from that. So sine square x therefore can be replaced with this 1 minus cos 2x divided by 2 whole squared. And now we've got a minus b whole squared inside the bracket in the numerator. We can expand that, a square minus 2ab plus b squared. Now we could write 4 outside this 4. That will simplify things for us. In the numerator, we've got 1. 1 can be integrated directly. That's not a problem. Cos 2x, this can also be integrated directly. The only problem is cos square of 2x. This is still a square. How do we get rid of the square now? Again, we use the double angle identity for cos. Cos 2a is identical to 2 cos square a minus 1. In this case, we've got cos square. So we use the cos square form. That's 2 cos square a minus 1. Make cos square the subject. Cos square a equals this. And now we have cos square of 2x there. Replace a with 2x. If you have 2x here, the angle on the right side should be 2 times that. So if it's 2x, that should be 4x. We have seen that before. So this becomes 1 plus cos 4x divided by 2. And now the powers are all eliminated. We can integrate them now. 1 integrates to x. Cos 2x integrates to sine 2x over 2. Cos 4x integrates to sine 4x over 4. 1 integrates to x. And then we just simplify all of that and we get the result. If you had to integrate cos raised to power 4, the process for that will be exactly the same, with just a difference of some plus minus, but the overall process will be pretty much the same as this. Okay. This is all that we have in integration as far as the concepts are concerned. These are all the concepts of integration. If you remember these rules well, all of these rules, then you would find that the integration questions are not going to be as complicated. The reason why a lot of students find integration difficult is because they don't remember these rules. If you don't even know the rules, then you can't, solve problems, even if they're relatively easier. And you would find once you know all of these different methods, you would not get something that's very different 95% of the times. Yes, there will be some rare questions in which you'll have to think a bit more, but generally you will be able to figure them out fairly easily if you've done enough practice. So overall, just a quick review of that. If you have any simple function without any product or fraction, use direct formulas that we discussed in the very beginning. If you have a product, you can either use substitution, that will always be given, unless you have sine cube, tan cube, cos cube. For them, you can memorize those 3 substitutions. Apart from that, if it's any other substitution, that will always be given in the question. The other possibility is integration by parts. If they've not given a substitution, you might be able to do integration by parts, or that extended power rule that we discussed. When you have the derivative of what is inside multiplying outside like this, you could use this extended power rule for products. These are the options that we've got for products. For fractions, we've got a number of rules. You might be given a substitution. In that case, you just use that substitution. You have the ln rule then, tan inverse rule, partial fractions. After partial fractions, you could integrate using ln or tan inverse then. Then you have these 2 specific forms of partial fractions that are given in the formula sheet directly. You could split the numerator. You could use the improper fraction method, break it down into quotient plus remainder over divisor if it's an improper fraction. And then if none of them work, you could take the denominator to the numerator. For example, if you have 4 over 2x plus 5 whole raised to 2x plus 1 whole raised to power 5, in this case, you can just take the denominator to the numerator. It becomes a power function. You can apply the power rule in this. In this case, you could take x to the numerator and then apply integration by parts on this. So if none of those fraction rules work, you can take the denominator to the numerator like this. Even powers of trig functions, they are integrated using trigonometric identities. Odd powers, they are integrated using substitution or the extended power rule. This is something that's very common in some recent papers. 4 over cos square. How do you integrate this? 4 over cos square. So 4 is not important, but the fact that you have cos square in the denominator. Now this is in the denominator. You don't use trigonometric identities for this, as in for cos square, you don't use the double angle identity. you only do that when that's in the numerator, right? This is in the denominator. Now this is cos square. Now a lot of times you end up forgetting about this, or it doesn't click at that time at that point. But since it's coming quite often, just remember when you have cos square in the denominator, think of whether you can take it to the numerator like this. When you bring it to the numerator, it becomes secant square. And integration of secant square, we know directly integration of secant square is actually tan. So it can be integrated directly to tan. Okay, so when you have cos square in the denominator, you bring that to the numerator, that becomes secant square. And then that it integrates to tan like this. Okay. Now, these are some examples from some recent papers. I'll quickly show you those examples. In this case, for instance, in the first part, they made you prove an identity. So you'll do that using trigonometric identities. And then they ask you to find this integral. You would have to use that identity, make cos cube theta the subject in that identity. So you proved this, cos 3 theta is identical to this. Make cos cube theta the subject. That gives you this. And replace that expression with that. So a lot of times what happens is they make you prove something in the first part, and then you have to use that in the next part. So when you replace it with this integration becomes quite straightforward. After that, integrate it, input limits, and you get the result. Now, when you're doing integration and you have limits given, a lot of times they want exact answers from you at the end. It's very important that you show all steps in that. When you input limits, you have to make sure that you show that step in which you're inputting the limits. And if they want exact values, you'll have to show more steps as well. And if you're getting something in terms of logs, then you have to write your final answer as a single log term, right? If you have multiple log terms in the final answer, it's necessary to write them as a single log term at the end. Okay. Let's look at this example. In this case, in the first part, they asked you to prove this identity, and then they wanted you to integrate this. Cot x, how do you integrate cot x? Cos over sine. And then you input limits. Make sure that you use exact values because they want exact values from you, and you get the result from that like this. In the third part here, you have cosecant of 2x. In the third part, you have cosecant of 2x. How do you integrate this now? Do we know how to integrate cosecant? We do not have a direct rule for this. So how do we do that? Now, in this case, they have not used the word hence. Otherwise, in a lot of such cases, they would use the word hence, and that will give you a hint that you have to use the previous part. But sometimes they just won't use that and leave it for you to think about it, to figure it out yourself. Cosecant 2x, we don't have a method that we have done to be able to integrate this directly. However, in the first part of this question, you have proved this identity that cosecant 2x can be written as cot x minus cot of 2x. Even though the question does not hint you towards that, you've done that in the first part of this question. You should be able to use that. Use cosecant 2x identical to cot x minus cot 2x, put that in this integral, and then integrate those two separately. So you say cosecant 2x can be written as cot x minus cot 2x. And then you know how to integrate cot x. Cot x, in fact, you've already done in the previous part. That gave you half ln 2. You can just put that there. Cot 2x, you write that as cos 2x over sine 2x. You could write that as cos 2x over sine 2x. And that can then be integrated using the ln rule. What's the derivative of the denominator? Derivative of denominator is 2 cos 2x. So we multiply by 2 here, and to balance that, we divide by 2 outside. And then we just simplify that. We apply the ln rule and input limits, simplify everything, and we get the final result from that. Right. So these calculations tend to be quite lengthy sometimes. You have to be careful in your working about plus minus signs, using exact values, and you have to save yourself from careless errors. Now, these are just some examples now. What I'll do is I will show them to you quickly, and then you can have a look at them in your own time. I'll be skipping through some of them, and then just focus on a few that I think have something that's important in terms of concepts. Okay, so I'll quickly scroll through them. I'll slowly scroll through them so you can have a look at them as well. And if there's something that I want to mention in particular, I will do that. So this is integration of sine squared 2 theta. That's the second part. Yeah. So you have this function. They want you to find the area under the graph. You use the formula for area under graph, area between graph and x-axis, integration of y with respect to x, using the substitution x equals sine theta. Now, how do you use the substitution? You find the derivative of this first of all, and then write it like this: dx equals cos theta into d theta. Replace in this dx equal to cos theta d theta and x with sine theta, and then just simplify that. You'll need some simplification until you get something like this: sine squared theta into cos squared theta. Now, this is very important. When you have a product like this, sine theta and cos theta multiplying. Now, how would you integrate this? You might think of integration by parts here, but this should remind you of something. When you have sine theta and cos theta multiplying, you have an identity that has these two things multiplying. And that's the double angle identity for sine. Sine 2a is identical to 2 sine a cos a. You could use that here because when that is rearranged, we get half sine 2a equal to sine a cos a, square both sides. And sine square a cos square a, that can be written as 1 over 4 sine square 2a. We could replace it with that. So it just leaves us with half sine square 2 theta. And that is what we wanted to prove in the second part, that integration can be written like this: sine square 2 theta. So that was a double angle. We got this sine square theta into cos square theta. So we had to use that double angle identity to convert it to that. And then how do we integrate this? We've talked about this before. Sine square 2 theta, we'd have to use double angle identity for cos for this, integrated input limits, and you would get the result from this. Okay, I'll answer your questions later on. This is another question that you can have a look at, a bit complicated, but a one-off. So I'll just, scroll through it. Does this have anything important? Okay, so sometimes you can end up getting infinity as one of the limits. This used to happen in paper 1 as well. There as well, it used to happen sometimes. You would have infinity as one of the limits. Now, all you have to do is just integrate like you would normally do. In this case, they've asked you to use a substitution for this. Now, when you use the substitution, how do you change the limits now? The substitution is u equals x power 1 over 2. If x is going from from 3 to infinity, then what about u? U would be under root 3. Under root infinity, what's that? That is still infinity. If you take square root of infinity, that is still infinity. So these are the limits that you have there from under root 3 to infinity. Now, how would you deal with them? You integrate it like you normally do. It ends up being tan inverse of u after integration. Right? 1 over u square plus 1, the integration of that is just tan inverse of u. Now you input the limits, it becomes tan inverse of infinity minus tan inverse of square root of 3. Now, tan inverse of square root of 3, you can evaluate this on your calculator. What about tan inverse of infinity? For this, you'd have to think about the function tan yourself. When is tan equal to infinity? When is tan of something going towards infinity? Think about the graph of the tan function. What does the graph of tan function look like? It starts from 0 at pi over 2. It goes towards infinity like this. So you would not be able to do that on your calculator. You would have to do it yourself. Think of the graph of tan function. It goes towards infinity when it's going towards pi over 2. So tan inverse of infinity, when you have here, you would write that as pi over 2. And then you simplify that, you get your result. That's pi over 3. Right? So tan inverse of infinity, that is pi over 2. Sometimes in these problems, you end up getting infinity in the denominator. So if you have anything over infinity, for example, 4 over infinity, that is basically 0, because 4 divided by an extremely large number, that is 0. But in this case, we have tan inverse of infinity. That is when tan approaches pi over 2. And that was something different that I saw in one of those questions. Let me scroll through further. Okay, sometimes they make you do something like this. In the first part, they wanted you to differentiate this cos x over sin x to show that the derivative of cot x is minus cosecant square x. And that's the first part of this question. So you write cot x as cos x over sin x, then differentiate it using the quotient rule, and that gives you minus cosecant square x. And then in the second part, they want you to integrate this thing, x into cosecant square x. Now, whenever you have something done in the first part like this, it will always have some use in the next part afterwards. Now, how can you use this first part in the next part? X into cosecant square x. It's a product. We apply integration by parts on this. U equals x, v dash equals cosecant square x. Now, how do we integrate cosecant square x? In the previous part, we proved that the derivative of cot is minus cosecant square. So what will be the integration of cosecant square? That will be minus cot x. Now, this is from 2019. In the recent papers now, from 2020 onward, you actually have this given in the formula sheet as well, as I showed you earlier. This integration is already given to you. So now you could use that directly. But if it was something else, and that they made you do something in the first part, find the derivative of something, in the next part, you should know that whatever you found as the derivative here, that means the integration of this thing is going to be cot x. So you could use that in the next part, right? Now for cosecant square x, we saw in the very beginning of this session that cosecant square integration of that is minus cot x. That's written in the formula sheet as well. So that's what you use there. Then you just apply integration by parts, simplify that further, input limits. It becomes a fairly difficult calculation because of those square roots involved, and then a lot of calculation. You want an exact answer as well, I assume. Okay, sorry. Yeah, you want an exact answer as well. That means you need to show working. So you do it step by step like this. Convert the multiple log terms to a single log term if there are any, and then you get that final result that they wanted there. Okay. Similarly, you find other questions. For example, this is the function. In the first part, it's about differentiation. We'll skip that. In the second part, they want you to use this substitution and partial fractions to find the exact value of this integral. Now, f of x was this fraction. How do you integrate this? They've given you a substitution, and that is u equals e raised to power x. You use that substitution. After using that substitution, you end up getting this. Now, how do you integrate this? They gave you a hint in the question that you have to use partial fractions. Even if they did not give you that hint, you should have been able to think about it yourself, that you can factorize the denominator into two parts like this, and then use partial fractions, and then integrate that separately. Now, in this case, they've given you a hint, but it's not necessary that they would always give you that hint. You would think of this fraction. Can you use the ln rule? Tan inverse, partial fractions. When you think about partial fractions, think about whether you can factorize the denominator or not. In this case, you can, so you should do that. Okay. Next, you just do it using partial fractions and then simplify everything. That's a pretty long working. They want an answer in this form, ln a. That means a single log term. Where a is rational, that means it could be a fraction, but it should be a single log term, not multiple log terms. So when you get the answer, it turns out to be something like this. You have to convert it to a single log term. What you do is the numbers that are multiplying outside, you take them to the powers and then apply the multiplication and division laws to write them as a single log term. You can have a look at this working as well. Sometimes they will give you constants like this, like we saw in differentiation earlier as well. Now, don't worry about them. That's just a constant. Treat it like a constant. and just work in terms of that. So in this case, you have x e raised to the power minus ax. It's a product. You apply integration by parts in this. U is x, v dash is e raised to the power minus ax, and then just apply integration by parts. Don't get worried about a. Just keep writing it as a or minus a. That's just like any other number. For example, it could be -3, -4. So you'll just do everything in terms of a. Eventually, in this case, what happens is when you simplify everything, you get this as the result, and the result is also in terms of a. Now, you have to keep it in exact form like this. Careless errors tend to happen in problems like these when you have constants involved, especially. So you have to be just careful about them. If the rest is just standard working, that would work like that. Again, in the first part, they ask you to prove an identity. And then in the next part, they want you to integrate something. Now, they want you to integrate this now, exact value of this integral. Now, in the first part, we proved that this thing was equal to cos 2 theta. So that's one thing that we can do. We can replace this with cos 2 theta. And that can be integrated directly. But the problem is, how do we integrate this? We saw this earlier as well, but in that question, we had a hint given in the question. Here, we are not given any hint. It's just 4 sine square theta cos square theta, and we're left to figure it out on our own, how to integrate this. Sine into cos, that should remind you of something. Sine and cos multiplying, if they have the same power, you can use the double angle identity for sine. Sine 2 theta is 2 sine theta cos theta. If you square that, that becomes sine square 2 theta, that equals 4 sine square theta cos square theta. So you can replace this right inside with sine square 2 theta. And then we know how to integrate that. We've discussed that before as well. Use the double angle identity for cos to get rid of that power, integrate that, input those limits that are given, and you want an exact answer at the end again. So you have to show all working, and you get the result from that. Okay. This is another example. In the first part, they wanted you to convert it to this form. First of all, r cos of something plus alpha. You did that. And then in the next part, they want you to integrate this. So that's the same expression in the denominator, 3 cos 2x minus under root 3 sine of 2x. You got that in the denominator here, and there's a square on top of that. Now, in the first part, you've already converted that denominator to this form. So you replace it with that form. And then in the denominator, now you have cos of something. When you square that whole thing, it becomes cos square of that. Right? And you have constant here, 3 over 12. You could write that outside to simplify things, 1 over 4 outside like this. And then inside the integral, we have 1 over cos square. Does that remind you of something? 1 over cos square. When we have cos square in the denominator like this, we could bring that to the numerator so that it becomes secant square. And we know how to integrate that directly. Integration of secant square is tan. We integrate that, and then we just input those limits and get our result from that. Okay. When you have a constant a like that, like we saw in the previous example, it's not necessary that they would tell you in the question that you have to give an answer in terms of a. Sometimes you have to figure it out yourself, as in from the question statement and from the context. You need to understand yourself that the answer will be in terms of a. It would not get eliminated, and that's all right. You would just leave it in terms of a. They would not always tell you that it has to be in terms of a. It's kind of going to be understood from the context of the question. This is another example. You can have a look at this working. There's nothing new here as such, but we just have to, apply that substitution, use that identity here as well. 1 plus tan square is secant square. Then we have secant square in the denominator. When you bring that to the numerator, you have cos square, and use that double angle identity to integrate that further. Again, you have something in terms of a. In the first part, they wanted you to find partial fractions, and the fractions that you have are in terms of a here. Now, in this question, they are telling you that the answer has to be in this form: P ln Q plus R ln S, where P and R are integers and Q and S are prime numbers. Even though this is in terms of A, they want the final answer not to have, they want the final answer not to have A in it, right? You would just do it the standard way. A is just a constant, remember, so its derivative would be 0. So the derivative of x plus 2a, that is 1. You have, that's the ln form. This is also ln form. This is also ln form. You integrate all of them, input those limits from minus a to plus a, and then convert that to a single log. And do they want a single log? No, they don't want a single log in this case. You just simplify everything. The a's get cancelled. Now, this is actually important because in this case, what we're getting is this is ln of 3a, and this is ln of 7a, and this is ln of a. They don't want any a in the final answer. So the question is telling you the final answer should not have an a, right? How do you get rid of a from here now? You break it down like this. Ln of 3a can be written as ln of 3 plus ln a. Ln of 7a can be written as ln of 7 plus ln a. And then you simplify everything. Ln a's will get cancelled as it's happening here. And you just are left with this. And that's your final answer. So you need to be very good at using the laws of logarithms here as well. Volume questions, they do come, but in paper 3, they're very rare. Mostly you get area questions, but volume questions do come sometimes as well, as in they are part of the syllabus. But in recent questions, you won't find many of them. It's mostly area that's tested in paper 3. But volume is indeed part of the syllabus. That is part of the syllabus. This is another example. You have to find this area, integration of sine x into cos 2x. Now, how would you do that? Integration of sine x into cos of 2x. Now, one idea is that you break it down and you expand this double angle as 2 cos square x minus 1. Simplify that and you get 2 cos square x into sine x here and sine x here. And then on the first integral, you could use the extended power rule as we discussed. That's one idea. Use the extended power rule here. So it becomes derivative of cos x is minus sine x. So we put minus outside, and to balance that, we put a minus outside, and it becomes that form. We use the extended power rule in this, and integration of sine is just minus cos, and then we integrate it like this. That's one idea. This is a fairly complicated example if you do it yourself the first time. Because if you think of integration by parts does not work. The loop method also does not work here because you don't end up getting that loop in this. And it does not become any simpler. So you either have to use the extended power rule, that's one idea, or the alternative here could be that you break it like this again. You say sine x into 1 minus 2 sine square x, and that could be broken down into two parts like this: sine x into 2 sine of cube x. Integration of sine x sine cube x, then you could either use extended power rule for this as well, as we discussed earlier, or you could use the substitution as we covered. So for sine cube x, use the substitution u equals cos x, and then you apply that process for that substitution and input the limits at the end, and you would get the result using this as well. Okay, so I hope that was helpful. That's many different types of questions that I've showed you here. Have a look at them. Why does the loop not work here? You do end up getting a loop in this question, but I think I remember trying this once. But what happens in this case is you end up getting an I on the left side and an I on the right side as well. So it ends up getting cancelled out. So instead of having a minus I on the right, it ends up being a plus I. So it's the same coefficient on both sides, and it ends up getting eliminated. So you don't get anything useful from that. So that kind of doesn't work in this case. But you can use one of these two methods, right? Okay, so I hope that was helpful, and I will not scare you too much with this. Now let me know if there are any questions. Okay, all right. Okay, so next topic is differential equations. Let's begin with this. What are differential equations? Differential equation is any equation that has a dy over dx term in it, right? So any equation that has dy over dx in it, we call that a differential equation. For example, this could also be called a differential equation, dy over dx equals 7x plus 3. Now, from this, if we had to find the function y, we could just integrate it directly because we had dy over dx, the subject on the left side, and on the right side, we only had x terms. We could just integrate integrate it with respect to x, and that gave us this. And we would have y in terms of x like this. However, sometimes what happens is you get equations in which you have both x and y along with dy over dx. How do you solve those equations? First of all, solving a differential equation means finding an equation that connects x and y without the dy over dx term. Without the dy over dx term, right? Now, what does that mean? This was an equation, that was a differential equation. When we integrated that, we got this. It was an equation that connected x and y without dy over dx. We would say this is the solution to that differential equation, okay? Now, generally, differential equation would look like this, in which you would have both x and y like this, both x and y. So you've got x here and you've got y here, right? How would you solve these equations? So let's say you've got this example. Solve x squared into dy over dx equals y, obtaining y in terms of x, that means y should be the subject in the final answer, given that y is equal to 2 when x is equal to 4. Now, how do you do that? First of all, the first thing that you always have to do when solving differential equations is that you separate the variables. You separate the variables. What does that mean? The side that has dy, you want all y terms on that side. And the side that has dx, we can take dx to the other side. Dx will be in the numerator here. So dy and dx, both of them should be in the numerator. So dx will be in the numerator on the right side. When it goes to the right side, we want all x terms on the right, all the y terms on the left. That means separating the variables, okay? So in this case, we could say, we could take dx to the right side, and now we want the x terms on the right, y terms on the left. So that becomes 1 over y into dy and 1 over x squared into dx. And now once the variables are separated, we've got one variable on one side, the other variable on the other side. Now we can just integrate both sides. Integrate the left-hand side, but that will be with respect to y. Integrate the right-hand side, that will be with respect to x. And now both of them can be integrated because the side that is supposed to be integrated with respect to x, that only has x, so that works, and the other side only has y, that also works. What's the integration of 1 over y? That's ln y. Integration of 1 over x squared, we would have to bring that to the numerator, x power minus 2, apply the power rule on this, and that becomes x power minus 1 divided by minus 1 plus c. Now, whenever we integrate, we always have plus c. We could have that on both sides here. However, we only put that on only once on one of the two sides, because even if you put that on both sides, you could just bring that other constant on the right side as well and make that c2 minus c1, and that's just another constant. So we could just write c on any one of the two sides, and that will be sufficient. In differential equations, just write c on any one of the two sides. And that gives you this equation, ln y equals minus 1 over x plus c. This is an equation that connects x and y. We say this is the solution of that differential equation, okay? We don't have dy over dx here, only x and y terms. So we say this is the solution. Now, at this point, we haven't found the value for c yet. This is called a general solution to this equation. You have to know this terminology as well. Sometimes they use this in some questions. Find the general solution. All that means is solve that differential equation and then just leave your answer in terms of c. You don't have to find the value of c in that. At this point, we call this a general solution. But then we were given some values here in the question, that y is equal to 2 when x is equal to 4. The point of giving that value is that you can use that set of values to find the value for c. Now, once you've got this point, once you've got to this point, you put x equals 4, y equals 2 in this equation. solve that and find the value for C. That turns out to be 1 over 4 plus ln 2, right? Input that value for C in that equation. This is what you end up getting. Now what you want is y in terms of x. You want to make y the subject. Now, where is y here? You've got y here. You have to make that the subject. Now, one idea could be that you just say base of ln is e, take that to the other side, it becomes the base of this whole thing, and you write it like this, but that's not acceptable. That's going to make you lose 1 mark because you have log in the power of e, and that's not a simplified form. We want to avoid having log in the power of e. How would you do that? You would bring all log terms to one side, ln y minus ln 2, bring that to the left side, apply the division law on this, that becomes ln of y over 2. Now you've got a single log, and now you can say e is the base of ln, that goes to the other side, becomes the base of this whole thing, and you get y equals 2 times e raised to power that, and that's your final answer. That's the solution of that differential equation, y equals 2 e raised to power minus 1 over x plus 1 over 4. That's how we solve differential equations. So what do? We separate the variables first of all, one variable on one side, the other variable on the other side, integrate both sides separately, and then whatever variable it is, in fact, first of all, find the value for C, given what is there, given the values in the question, you find the value for C, and then whatever it is that they want as the subject, we make that from the subject, and that gives us the final solution, right? So that's the idea that we use for finding solutions of differential equations. Now, in this case, when we have 1 over y, we cannot use power rule on this. That would not work because 1 over y is actually y raised to power minus 1. If you try integrating it using the power rule, that will become minus 1 plus 1, that's 0, divided by 0. So that does not work. So if you look at the formula sheet, they have this exception written there in the integration rule, that this integration is x raised to power n plus 1 divided by n plus 1. However, it's when n is not equal to 1, not equal to minus 1. When it's equal to minus 1, in that case, you use the log form 1 over x. That is basically ln x. So for power minus 1, we have to use log. So on the left side, we have to apply the log rule. On the right side, we take that denominator to the numerator and then apply power rule on that. Okay. So that's how this works. That's how you find solutions of differential equations. Now, sometimes separating the variables is going to be a bit tricky. So let's do some examples to understand how you would separate the variables. If you have this equation, you want dx on the right side, right? So the first thing you should do is just take dx to the right side. When you take that to the right side, you see that's going to multiply with the whole thing. Make sure to use brackets there. It's multiplying with that whole thing. So now what you want is x terms on the right, y terms on the left. There's no x term here. There's no x in this equation. So you just take y to the other side. Now you divide 1 plus y squared on the other side, like this. When you divide it on the other side, you're just left with 1 here, right? It won't be 0, it would be 1 here. And then you integrate both sides. The left side can be integrated using the log rule, as we discussed in integration. Integration of 1 is just x. Have a plus c there. Find the value of c by inputting these values that are given in the question. Find the value of c from that. Put that value of c. You would prefer leaving c in exact form as much as possible. Do not convert it to decimals unnecessarily. You would want it to be in exact form because it has to be inside an equation. In equations, we prefer writing everything in exact form. Okay, unless it's just not possible for some reason, which happens sometimes. But in most cases, we will keep this in exact form. So this is what we end up getting. That's the solution. They wanted y square in terms of x. So y square had to be the subject. What do we do for this? We've got multiple log terms. We take all log terms to one side. First of all, I multiplied the whole equation by 2 so that the fraction gets eliminated. And that gives us this. We take log terms to one side, apply the division law. And then the base e goes to the other side, becomes the base of 2x. And then you make y square the subject. And that's the result that you get from that. Okay, so that's how you solve these differential equations. If you had this equation, dx over dt equals 1 over x minus x over 4, how do you separate the variables for this? Again, the first thing you do is you just multiply this thing on the other side. So you have dt times this whole thing, okay? Make sure to use brackets there. Now, how do we take this to the other side? What you should do is you should first take LCM here. So it becomes 4 minus x squared divided by 4x. So it becomes a single fraction. And then you just take it to the other side, multiply 4x here, divide by 4 minus x squared. And now on the right side, you're just left with 1. What's the integration of 1 with respect to t? That's just t. On the left side, we use the ln rule. And then we just solve it further, input those values that were given, find the value of c from that, and then input them back in this. You have multiple log terms again. C was also in terms of log. So now if you want to make a particular variable the subject, they want x squared the subject, you would take log terms to one side, apply division law, and then make x the subject, x squared the subject like it's shown here. Okay. Let's look at another example. Now, this is another thing that happens. After solving an equation, they would ask you some 1 mark, 2 mark questions. So let's say you've got this equation, e power 2t into dx over dt equals cos square x. We have to solve this differential equation. Now, that first part is not that complicated. You take dt to the other side, take e raised to 2t to the other side as well, divide that on the other side, cos square x, we go to the left side. Now, on the left side, we have 1 over cos square. Remember what that becomes? 1 over cos square can be written as secant square x. This happens quite a lot. And then secant square integrates to tan directly. On the right side, we have e raised to power minus 2t. That can be integrated directly. We have a plus c. We find the value of plus c using the points that are given in the question t0, x equal to 0. And then once we have the value for c, we can make x the subject. And that becomes tan inverse of this whole thing. Okay. But then in the second part, they're saying, state what happens to the value of x when t becomes very large. Now, very large means when t goes to infinity. That's what they're saying. So when t goes towards infinity, what happens to the value for x? That's what they're asking about. Now, if this is the solution that you're getting, tan inverse of minus half of into e raised to power minus 2t plus 1 over 2. Now, if t becomes very large, what happens? I would recommend that you first make it a positive power. So take that to the denominator. That will help you think about it more easily. If t becomes very large, what happens to the denominator? T is in the power. The denominator will become very big, right? The denominator will become very big. When denominator becomes very big, this whole thing, that becomes 0. What are we left with? Just 1 over 2. So tan inverse of 1 over 2, that's the value of x that we end up getting from that. Makes sense? When denominator becomes very big, the overall expression, that becomes 0. So that's the value of x that we get. Now, that's a standard question that they ask a lot. What happens to one variable when the other becomes very large like this? Then they're saying, explain why x increases as t increases. What does that mean? Explain why x increases as t increases. So think about this. This happens in paper 1 sometimes as well. You have 2 variables. One is t and the other is x. If as t increases, x is also increasing, the graph would look something like this. It's going to go up, right? So as t goes right, x goes up. So the graph could look either like this or like this, right? Some form like this, that from left to right, it's going in the upwards direction. Now, when it's going in the upwards direction, can you say anything about the gradient of the graph? It's positive, right? The gradient is positive. As if x increases as t increases, that means they're directly proportional. They're both going in the same direction. The gradient is positive. If the gradient is positive, that means the derivative is positive, right? That's how you find the gradient of a curve. So can you somehow show that the derivative is positive here? You've got this differential equation, right? You've got this differential equation. e raised to power 2t into dx over dt equals cos square x. You make dx over dt the subject because that's the derivative, right? That equals cos square x over e raised to power 2t. Now the numerator, cos square of x, this is always positive or zero, right? A square can never be negative. So cos square, its minimum value is zero. What about e raised to power 2t? E is a positive number. For a positive number, whatever power you have, it's always going to remain positive. So this is also positive. That means the derivative is positive, right? So that's what you would write. You would say the derivative is positive. Since the derivative is greater than or equal to zero, that means as x increases, t also increases. And that's what you had to show there. Make sense? So as one variable increases, so if one increases as the other increases, that means they're directly proportional. The gradient is supposed to be positive. If they had said x decreases, x decreases as t increases, that would mean it would be a graph that's going down like this, right? And in that case, we would have to show that the gradient is negative. In this case, it's supposed to be positive. Okay, so sometimes they ask these small questions after this like this as well. Now, the other major thing that a lot of students find difficult is forming a differential equation. The first part of differential equation question sometimes, in which they ask you to form a differential equation yourself. And then in the next part, you have to solve that. Now, how do you form differential equations? There are some statements that you need to understand how to convert them to a mathematical form. So if they say rate of change of something, rate of change of y, for instance, how do you understand that? Rate of change of y is dy over dt. That's how we understand rate of change of y, dy over dt. Now they're saying it's directly proportional to x squared. Directly proportional, that means it's equal to k times x squared. That's the equation that you could make from that, right? So a statement like this, you could convert that to an equation form in this way. The rate of change of y, that's dy over dt. And then directly proportional, that means k times something, k times x squared. If rate of change of y is inversely proportional to 5 minus x, for instance, rate of change of y, that's dy over dt. Inversely proportional, that's k over something, that's k over 5 minus x. That's the equation that you have there. Rate of increase of x. So earlier they were talking about rate of change. Now they're saying rate of increase of x is directly proportional to 20 minus x. What about this? Increase, you would treat it the same way. Change, dx over dt, rate of change of x, is directly proportional to 20 minus x. That's k times 20 minus x. In this case, since it is supposed to be an increase, we know that the value of k that you would get eventually, that would always be a positive number, right? Because then it would be an increase. If it's a negative number, then it would be a decrease. So this k would turn out to be a positive number eventually. But the way to write this would be the same as before. Now, in this case, it's not, if they just say proportional as well, if they don't mention directly, and then that also means that they're talking about directly proportional. So if they just say one thing is proportional to another thing, then that's directly proportional. If it is inversely, they would always specify that. If they don't specify anything, you assume that's directly proportional. Then if they say rate of decrease of x is inversely proportional to x cubed. What about this now? Rate of decrease of x. Now, rate of change of x, what's the expression for that? Dx over dt. Now, since they're talking about decrease, we put a negative sign explicitly here, right? We put a negative sign ourselves there. K over x cubed, it's inversely proportional, so we say that's k over x cubed. Now, the value for k is still going to be positive, but you have this negative sign explicitly put there. That will make the whole expression as negative, and that means it's rate of decrease. So when they say rate of decrease, you will put negative sign yourself there, okay? So these are simple cases. A lot of times what happens is you've got one thing increasing and another thing decreasing. Let's look at this example. We have this container and water is being poured into this container at a rate of 1.5 meter cube per second. That's a fixed rate. That's the rate at which the water level is increasing. So we could say from this we get dV over dt, rate of change of volume, that is equal to 1.5, right? But at the same time, it's leaking out of the container as well. And it's leaking out, they're saying, at a rate that is proportional to the volume of water. It's leaking at a rate that is proportional to the volume of water. Now, when they say it's leaking, that means its rate of decrease, right? It's decreasing at what rate? Proportional to volume, that means K times V. Since it's a decrease, we say it's minus K times V. Okay, that's the rate of decrease. So what would be the overall differential equation that we get from this? Rate of increase minus the rate of decrease. What does that give you? You'll say dv over dt, that equals 1.5. That was just a constant number. That was not proportional or anything. That was just a constant. It's increasing at 1.5 meter cube per second. However, it's decreasing at a rate that's proportional to volume of water. For that, we have K times V. 1.5 minus K times V. Rate of inflow minus the rate of outflow, or the rate of increase minus the rate of decrease. That's how you'll make equations in cases like these, when something is both increasing and decreasing at different rates. Okay, that's the equation that you get. So these are simpler cases. Sometimes what happens is they will give you information about one variable. For example, they might tell you about the volume of water, that the volume of water is increasing and decreasing at a certain rate. And then they want you to find an equation, form an equation for the height of water or the depth of water, dH over dt. The information given is dV over dt, but they want you to make an equation for dH over dt. Now, what do you do for that? For converting dV over dt to dH over dt, you would have to use chain rule in such questions sometimes as well. These are going to be the relatively more complicated types of problems. Now, let me show you some examples of this. Let's say we have something very simple as this. A model for the height of a certain tree at time t years. So these are the variables, right? So highlight those variables. The variables are h meter, that's the height, time t years. While the tree is growing, the rate of increase is proportional to 9 minus h whole power 1 over 3. Rate of increase in height. Now that's the line that's going to tell you how to make the equation. Rate of increase of height is proportional to 9 minus h power 1 over 3. Now, have they mentioned whether it's directly proportional or inversely proportional? They haven't. We assume that's directly proportional. Okay. Rate of increase of height, how do you write that? That's dh over dt. That's directly proportional to this. We say k into 9 minus h whole raised to power 1 over 3. That's what the equation is going to be. But then we have to find the value for k. How do we do that? We've got this point given. At a certain point, t is equal to 0, h is equal to 1, and dh over dt is equal to 0.2. Now, in this equation, we've got dh over dt and h. We input h as 1 and dh over dt as 0.2. And that would give us the value for k. You can see what that is. That's 0.1. And then you input that back in that equation. That's the equation that we were looking for. Then in the next part, you might have to solve this equation. Then, based on that, find some particular thing. But that's how you form this equation. Let's take another example. You have this study on the spread of a soil disease. In this, what happens is an area of 10 meters square is exposed to infection. Now, the yellow line here, that's telling you how to make an equation. Where they talk about rate of something. Infected area grows at a rate which is proportional to the product of the infected area and the uninfected area. Now, they are saying the infected area is A, uninfected area is 10 minus A. Infected area grows at a rate of growth of infected area. How do we write that? Infected area is A, rate of growth of that, rate of change of that, that's dA over dt. Rate of growth of infected area, that is directly proportional. Proportional means directly proportional to what? We have K times product of the infected area, that's A, and the uninfected area, that's 10 minus A. That's what the equation becomes. dA over dt, that equals Ka into 10 minus A. And then you have to find the value for K. Do we have any information that's given here? So this is one piece of information that we have. Initially, 5 meters square is infected. So that basically initially means time 0. So at time 0, we are given that A is equal to 5. That's one piece of information. Anything else that we're given? They're also saying initially the rate of growth of the infected area is 0.1 meters square per day. So initially at time 0, dA over dt, that is 0.1. So we can input that when a is equal to 5. So in this equation, we don't have any t value that we can input. We have just a and dA over dt. So we input those values for that point. A5, dA over dt 0.1. Input those values, find the value of k from that, and you get that differential equation. Okay, and then you might have to solve that in the next part, and then do something based on that. Now let's look at a more complicated example. Let's say you've got this reservoir that has a horizontal base of 1,000 meters square. Rectangular reservoir, what does that mean? That's a cuboid, right? The base is a rectangle. If the base is a rectangle, then it's a cuboid, right? It has an area of 1,000 meters square. So base area is 1,000 meters square. It's a cuboid like this. At time t equal to 0, it is empty and water begins to flow into it at a constant rate of 30 meter cube per second. Now, this yellow line is telling you how to make an equation. Begins to flow into it, rate of inflow. What's that? That's 30 meter cube per second. At the same time, water begins to flow out as well. We've got rate of outflow as well, at a rate proportional to square root of h. Show that h satisfies this differential equation. Now, the information that's given is about volume, meter cube per second. They're talking about water beginning to flow out. How do you measure water? In volume. So we are given that the rate of inflow is 30 meter cube per second. How do we understand that? dV over dt, that is 30. That's the rate of inflow. Minus the rate of outflow. What's the rate of outflow? It's flowing out at a rate proportional to square root of h. That means k times square root of h. We subtract from that k times square root of h. And that's what the equation turns out to be. dV over dt is 30 minus k square root of h. Make sense? That's the equation that we get. Now the problem is they did not ask us for dV over dt. They wanted dH over dt. Now the information that was given was for volume, so we made dV over dt equation. Now we have to go from this to dH over dt. Now how do we do that? We have to use chain rule for that. dH over dt, we have two fractions. The first fraction will have this numerator. The second fraction will have this denominator. And in these places, we've got the third variable, which is dV in this case. And now we know the value for dV over dt. What we do not know is dH over dV. Where will this come from? We will need some equation that connects volume and height, right? Volume and height. Now, do we have an equation that connects volume and height? It's a cuboid. Water will be in the shape of a cuboid as well. What's the form that we've got for that? Base area into height. What's the formula? Base area into height, right? For the cuboid. Length into width into height. Length into width is 1,000. Into the height, that's h. So v equals 1,000 h. Now, from this, what we can do is we can find the value for dV over dH. Okay. From this, we can find the value of dV over dH. That's 1,000. So just like if you have y equals 1,000 times x, dy over dx, what would that be? That would be 1,000. In this case, the variables are different. Instead of y and x, we've got v and h. But the differentiation process will remain the same. We get 1,000 from that. Okay. So that's dV over dH. Now we put that here. This is dH over dV. So we put reciprocal of that, simplify that, and we get this expression. Now we have to find the value for k. Do we have any information that's given? They've given that h is equal to, when h is equal to 1, dH over dt is 0.02. We input those two things here. And that gives us the value for k. We put that value of k back. And the equation that we get is this, dH over dt equals this. Now they want us to prove that it becomes this thing. So in the numerator, they have 3 minus square root of h inside the brackets. So what we can do is we can take 10 common from the numerator so that we're just left with 3 minus square root of h. That's what you want inside brackets. And then outside, we've got 10 over 1,000. That becomes 0.01. And that's the equation that we were looking for. dH over dt equals this. right? So that's the more complicated part when you have information given about one variable, and what you have to prove is in terms of another variable. Make sense? When you have two things that are proportional to each other, for example, y is proportional to x, how do you make an equation out of that? Y is equal to k times x. So when they talk about proportionality, we have k in that case. So in this case, they said the water is flowing into it at a constant rate of 30. So 30 is just a constant. That's just 30. It's flowing out at a rate that's proportional to square root of h. When you have proportionality, we have that constant of proportionality, right? K is the proportionality constant that you have done in paper one, is in O levels as well, right? Directly proportional, inversely proportional. That's what we get from this. Okay, so that's how you might have to form these equations. This is another example that you can have a look at. In the first part, you just have an equation that looks like this: dA over dt equals k into square root of 2a minus 5. Now, they haven't given any information to be able to find the value for k. But then in the next part, they have given that at the start of the investigation, what does that mean? At time 0, area covered by the weed is 7 meters squared, a is equal to 7. And 10 weeks later, that means when time is equal to 10, a is equal to 27. We've got these two values given. And we have to find the area covered 20 weeks after the start of the investigation. Now, how do we do that? It's a 9-mark question. That's a lot of marks because you have to do the thinking yourself as well, as in how exactly to find this. You'll have to follow that whole process. This was the differential equation. You solve this differential equation. How do you do that? You separate the variables first of all, then integrate both sides separately. You can see them. You just have to apply the power rule on both sides. Now, the problem is we don't have the value for k here. We don't have any information that's given for dA over dt, so we can't find the value of k in the first part, right? So what we do is we do everything in terms of k. So eventually when we have integrated, we get this expression in which we have both k and c. Now to find the values of k and c, you have those 2 points given. Those two points are t equals 0, a equals 7, t equals 10, a equals 27. You input those 2 points one by one, and they give you the values of c and k. Once you have them, you get this equation, and then you find the value for a. 20 weeks after the start of the investigation, you put t equals 20 in that and find the value of a from that. That turns out to be 63. That's not much work for 9 marks. That's a lot of marks for just this. But that's what can happen sometimes as well. That you have some constant here in the differential equation already, then you have a plus c as well. And then they have 2 points given that you can use to find both of those constants eventually. Let's look at another example. You have this differential equation, dn over dt that equals this. It's given that n is 125 and t is equal to 0. Solve this differential equation, obtaining a relation between n, k, and t. Now, they've not specified that you want a specific variable as the subject. All you have to do is separate the variables. First of all, you separate the variables, integrate both sides, then input n equals 125, t equals 0 to find the value for c, and you get this thing. Then since you want any relation between n, k, and t, this would suffice. You could leave it like this as well. Or it's a better idea to convert it to a single log term. You've got multiple log terms here. Even if they have not specified that you want one variable on one side, one variable is subject, it's still a good idea to make it a single log term, because sometimes they have 1 mark for this at the end, and it's not clear when they have it and when they don't have it. So you should always do it, convert it to a single log term. Then you can leave it like this, and you can say, this is the relation between n, k, and t. Right? That's the solution of this differential equation. In the second part, they want you to find the value of k given these points. You can do that. But then they're saying, obtain an expression for n in terms of t and find the least value of n predicted by this model. Least value of n. Now, how do you do that? You had this differential equation. We had already found the value of k here as well. How do you make n the subject? First of all, they wanted n in terms of t, right? You can take e to the other side, it becomes this, and then n equals this thing. So you've got n in terms of t. Now, what's the least possible value of n here? How do we think about this? For n to be least, we would want the power to be as small as possible, right? Now, the only thing that is a variable here is this t, right? So that is inside the sine function. What do we know about sine function? Sine is maximum at 1 and minimum at -1. The sine function is between -1 and +1. So we just check what happens at those extreme values. In fact, in this case, we know that we want the power to be as small as possible. So just use the smallest possible value of sine that you can have. The smallest possible value of sine is -1. You input that here, and that gives you the least possible value of n. Since we're talking about number of something here, number of insects, so at the end, the answer that we write, it's a better idea. It's a good idea to write that as an integer. The least value of n predicted by the model, that's the number of insects. So you write that as an integer, that's 76. That's your final answer. So when you have sine cos functions like this, we've seen this before as well in other topics as well. For least and greatest values, we use -1 and 1 and see what happens at those values. Whichever then gives us the smaller value, that's the least value. Whichever gives them the bigger value, that's the greatest value. Okay, this is another example. Just the first part of this. It's a bit tricky, a different kind of question. And so you have this curve, and they're saying the normal to the curve at this point P that meets the x-axis at the point n. So this is the normal. That's meeting the x-axis at the point n. M is the foot of the perpendicular from P to x-axis. This is the perpendicular coming from P to x-axis. M is the foot of the perpendicular. Show that Mn over y is equal to dy over dx. Now, how do you do that? Mn over y equals dy over dx. How does that make any sense? Now, what is Mn over y? That's this length over this length. Where is that coming from? We could think of it like this. What's the relation between the gradient of the curve and the gradient of the normal? Gradient of the curve, that's just dy over dx, right? Dy over dx is the gradient of the curve. So we could say that's dy over dx, gradient of the curve. Gradient of the tangent at that point is also going to be the same. What about gradient of the normal? This is what the normal looks like, right? This is the normal. For this line, we know the change in y and the change in x, right? Gradient is given by change in y over change in x, right? What's the change in x? Mn, this length. Change in y, that's negative change, right? Y is decreasing. So we say that's minus y divided by Mn. That's the gradient of the line Pn. Change in y over change in x, right? And then we could say gradient of the normal and the gradient of the tangent, the product should equal -1. We rearrange that, and that gives us that equation that they wanted us to find out. Okay, so a different kind of question, not exactly in differential equation, I say, but that's how you would approach that. In the next part, they say, hence show that x and y satisfy this differential equation. Now, how can you do this now? X and y satisfy this differential equation. Now, are we given any information in the question? So they're saying the area of the triangle PMN is equal to tan x, right? That's the information that's given in the question. Area of triangle PMN is equal to tan x. So you can find the area of triangle PMN. That's just half into base into height. Base is mn, height is this. So you could say half into mn into y. That should equal tan x. That's an equation that we get. Now, using the first part, we could convert mn to something in terms of dy over dx. So mn can be written as y into dy over dx, and then we just rearrange that to get that differential equation. And then in the next part, we just have to solve that, right? That's just a different kind of question. Just want to show that. Okay, let's have a look at this. Okay, so sometimes they give you problems like these in which the constant that you get and the constant that they want here, that they're both different from each other. Now, let me explain what that means. So they have said You have this container, water is flowing out at a rate proportional to square root of h, right? Rate of outflow is proportional to square root of h. How do you write that? dv over dt, rate of change of volume, that's minus k into square root of h. Okay. And then you want to show something in terms of dh over dt. You use chain rule for that. Now for chain rule, you have dh over dv into dv over dt. This is already known. What about dh over dv? We need some relation between height and volume. We know that the volume is given by this. They've given us the volume formula here for this container. We use that to find dv over dh. That turns out to be this. Put that here. dh over dv will be reciprocal of that. Simplify that. And after simplification, we get something like this. Minus k divided by h power minus 1 over 2. So I've taken this h to the denominator. This was h power 1 over 2. They did not have any h in the numerator here, so I took that to the denominator. And now in the denominator, we've got h power minus 1 over 2 like this. Okay. Now we multiply that, multiply this inside. And now in the denominator, in the bracket, you have what you want there. Outside, the constant that you are getting is k over pi. That's a constant. K over pi is a constant. They wanted us to show that h and t satisfy this differential equation of this form. Now we are getting minus k over pi times that. They have minus b over something. We could say this k over pi, both of them are constant. K is a constant, pi is a constant. Both of them are positive, right? Because of the rate of outflow, we have explicitly written this negative outside. So this k has to be positive. So we could say, therefore, the value for b is actually k over pi. We could replace that with b here. And that's the proof in the first part. In the next part, I just have to solve that equation. Then you can do that. I'll show that working for you. It's a bit complicated because of that unknown b there. So you do everything in terms of b, integrated, and then you have a point given, t equals 14 and h equals 0. You input that point there. In fact, you have 2 points given. You have this point, and also at time 0, height is equal to radius, h is equal to r. You input those 2 points, and then just find that equation in terms of h and r. You can have a look at this working. It's a bit complicated because of those letters that are involved. The method is not that complicated, but a lot of working that's involved there. Okay. You can have a look at this in your own time. A lot of algebra. Okay. Yeah, it's almost ending. Then we'll have a break. We'll have a longer break then. I'm also tired. Okay. This is another example. We have this differential equation. It's given that n is equal to 300 when t is equal to 0. Find an expression for n in terms of t. You can do that. Just separate the variables. I'll just leave this here. When you separate the variables, you get n into 1800 minus n here. So you have to use partial fractions for that, break it into partial fractions, and then simplify that. You get this integral that's pretty long working. And then eventually, at some point in future, you end up getting this. N equals 1800 EH per T over 2 divided by 5 plus EH per T over 2. Again, another question that's a bit tricky. I'm leaving this working here for you to have a look at. It's a 9-mark question, so that deserves this working, I think. I'll scroll through this a bit slowly. You can have a look at this in your own time later. And then they're saying, what happens after a long time? What happens to the value of n after a long time? A long time means t is going towards infinity, right? T is going towards infinity. So what happens as t goes towards infinity? You think about this now. Now, this requires some thinking. So make sure that you're paying attention now. If t goes towards infinity. What do you have as the power of e? That's infinity over 2. Infinity over 2 is still infinity, right? That does not make a lot of difference. In the denominator, you have e raised by infinity again, infinity over 2. That is not making a lot of difference. So now you have 1800 times e raised to power infinity divided by 5 plus e raised to power infinity. Or you can just have infinity over 2 here as well. Both of them are the same. Doesn't make any difference. Now, how do you find the value for n from this? Now, they've not asked you for an exact value here. They've not asked you for an exact value, have they? No, they haven't. So one idea could be that you put a large value in your calculator. So in place of t, put a large value. Sometimes if you put a very large value, your calculator will give an error because it can't handle that. In that case, you try relatively smaller values, and eventually you will see that the value becomes stable somewhere. So I'll show that to you. For example, if you have, or I'll not. You can try that. You can try some large value of t, for example, 1000. Most likely that will give you an error. Then try a smaller value, maybe 100, something like that, and some value will eventually work. Whatever that is giving you, that's going to be the result that you get. Or you can think of it logically. The logical way of thinking about this would be, you say it's 1800 into e raised by t over 2 divided by this. Now, if we have a very large number, an extremely large number, and you multiply that by 1800, does that make a difference? That does make a lot of difference. If you have 1 billion, you multiply that by 1800, that makes it 1800 billion. That's a lot. That's a lot, right? That's a much bigger number. However, if you have 1 billion and you add 5 to that, does that make any difference? 1 billion and 5? Not really. So when you add or subtract something to infinity, that does not change much. So we could say the denominator is actually approximately just e raised to power infinity over 2, right? Adding 5 to that does not make a lot of difference. So then these two get cancelled and we're just left with 1800, and that's the final solution. It becomes stable at 1800. Okay. So that's how you could think about this. A bit tricky, but that's how you would do it. Okay, let's move on. Okay, a few more examples, and then we have a break. What I'll do is I'll just quickly scroll through them. There's nothing that I particularly want to discuss here. These are just some relatively more complicated examples. You can have a look at them. In this question, in the second part, they made you find the quotient and remainder when 5r squared is divided by 50 minus r. And then in the next part, they want you to solve a differential equation. Now, out of the blue, they made you do a division in a differential equation problem. You should understand that that might be used in the next part then. In the next part, when you separate the variables, you end up getting this improper fraction, 5r squared over 50 minus r. How do you integrate improper fractions? Quotient plus remainder over divisor. And you've done that in the previous part. You found the quotient, the remainder. You can use that here, write it in two parts like this, and then integrate that. Find the value for c, simplify everything, and then find the result from that, right? You can have a look at this working. Another problem similar to that, they wanted you to show that dh over dt is minus lambda into square root of h, where lambda is a positive constant. Now, using the information given in the question, you get something like this, minus k into square root of v. That's dv over dt. You use chain rule. Use chain rule to find dh over dt. When you do that, you end up getting this expression. That's minus k over 4 pi raised to power 1 over 2 into square root of h. They said it should have been lambda into square root of h. So now you say this whole thing, k over 4 lambda raised to power 1 over k over 4 pi raised to power 1 over 2. We could say that's lambda. That's just a constant, right? K is a constant, 4 is a constant, pi raised to power 1 over 2 is a constant. So we could think of that as lambda and write that equation like this, minus lambda into square root of h. Make sense? That's the equation. And then the next part, you just have to solve that. This is the working that you have for that. That's not very difficult in this case. Another example in which in the first part, they make you find some derivative. You see, you have y, they make you find the derivative for that. And then in the next part, we have a differential equation to solve. Now, why did they make you do that differentiation in the first part? How is that relevant to differential equation? When you separate the variables here, you see, after separating the variables, you end up getting sine theta into secant raised to power 4 theta here. Now, how do you integrate that? If you were to do it directly, that will be pretty complicated. In the first part, they made you find this, that the derivative of secant cube theta is this. That means integration of 3 sine theta, secant raised to power 4 theta is going to be secant cube theta. So that's what you can use here. We've got sine theta into secant raised to power 4 theta here, right? That's what we had. Just sine theta into secant raised to power 4 theta. We had cos raised to power 4 theta in the denominator. You have to actively look for how to get this form that they had, because there's some reason they've made you do that in the first part, right? So you were getting sine theta over cos raised to power 4 theta. You take cos raised to power 4 theta to the numerator, so it becomes secant power 4 theta. And now this is what you have. You want a 3 there as well. So what you do is you multiply by 3 and divide by 3 outside. And now you have exactly that form that we had in the first part. This integrates to secant cube theta, and that's this integration done. On the right side, you just apply the ln rule and tan inverse rule after splitting the numerator. It can't be done directly. You split the numerator first of all like this, and 3 over x squared plus 9. Integrate the first one using ln rule, the second one using tan inverse rule. You have a plus c there, find the value of c, and then you just simplify that further. That's quite some working, and eventually get the result that you want from that. You wanted the value of cos theta when x was equal to 0. So once you had that equation, you put x equal to 0 in that, and then found the value of cos theta from that. Okay, you can have a look at this working. One last example, I think. Yeah. So this is another one that you have. You have this container. It's a 5-mark question now in which they want you to prove a differential equation, show a differential equation. How do you do that? How do you do that? dv over dt is minus k over t. Based on the information given in the question, the container decreases in volume at a rate which is inversely proportional to t, right? So minus k over t. Decreases, they have a negative sign because of that. Inversely proportional, that's k over t. And then what they want us to prove is dx over dt. So we have to use chain rule for that. How do you find dx over dv? We have the volume of the cuboid. That's x into 10 minus x. That's the volume of the cuboid. So v equals this. We can simplify that and then find the derivative of that, input that in the chain rule, and you get this expression. And then you are given that when time is 1 over 10, x is 1 over 2, and the rate of decrease, now this is important. They're saying rate of decrease is 20 over 37. So what about dx over dt? That will be minus 20 over 37, not plus 20 over 37. That will be minus 20 over 37. You input those values here. In place of x, you input 1 over 2. In place of t, you input 1 over 10. In place of dx over dt, you input that. So you had to put all of these values here because we've got t here as well, we've got x here as well, we've got dx over dt here as well. Use those to find the value of k. That turns out to be 1 over 2. Then you have this equation, and then you convert it to the form that they wanted. That's the differential equation that you get. It has both t and x in it on the right side. Okay, that's the differential equation. And then in the next part, they want you to solve this, obtaining an expression for t in terms of x. You can have a look at this working. That's how it would work. Separate the variables and then integrate both sides. These are easy integrations, but then you have to find the value for c. That's quite some calculation. And then at the end, you want your answer to be in the form where t is the subject. Okay. Now I'm just reminded of one other problem that sometimes people find difficult to separate the variables in. For example, if you had dy over dx, that was equal to e raised to power x plus y. How do you separate the variables in this case? Using indices rules, you would say it's dy over dx, or let's take dx to the other side as well. Dy equals e raised to power x plus y into dx. What we want is we want X terms on right side, Y terms on the left side. Now, how do you separate X and Y here? You can use the indices rules and you can say it becomes e raised to power X into e raised to power Y into dx. E raised to power Y goes to the other side now and becomes e raised to power minus y into dy. On the other side, you've got e raised to power x into dx. Integrate both sides, and then you can, find the solution for this. All right. So that's all that you need to know about differential equation. I hope that was helpful. Just a quick check if you can see my screen still. Yes. Okay. Okay. So the next topic is iteration. Now, what is iteration? In your syllabus, you've done a number of different types of equations. You know how to solve different types of equations. For example, quadratic equation, cubic equation, trigonometric equation, when you have sine, cos, tan, cosecant, secant, cot involved, logarithmic equations, e power something, right? Exponential equations. But there's still a lot of equations that you do not know how to solve. For example, if you had something like this, ln of 2x plus 1, that equals 5x cubed plus 2x minus 3. Now, do you have an idea of how to solve this? No, because we've got a cubic function combined with a log function, right? We don't have an algebraic method that we know of to be able to solve equations like this. Similarly, we can't solve this. So for problems like these, for equations like these that we do not know how to solve, we need some other methods, right? One idea could be finding the solutions using graphs, for instance. You could say, this is one function, this is another function. For this particular case, you could say, let's draw the graph of y equals tan of 2x. Let's draw the graph of y equals e power 5x minus 2. And using the graphs, look at the point of intersection of these two functions. Wherever they intersect, that's the solution of this equation, right? But that will not be very accurate. You can at least estimate the solution using this process. But how do you find more exact answers? That's what we use this process iteration for. It's called numerical method. It's a numerical method. There are actually multiple numerical methods that are there. In our syllabus, we only have iteration, right? This is one method that we use for solving equations. Now, what do we need to know about this topic? First of all, if you have an equation like this, for instance, x cubed minus x plus 3 equal to 0, if you wanted to solve this, you could make a graph of this like this, and then wherever it's intersecting with the x-axis, y-axis, because one function is this, the other function is this, y equals 0 is x-axis. So we are basically looking at where does this graph intersect the x-axis, right? Now, on the graph, we can see it's intersecting somewhere between -2 and -1. So using this, we have an estimate of the solution that, okay, this is going to be somewhere between -1 and -2. At least this much we can understand from the graph. Now, notice one thing. When this graph intersects the x-axis, towards one side of that, you have a positive y value, right? Y value is positive here. On the other side, the y value is negative. Between them, the y value becomes equal to 0. So when we want to find the solution when y is equal to 0, on one side of that point of intersection, on one side of that solution, the y value will be positive. On the other side, the y value will be negative. So that is one thing that you'll have to do, first of all, in this topic. You'll have to figure out by calculation whether a solution exists between two given values or not. Now, this is one way to do it graphically. So if you draw a graph, your graph will be intersecting the x-axis somewhere between -2 and -1. But we could do the same thing by calculation as well. How would that work? Let's say you've got a problem like this. Prove by calculation that a solution to this equation lies between -2 and -1. It says prove by calculation, not by sketching graph. How can you do that? We can say this is the function x cubed minus x plus 3 equal to 0. Now, whatever the shape of the graph is, doesn't matter. There will be some point at which it intersects the x-axis, right? What we'll do is, we would say, let's input the x value -2 in this expression. That gives you -3. So that means when x is equal to -2, the y value is negative. Input x equals -1 in that expression, and that gives you a positive value. That means When x is -1, the y value is positive. So if at one point the y value is negative, at the other y value is positive, it's necessary that between those 2 points, the graph is going to cross the x-axis, right? And it has to go from the negative side to the positive side. That means 0 will come in between that, right? When you go from negative to positive or from positive to negative, you have 0 in the middle. So that means if one value is negative, the other is positive, there has to be a solution between these two values. And that's what we say, since f of -2, if you call this function, if you call this expression f of x, f of -2 and f of -1, they have different signs. That is why there's a solution that exists between these two values, right? That's one thing that you have to do in this topic. They'll ask you to prove that a solution of an equation exists between two given values. What you would do would be, you would input those values in that expression one by one. You input -2, input -1. One of them will be positive, the other will be negative. And you would say, since the sign is changing or the signs are different, that is why a solution exists between those two values, right? Writing down the statement is important, where you either refer to the signs being different or that the signs are changing. That is why there's a solution. Let's take a look at another example. So let's say we've got this. Now, this is a different equation. We have to prove that a solution of this equation lies between x equals 1 and x equals 2. Now, we cannot just input values of x in this directly. First of all, we have to bring all terms to one side so that the equation becomes in this form. F of x equal to 0. You have all terms on one side, only 0 on the other side. So the first thing you have to do is you have to convert your equation to this form. Everything on one side, only 0 on the other side. Once you have done that, the expression that you have on the left side, you will call that f of x. And now you just input those values of x in this. Put x equals 1 in this, put x equals 2 in this. One of them is giving you a -3, the other is giving you +23. Sign is changing. You say a solution exists between these two values because of that. Okay. So that's the method that we use for this. First of all, convert the equation to this format, bring all terms to one side, find f of a, f of b. A and b are the different values that they give. If they have different signs, you say that a root exists or solution exists between those two values. But then we have proved that a solution exists between those two values. Now, how do we actually find that solution, right? For that, we have this process that we call iteration. Okay, we have this process that we call iteration. Now, first of all, let's understand how to use an iterative formula. We'll understand where this comes from later on, but how to use this formula? Let's say you've got this equation, x power 5 minus 5x plus 7 equal to 0. That's an equation that we've got. It's the same equation that we were talking about here. We have already proved that the solution of this equation is going to be between 1 and 2, right? The solution is between these two values. Now, what is that value? What exactly that value is, we have to find that out, okay? Now, for this, let's say we know this iterative formula that they've given. We will use this iterative formula to find the solution. Now, how does this formula work? You need a starting point for this, first of all. The starting point is going to be your best guess about the solution, right? Your best guess about the solution. So in this case, we have proved that the solution exists between x equals 1 and x equals 2. What's our best guess about the solution? We could say midpoint, right? It will be somewhere close to 1.5. We could put some other value as well, but the convention is when we know that it's between 1 and 2, now we don't know where exactly it's going to be. We say, okay, our best guess is the midpoint. Okay, that's 1.5. So that's what we start from. So the first value that we use here, x1, that is 1.5. That's the first value that we use here. Okay. Now that's x1. How do you find the next iterations from this? When n is equal to 1, we get x2. We can get x2 from that. Put n equal to 1 here. You get x2 from that. On the left side, on the right side becomes x1. So the idea is whatever value you're getting in the previous step, you are inputting that in the next step in this formula. So 1.5, you input that as the value for x1 here. And then whatever result you get from that, this value, you input that again in x for finding x3. So the formula in the next step becomes x3 equal to 5x2 minus 1 whole power 1 over 5. You input that value here in place of x2, and you get the next value. and so on. You keep repeating this until the value becomes stable. Now, you will not be doing this manually. You'll be doing this directly on your calculator. Let me show you how that's done. This is just for understanding how this process works. It's an iterative process. You find one value, input that again in the formula, find another value, input that again in the formula. You keep repeating this process until the value becomes stable, and that will be the solution of this equation. Now, how do you actually do it? Let's say this is the iterative formula that you have. You know the starting value is 1.5. Okay. What you would do would be, in your calculator, you would input 1.5 first of all. That's your starting value. So input 1.5, press the equal to button. That saves this number in the answer button of your calculator. Now what you do is, you input this formula in your calculator, like this. You'll say 5, or bracket first, 5 into, in place of xn, put answer, so that whatever you got the previous time, that gets input into this function as the next value, as the next input. So you'll say 5 into answer. So in place of xn, you would write answer minus 1 whole raised to power 1 over 5. You'll write the formula exactly like this. Just replace xn with answer. Okay, let's do that. And that gives us this iteration. Now they will tell you how many decimal places to use for each iteration and for the final answer. In this case, they've told that you want 5 decimal places. You get this result? You have to make sure that you round off the values correctly to 5 decimal places. In this case, the first value turns out to be, x2 turns out to be 1.45406 to 5 decimal places. You press the equal to button again, that gives the next value. Now in this case, notice, you're getting 1.443636. When you round this off to 5 decimal places, the last decimal here will become 4. If you do not do that, if you write 3 here, you lose 1 mark. Okay, so in iteration, they deduct marks for very small things. You have to be a bit careful about this. Make sure you're rounding off values correctly. So you keep going on, keep writing down these values like this, okay? Until the number becomes stable and it does not change anymore. You have to write down each iteration. You cannot just do it on your calculator and write down the final answer only. No, you have to write down each iteration. So you keep going on, writing down every single iteration, and eventually what happens is it becomes stable and it does not change anymore. And you say, therefore, the solution that you have is x equals 1.441 to 3 decimal places. They wanted each iteration correct to 5 decimal places and the answer correct to 3 decimal places. So you write all the iteration to 5 decimals, and then when it becomes stable, you write down the final answer to 3 decimal places. These are the easiest 3-4 marks in your paper. Make sure that you do not mess this up. That's the result that you get from this. Okay. Now, sometimes, in very rare cases, they will not tell you the level of accuracy you need for iterations, but they will tell you what the final answer needs to be. For example, they might tell you for the final answer, you need 2 decimal places. Iterations will be 2 decimal places more than that. Okay. So if this is for the final answer, for iterations, you would be using 4 decimal places. If for the final answer, they say you want 4 decimal places, your iteration will have to be 6 decimal places. So sometimes it happens that they only give you the level of accuracy for the final answer, not for iterations. For iterations, you will just use 2 extra decimal places as compared to the final answer. Okay. But mostly they'll tell you what to do. Okay. Now, how do you get that iterative formula? Where does that come from? Now, there's a logic behind it. We'll skip that. But this is the method that we follow. We've got this equation, x power 5 minus 5x plus 1. If we had to make the iterative formula ourselves, how would that work? We've got 2 x terms here. One is x power 5, the other is this x here that's appearing with 5. What we do is we make any one of these the subject. That's not probably the correct terminology for this subject. You bring one x term to one side, everything else to the other side. So for example, you can choose this x term. Bring this to the left side. So you have x power 5, that equals 5x minus 1. Take everything else to the right side. So it becomes 5x minus 1 the other side. Now, the one that you have on the left side now, you want its power to be 1. It's power 5 right now. You want its power to be 1. How will that happen? You take power 1 over 5 on both sides, and that gives you this. X equals 5x minus 1 whole power 1 over 5. And then all you have to do is, on the left side with the x, you put n plus 1. On the right side with the x, you put n. And that's your iterative formula. This is one possible iterative formula that we could make from this equation. And that was the one that we used in the previous example. But you could have another iterative formula from the same equation as well. And that would be if you made this other x the subject, this x the subject, as in keep this x on one side, everything else on the other side. How would that work? You could take minus 5x to the other side, or take the other terms to the other side. So it becomes minus 5x equal to this. Multiply the whole equation by minus to get rid of that negative sign. Divide by 5 on the other side. You get this. And then all you have to do is put n plus 1 with the x on the left side, put n with the x on the right side. If you have multiple x on the right side, so that can happen as well. For example, you might have another x here. With every x on the right side, on the right side, you put xn. Okay. Now these are two different iterative formulas. One of these will give you one possible answer. The other will give you another possible answer. So they will not both work at the same time, right? So for one solution, this might be working. For another solution, this might be working. So it's a power 5 equation. So it can have up to 5 possible solutions. So some of those solutions might come from this iterative formula. Some of them might come from the other iterative formula. Okay. Now, how do you know which one? We don't have to know that. Okay. Yes, you do have to know how to make an iterative formula. Yes. But in the question, you will get a hint about which of these two formulas you would have to use, right? So it will be clear from the question which of these is going to be used. Okay. And we'll look at some examples for that. If you have the iterative formula given, for example, if you know this is the iterative formula, and you have to go back to the original equation. So this is the iterative formula. We want to know which equation does it come from. Okay. For that, we just do the opposite. Remember what we did here? We put n plus 1 and n at the end in the last step. We can get rid of n plus 1 and n from this. And that gives us this equation. Then just simplify that. And you get this power 5 equation. And that's the equation from which the iterative formula is coming. Okay, so you need to be able to do both ways. If you have the equation given, you should be able to find the iterative formula. If you have the iterative formula given, you should be able to find the equation that it comes from. Let's look at this example. You have this equation. It has one real root alpha. First of all, it says show that alpha lies between 1 and 2. You can do that, right? Convert it to f of x equals 0 form. Have only 0 on the other side. We already have that. Input those two values. One of them is negative, the other is positive. You say they have different signs. That's why the solution exists between those two values. Now they're saying there are two iterative formula derived from this equation, right? You can understand how they're derived, right? The same way we did it for the earlier example. You can make this x the subject or this x the subject, and that will give you these two iterative formulas. Now they're saying each formula is used with initial value 1.5. Show that one of these formulae produces a sequence which fails to converge. And use the other formula to calculate the value for alpha, correct to 2 decimal places, give the result of each iteration to 4 decimal places. Now, how would that work? Fails to converge. What does that mean? When we used this iterative formula earlier, the value was becoming stable somewhere. So we can say this value is converging to a specific value. This terminology is used a lot in iteration. They will say, this is the sequence of values that you're getting, and that's converging to a specific value, right? This is the sequence x1, x2, x3, x4, and it's converging to this final answer, okay? They're saying, show that one of these formulae produces a sequence, that means x1, x2, x3, x4, that fails to converge. Now, what does that mean? Let's apply these iterative formulas. This is one iterative formula. This is the other iterative formula. We start both of them with 1.5. Let's look at the first one. When we input 1.5 there, we just do this on our calculator like we did earlier. Keep writing down the iterations and see what happens. x2 is this, x3 is this, x4 is this, x5 is this. You see, the values are going towards negative infinity. They're not, the distances between consecutive values, they're actually increasing. Rather than becoming stable, it's going further and further away in one direction. So it's becoming, 0.37 here, negative more negative, even more negative, and you keep going on for a few more steps, it'll reach negative infinity, right? It'll go towards negative infinity. Now, this is not converging. This is not becoming stable at any value. So that's what you say. This formula fails to converge. What about the other formula now? The other formula, you see, it becomes stable gradually, and it becomes stable at this value. And you say that's your final answer. You write down the final answer to do 2 decimal places. Now, in this case as well, it's very important. They wanted you to find the value for alpha. In the final answer, it's necessary that you write that alpha equals 1.67. Do not write x equals 1.67. Do not just write 1.67. Write alpha equals 1.67. They can sometimes deduct a mark for this as well if you don't write alpha equal to that. Okay. Again, in easy topics, they tend to deduct marks for very simple things. So in this case, you have to be careful. Alpha equals 1.67. That's your final answer. That's what you get here. Let's look at this example. In the first part, just want you to use this iterative formula to calculate the value for alpha. You can see that. In the second part, they're saying state an equation satisfied by alpha and hence find the exact value of alpha. Now, iteration does not give you an exact value. For example, if some solution was square root of 2, iteration cannot give you square root of 2. It can give you a decimal value, for example, 1.43. You can keep making this more and more accurate. You can get a value correct to maybe 10 decimal places, 100 decimal places, 1,000 decimal places. However, you can still not get exactly square root of 2 from that. So square root of 2 is exact value. This value is in decimals. That's not exact. Iteration will not give you answers in terms of square roots, for instance. It will give you only decimals or not even fractions. Okay. So how do you find the exact value of alpha? First of all, they're saying state an equation satisfied by alpha. This is the iterative formula. How do you get back to an equation from this? Remove n plus 1 and n with x. You get this. Now simplify this. Simplify this equation. That becomes this, x power 4 minus 50x equal to 0. And that's an equation that we can actually solve directly as well. Take x common, that leaves you with x cubed minus 50. And the exact value of x, that turns out to be cube root of 50. That's the exact value of x. Or the exact value for alpha, that's cube root of 50. And you say, this is the exact value that we were looking for. This was an approximate value, as in the decimal value. This is the exact value, cube root of 50. Okay, and that's what you write there. The exact value of alpha is this, cube root of 50. Okay, that comes from the algebraic method, not iteration. Okay, now this is another thing. Another type of problem that you will see. You have this equation. It has one real. Okay. Find by calculation the pair of consecutive integers between which alpha lies. Now, what does that mean? Generally, what they do is they give you two specific numbers and ask you to prove that the solution lies between these two values. But in this case, they've not done that. They're just saying, find the pair of consecutive integers between which alpha lies. For example, if the solution was, let's say, 1.7, then you would say it lies between 1 and 2. Okay. So you have to find those two integers between which the solution lies. So what you do is you try some integers randomly. So generally in such questions, they start with smaller numbers, small positive values. If they don't work, try a few negative values as well. So in this case, we start from, for example, 0. What do you get at 0? 0 gives you minus 6. Try 1. When you input 1 in this, that gives you minus 6 again. You try f of 2, that gives you minus 2. You try f of 3, that gives you 12. And now you see the sign is changing. The sign is changing from 2 to 3. That means the solution lies between 2 and 3. Okay. So that's the value of alpha that we are getting. And that's what we're getting, that alpha lies between these two consecutive integers. Okay. So in this case, they did not tell you which numbers the solution lies between. Okay. You had to figure that out yourself. Consecutive integers. So you just try inputting consecutive integers. Start with 0, for instance. That gives you minus 6, minus 6, minus 2, 12. When the sign changes, that means that's where the solution is going to lie. solution lies between these two cases. So that's x equals 2 and x equals 3. It lies between 2 and 3 in this case. Now, the second part, they use this kind of statement a lot in questions on iteration. Show that if a sequence of values given by this iterative formula converges, then it converges to alpha. Now, what does that mean? Sequence of values. What sequence of values? From the iterative formula, you get x1, x2, x3, x4, and so on, right? That's the sequence of values. If it converges, that means if it gets stable to a value, that means if it gives you a solution. If this iterative formula gives you a solution, then that solution would be alpha. That means the same solution that you got from this equation. So in these complicated words, what they're trying to say is show that this iterative formula corresponds to that equation. That the solution that you get from the iterative formula is actually the solution of that equation that we had. That's what you had to prove. Okay? Now, how do you do that? This is what we understand from this, right? Show that the solution from this iterative formula is the solution of the equation in part 1. Now, we don't actually have to use the iterative formula at this point. You can see in the third part, they ask you to do that. We have to show that this iterative formula and this equation, they are basically coming from each other, right? How do you prove that? This is the equation. This is the iterative formula. You either rearrange this equation to convert it to a format like this, or the easier way generally is that you convert the iterative formula to a form such that it becomes this. So remove n plus 1 and n. That gives you this. Square both sides to get rid of the square root. You get this. Simplify that further, you get that equation, and that proves that this iterative formula is coming from this equation. If it's coming from that equation, that proves that the solution that you would get from this iterative formula, that will be the solution of that equation, because the iterative formula is actually coming from that equation. So that's what you prove in such questions, that the iterative formula and that equation, they correspond to each other. So generally, you would simplify the iterative formula and prove that that can be converted to that form. Okay. Last part is just the use of iterative formula. You can have a look at that. Okay, so that's the major concepts of iteration that we have. Then we have graphs in iteration as well. Let's talk about that next. Sketching different graphs. In your syllabus, you have done a number of different types of graphs. Iteration is where most of them are going to be tested. Okay, so let me quickly go through all the different types of graphs that you need to know about. And I'll try to quickly go through the method for sketching them. But of course, the assumption is that you know about it already. So we'll try to go through this quickly. Linear functions are straightforward. You just take 2 points and join them in a straight line. That gives you the straight line. For quadratic functions, there are 2 possible shapes, U shape and N shape. Okay, now just a point that you need to keep in mind. For all of these functions, the key thing that you need to remember is the shapes of these graphs, these graphs. Because once you know the shapes of these graphs, mostly what we would be doing would be, we would just be taking some values, plotting those values, and using those values, sketching a shape that we know it's going to look like. For example, for quadratic, we know it's going to be a U shape. We'll just take a few values and draw a U-shaped graph through that, or an N-shaped graph, depending on which case it is. Okay, so remembering the shapes is what is important. Apart from that, the important points that you need to remember, we will talk about them as we go along. So first of all, there are 2 possible shapes, U-shape or an N-shape for a quadratic function. When you get U-shape, when the coefficient of x squared is positive, you get a U-shape. When it's negative, you get an N-shape, right? C, the constant that represents the y-intercept. Now, for drawing these graphs, which are the important points? X-intercept, you do not always have to show them. If they're very straightforward to figure out, you can do that. Or you can just put them on your calculator, in fact. Solve that equation on your calculator, you find the x-intercepts if you need to. And the y-intercept, but turning point is important. On a quadratic graph, you must show the turning point appropriately. How do you find that? Minus b over 2a or differentiation, any method, show the turning point on this graph. That's important. Cubic functions, there are 4 possible shapes for them. You could have a shape like this. The shapes on the left side, in which overall the graph is going in the upwards direction. From left to right, overall, the overall trajectory is that it's going upwards. That is what happens when the coefficient of x cube is positive. The graph is going to be one of these 2 shapes. And when the coefficient of x cube is negative, then you have one of these 2 shapes. Now you do not need to be able to distinguish between these 2 shapes. It could be any one of these 2. And any one of these 2, that does not matter. Just remember that it's going to be one of these shapes. And how do you actually sketch the graph? Using the table function on your calculator. You must know how to use the table function on your calculator. You'll just plot those points and sketch these graphs through those points. For example, I'll just show this to you quickly for just this example. Otherwise, you can watch the calculator video for table function on my channel. Somewhere you'll find that to understand how to use table function. I'll just do this quickly for this particular function. You go to menu, you have this table function. The function is x cube plus 2x minus 3. You input that function there, skip g of x. G of x would be used when you have 2 functions at the same time. You would input both f of x and g of x at the same time. That will give you a single table that has both the functions values. In this case, we'll skip that because there's only one value. We'll have some starting point, some end point that we'll have to use. In this case, let's suppose we are using minus 3 to 3. Step means the gap that you want between values. In this case, you get these values on your calculator, x and y values. You'll plot these values, and using those values, you'll just draw a graph that looks like one of these shapes, right? So when you plot some values, you'll realize which of these shapes it is going to be. You just draw that, and that's it. Then you have reciprocal functions. Reciprocal functions are those functions in which you have x in the denominator. It could be like this. It could be like this. You can have square in the denominator. All you need to remember about such functions is that their graphs are going to be broken. They will occur in multiple parts, right? Because when denominator becomes 0, the graph will be broken at that point, and it will come in 2 different parts. Okay, just remember that, so that when you plot values, you do not try to join these points like this. You do not try to join these 2 graphs like this. That's not what you're going to do. It will come in 2 different parts. Okay, that's all that you need to remember. Otherwise, you just use the table function, plot some values, and whatever shape you get from that, you just draw that. For 1 over x or any other function that has just x power 1 in the denominator, the shapes are going to look like this. Okay, but you just plot them, and just remember they're going to occur in multiple parts like this. Then you have trigonometric graphs from paper 1. You need to remember how to sketch them as well. The sine graph, it looks like this. Remember the shape. For sketching that, just use your calculator. It will be in radians. It shows in degrees here right now, but you'll be drawing this in radians in iteration, not in degrees. Always use radians. Use radians to plot some points. You would remember the shape of the graph. It's going to look like this. Through those points, just sketch this graph. It could be sine x or any transformation of sine x. For example, 5 into sine of x minus pi over 4 plus 7. It could be like this. You do not have to think about transformation. Just put this whole thing on your calculator as it is. Make a table, plot those values, and sketch a graph that looks like this. It could be like it will be some shape like this. Okay, you just draw that, and that's it. Exactly the same thing for cos. Just remember the shape. Remember the shape of the graph. Plot values using the table function. Join them. You'll get a shape that looks something like this. Okay. For tan, remember the graph is going to occur in multiple parts. It's going to be broken at the points where the function is undefined. So when you input this function on your calculator, wherever you have undefined, at those values, you would have an asymptote. You'll have a vertical asymptote. And the graph is going to go either towards positive infinity at that point or towards negative infinity. Okay. And then the rest of the points, you can see how to draw them. That's what your tan function is going to look like. If it's some transformation where tan is multiplying by something or adding with, or you have plus minus something, you just put that on a calculator. Don't think about transformation. Just use the table function, plot values, and join those points. You get the result. Then you have cosecant, cot, and secant functions. Again, remember the shapes of the graphs. This is what the cosecant graph looks like. A U shape, an N shape, and it alternates like this. You will input these values in your calculator. Wherever you get undefined on your calculator, so it will be at 0 in this case, it will be at pi in this case, it will be at 2 pi. You don't have to make this table in your paper. You just look at the table on your calculator, plot those values, and make a shape like this. Just remember, when you have undefined, that means you have a vertical asymptote at that point. So you have an asymptote at 0, another at pi, another at 2 pi. At those points, the graph is either going to go towards positive infinity or towards negative infinity. Shape of the graph will tell you if it's going upwards or downwards. That's the graph of cosecant. Secant looks similar to that. It's just shifted to the left by pi over 2 units. In your calculator, you don't have buttons for cosecant and secant, by the way. For cosecant, you'll put 1 over sine. For secant, you'll put 1 over cos, right? Plot these values, draw a graph like this. When you have undefined in the function, you draw asymptotes like this. Whatever it is, if it's cosecant 2x, just put that in your calculator. For cosecant 2x, you put 1 over sine 2x in your calculator. You won't think about transformation. Just put this on your calculator, plot those points, and make a shape that looks like this. That's it. Cot x, for cot x in your calculator, you're not going to put 1 over tan x. You're going to put cos x over sin x. 1 over tan x is not going to give you correct values. Again, there's a logic behind that, but we're not going to go into that. For cot x, remember, you will be inputting cos x over sin x in your calculator. You'll be putting cos x over sin x in your calculator. You'll get some values, plot them. When it's undefined, you have asymptotes, and the graph is going to look something like this. Remember the shapes. When you remember the shapes, you'll plot some points and you'll understand what the graph is going to look like. So this looks like tan, but it's flipped, right? Tan was like this. This is flipped. That's the graph of cot. Okay, just put that on your calculator, get the result. You can do it like this. Then you have exponential and log functions. E power something or log of something. How do you sketch these graphs? For exponential function, for example, you could have some number multiplying outside. You could have some power of e, some number adding or subtracting outside. Similarly, for log function, you could have something like this: some number multiplying outside, some number multiplying or added inside, some number added outside, right? Now, for these two graphs, exponential and log, roughly, these are what the shapes are going to look like. These are the 4 possible shapes that you would have for the log graphs and the exponential graphs. Right, roughly, this is what the shapes are going to look like. These 4 shapes. These are 4 different graphs. This is 1, 2, 3, 4. One of these shapes you would get when you draw the graph of either log or exponential. Now, the difference is exponential graphs have horizontal asymptotes. So they will be almost flat at some point. So they'll go like this. They'll go like this here. And this will also go like this here. And like this. So exponential graphs have horizontal asymptotes. Log graphs have vertical asymptotes. So they will be extended to this side like this. They'll be going vertical here and vertical here. But roughly the shape is going to be one of these 4. Now, how do you draw these graphs? For exponential function, there are 2 things that you have to keep in mind. Where the asymptote is going to be, and one important point that you always have to plot. Now, what's that? The important point that you also have to plot, that you always have to plot, is when the power of the function is equal to 0. So you'll put the power equal to 0, minus 2x plus 4 equal to 0. The value of x that you get from that, that's the important point that you would always show on the exponential graph. Okay? That's this point here. At that point, you will see that the graph is going to quickly change its trajectory, that it would be less steep on one side, but then after that point, it becomes very steep all of a sudden. So that point where the direction of the graph changes significantly. That is the important point. What's that? Whenever the power is equal to 0. You always have to mark this point on the graph. Put the power equal to 0, you get some value of x from that. The corresponding value of y in this case turns out to be -2. Plot that point. You have to show that point on this diagram. Okay, then what about the asymptote? Remember, exponential graphs have horizontal asymptote, and that asymptote is going to be the number that's adding or subtracting outside. Y equals -3, that's the asymptote. If there's no number outside, then the asymptote would be y equals 0. Okay, if you have some number adding or subtracting outside, then that's the asymptote, y equals -3. So in this case, this horizontal line, this is the asymptote of this graph. The graph is not going to cross this line. The graph is not going to cross this line. It's going to, go very close to this line here like this, but not go below this line. That's not possible. Okay. So now you've got the asymptote. You draw that dotted here. You've got that important point. How do you actually draw the graph now? Take one point to the left of the important point, take one point to the right, and that will show you how the graph is going to look like. So in this case, I took one point on the left side, one point on the right side, and that gives me this and this. For exponential and log functions, the table function is not helpful. For this, you would just input values yourself. For the rest of the functions, you will always use table function, plot those values, and draw the shape based on that. This is how you would do the sketch of exponential graphs. For log graphs, the important point is going to be when the inner part is equal to 1. That's the important point that you always have to show. So 2x minus x equals 1. What's the value of x that you get from that? X equals 3.5. You have to show this value. Okay. Now, this is one point. You have to show this point on the diagram. What about the asymptote in this case? The asymptote in this case is when the inner part is equal to 0. That's when you get the asymptote. When the inner part is equal to 0. That's x equals 3. That's a vertical line. So the graph is not going to cross this vertical line, x equals 3. That's the asymptote of this graph. Close to this line, the graph is either going to go towards negative infinity or towards positive infinity. Depending on the shape, you can figure that out. So you take this important point. That's one point that you have. This point. Now you take one point to the right of that, one point to the left of that, and you will understand what the shape of the graph looks like. Close to the asymptote, it's going to go towards negative infinity. On the other side, it goes like this. And that's it. That's your graph. Okay. So you need to remember for both of these graphs, what important point you have to show and what the asymptotes are going to be. Okay. Important point and the asymptotes for both of these graphs, you need to know them. Because in these graphs, sometimes they don't even tell you the interval. That's in which interval you have to draw these graphs. For the other graphs, they will always tell you the interval. For these two graphs, they sometimes don't even tell you the interval. In that case, you have to make sure that you show this important point and also the asymptote, and based on that, you would understand what part of the graph that you need to draw. Okay. So these are all the different graphs that you need to be able to sketch in this topic. Let's have a look at some problems that involve graphs now. So it says, by sketching a suitable pair of graphs, show that this equation has only one root in this interval. How do we show that? We have two functions here, one on the left side, that's y equals 2 cot x. Another function on the right side, y equals 1 plus e raised to power x. What we do is we draw those two graphs. The important point for the exponential graph is when the power is 0, right? X equals 0. We take that point and then we draw that graph in that interval that's given 0 to power 2. That looks like this. And we draw the graph of the other function as well, that's cot x. How do we draw cot x? For cot x, in our calculator, we put cos x over sin x. So we'll put 2 cos x over sin x in our calculator for cot. Okay. And then just plot values. You'll get a graph that looks like this. This is how I would, do it. Make sure calculator is in radian mode. Put f of x as 2 cos of x divided by sin of x, for instance. That's your first function. Now, in this case, since you know the interval, 0 to pi over 2, you can just put g of x, the other function, as 1 plus e raised to pi x. That's the second function. And that gives you this next step. Actually, where do you start from 0? End at pi over 2. Now, the step should be such that you have sufficient number of values within this interval. So generally, if you have a trigonometry graph involved, I recommend that you at least divide the interval by 4. So pi over 2, divide that by 4, and that gives you pi over 8. So you have pi over 8, pi over 4, 3 pi over 8, pi over 2. These values are what you plot on the x-axis. And that they should be sufficient to make you understand what the shape is going to look like. If you still don't understand, if you still don't understand what the shape is going to be like, then you have to take more points. You'll have to break it down further. But generally, if you remember the shapes of the graphs, dividing by 4 is going to be sufficient. So pi over 2 divided by 4, what's that? That's pi over 8. Okay. And now you get these values. You plot those values. Now, the problem with table function is that it does not give you exact values. So you should know what the values on the x-axis are. So values on the x-axis, when you divide it by 4, they're going to be pi over 8. Then 2 pi over 8, that's pi over 4. 3 pi over 8, and then pi over 2. So these you should know, so that you know on the table, the first value, the second value, what are they giving you on the x-axis, and then you just plot the corresponding y values for them. At 0, you're getting an error for f of x. That means this function is undefined. So you have an asymptote for chord here, right? You plot the rest of the points, 4.8 to 0.8, and then finally 0. That's the last point that you have here. You plot those points and you sketch a shape like this to those points. Okay. And then the other one, the exponential function, you have those points as well. Plot those values and you draw a graph like this to them. And that gives you the graph. And then you say, the question is saying, show that this equation has only one root in this interval. How do we show that? We have to write down now that there's only one point of intersection. Since there is only one point of intersection, that is why there's only one root. Writing down the statement is important. Otherwise, even with all of this effort, it's a 2-mark question. If you don't write that statement, you only get 1 out of those 2 marks. So if there's only one root, you write that there's only one point of intersection. That is why there's only one root. And you can mark that point in the diagram as well, that this is the one root that we've got. Okay. For trigonometric functions, they will give you the interval. For exponential log functions, sometimes they don't give you that. So you'll have to figure that out yourself. Okay, just give me a minute. I'll be back. Okay, let's look at this example. So they're saying, sketch this curve, and hence by sketching a second curve, show that this equation has exactly one real root. Now, we have to state the equation of the second curve as well. Now, how do we do that? They want us to sketch this curve first of all, y equals ln of x plus 1. Now, remember graphs of functions O-levels. This is one function that you have. What's the other function going to be? We want in this equation that ln of x plus 1 is on one side, everything else on the other side. So we can rearrange this so that we get ln of x plus 1 equal to 40 minus x cubed, right? And now this is one function that we would draw, y equals ln of x plus 1, and the other one would be y equals 40 minus x cubed. These are the two functions that we would draw. We can sketch them like this. For the log function, consider the important point, the asymptote, sketch that, and then according to that, take a similar interval for the cube function. You'll just do this on your calculator. You don't have to write this down here. I just showed this for wrote them down for notes, but you'll just draw this table in your calculator, plot those values for the cubic function. This is what the graph is going to look like, and then you say that there's only one point of intersection. That is why there's only one root. Okay, you can have a look at this later on in your own time as well. And that's how this would work. Then they're saying, verify by calculation that the root lies between 3 and 4 by calculation. How do you do that? You bring all terms to one side, leave only 0 on the other side, and then put those values one by one. One is negative, the other is positive. Sign is changing. That means there's a root between those two values. Now the next part is saying, use this iterative formula to find the value of alpha. Okay, so you can do that as well. The last part, reduce the root of this equation. So based on that, now you have to reduce the root of this equation. Now, how do you do that? How is this connected to anything that you've done before? You found the solution of this equation. And based on that, they want you to find the solution of this equation. How are the two connected? You have to think about that. Let's write down those two equations here. One is this, and the other is this. Let's compare the two. This equation, using iteration, gave us the solution x equals 3.377. Now, when you compare that with this, we have 40 on the right side for both of them. And on the left side, what's happening is we have x cube here, and here we have e raised to power y minus 1 whole cube. So it looks like what's happening is x has been replaced with e raised to power y minus 1, right? And that's the same that we have here, same thing that we have here as well. It's in a different format, but it's actually equivalent because y equals ln of x plus 1. If you take this to the other side, it becomes e raised to power y equals x plus 1, and x equals e raised to power y minus 1. So that's the connection that you get between these two equations. X has been replaced with e power y minus 1. Now, what does that mean? The values of x that we got as solution from there, the value of x that we got, that is now going to be the same as e raised to power y minus 1. So we say e raised to power y minus 1, that equals this value, and find the value of y from that. Okay. So it's, again, show a couple of more steps here. What I've done here is that I've just used this directly. But if you wanted, you could also do this. E raised to power y minus 1 equals 3.377. And that gives you e raised to power y equals 3.377 plus 1. And then take log on both sides, and that will give you the same thing as that. Okay, so you can do it either way, and that gives the value for y. Okay, so sometimes this can happen as well, that they make you solve one equation, and using that, you have to solve another equation by finding the connection between them. Okay. Okay. A few more examples, and then we end. Let me just see if there's anything different anywhere. Let's just show the solutions and we. Okay, this is another equation, equation that we have. Secant x equals 3 minus x squared. We have to sketch graphs for this. Which graphs do we draw here? Secant x is 1 over cos x, so that's one graph that we draw. Again, just input values in your calculator from 0 to pi over 2, right? Break it down into 4 parts like this. Put values in the calculator, table function, right? Plot those points and make the shape that you know of. When you have undefined, that makes it an asymptote. Otherwise, you just, plot those points, plot those values, and draw a graph through them. They're saying show that it has only one root. So you're clearly right. There's only one point of intersection. That's why it's only one root. The next parts are pretty straightforward. You can have a look at this working. It's the same type of question. If a sequence of values given by this iterative formula, it converges, then it converges to the root of the equation in part 1. All you have to do is show that this iterative formula corresponds to which equation? Yeah, this equation in part 1. It corresponds to that, right? How do you do that? Simplify the iterative formula, remove n plus 1 and simplify everything and convert it to that form. Okay. Then you have iterative formula. Make sure calculator is in gradient mode. Sometimes the first parts of these questions, they tend to be a bit tricky. So that's circular measure. Sometimes it's differentiation. Sometimes it's integration. So that's other topics that a lot of people struggle with, especially circular measure, because those of you in A2, sometimes you end up forgetting the A1 concepts. You need to make sure that you revise them as well. You need to know circular measure that is often tested in iteration like this. So you sometimes have to make extra lines to, do some calculations. This is a relatively difficult one. You can have a look at this working. That's not iteration, that's the circular measure. You can see that the iteration part, generally they're going to be relatively easier. The first part will be some other topic when you're doing this question in the exam. If you get stuck on the first part, it's okay, leave that, but do not leave the whole question. As in leave that for the end, not just leave it all together, but leave that for the end of the exam. But do not skip the second and third parts. They will be the easiest on the paper for iteration. Do them right away at that point so that you don't end up missing them at the end. But you can do the first part at the end if you cannot figure it out in a few minutes. Then you just skip that and come back to that at the end. But do not skip the rest of the parts, okay? You can have a look at that working. Okay, that's how you would do it. Okay, there's just one small thing that I want to tell you about this. We have this diagram that shows the graph of this function. The curve intersects the x-axis at the points a0 and b0, where a is less than b. You can see that in the diagram, a and b. These are the x-intercepts of this graph. We need to find the value for b, first of all. How do we do that? It's polynomials, basically. They're saying b is an integer. So remember, we talked about this in polynomials. If you have an integer solution of a polynomial, it will always be amongst the factors of this constant. You'll try some factors of 6, plus minus 1, plus minus 2, plus minus 3, plus minus 6, and see which one of them satisfies the equation. That will be the solution. Now, the trick that we discussed for this was solve this equation in your calculator directly. The integer solution that you get from that, in this case, you'll get the solution x equals 3. Just show the working for that in your paper. Show that when you put x equal to 3, the equation is satisfied. So that means the value of b here, that should be 3. Okay. That's the value that satisfies this equation. We discussed this in polynomials. Then hence show that a satisfies this equation. Now this is important. A and b are the points of intersection of, are the x-intercepts of this function. Both of them are x-intercepts of this. How do you find x-intercepts? By putting y equal to 0. So that's what we do here. In this equation, we put y equal to 0. And that's the equation that we got in the first part. This equation, its solutions are going to be b and a. Now, in the first part, we found one solution. We found one solution, and that one solution was 3. X equals 3 is one solution. If you know one solution of a polynomial, how do you find the others? Using polynomial division, right? If x equals 3 is a solution, we can say x minus 3 is a factor. Do long division, find the other factor, that's this. And then you say, this other factor, when this is put equal to 0, that is going to give you the other solution. Okay? They are saying, show that A satisfies this equation. So you rearrange that now and convert it to a form like this. Convert that to a form like this. Okay? So this is what you want to convert it to. So you rearrange this, think about what variable you have to make the subject. So you see, you've got 3 divided here. That means most likely it will be this x that you would have to make the subject. Or maybe not. Let me look at this. A square, A cube, 2. Yeah. So this will be the x that you would want to make the subject, this x, because you have 1 over 3 here, right? And the x square, a square and a cube, they are both on the other side. So square and cube, they will be on the other side. So what you do is you try to make this x the subject, as in keep this on one side, everything else on the other side. And that's what you end up getting. And at that point, the solution that you're looking for, at that point, x is equal to a, put x equals a, and that gives you that equation that they were looking for. A has to satisfy this equation. Okay, because it has to be a solution of this equation. So when you rearrange that, this is what we end up getting from that. All right. Then they say use an iterative formula based on this equation to find the solution, find the value for A. How would we do that? First of all, what iterative formula do we use? We've got this as the subject. We talked about this when we discussed how to derive an iterative formula. We've got one variable on one side, everything else on the other side here. They've already made you convert it to this form. You just put n plus 1 here and put n with the a's on the right side. That's the iterative formula that we got. Okay. The next thing is, how do we know what value to start from? They have not given us any starting point here. Right? They've not given us any starting point here. We have not even proved that the solution lies between any two values. Remember, the starting value is supposed to be your best guess about the solution. Look at the graph. Look at the graph. If this value is 3, what do you think A is going to be roughly? If this is 3 units, then what about A? It's close to maybe 1 unit, slightly less than that. So your starting value for iteration is going to be your best guess about the solution. If this is 3 units, we could say this is somewhere close to -1. So you could use -1 as a starting point. Okay, you could use minus 0.9, minus 0.5. Any of them would. It's somewhere between minus 0.5 and -1. So that's what you use as a starting point. You say A1 is equal to -1. Then you just put that in the iterative formula, solve that, you get the result. And that's the result. That's the answer that you get from that. Okay. This is just another example. First part is fairly straightforward. They have cot here. So when you have to use this on your calculator, cot will have to be replaced with 1/tan for that. Right? So 1/tan of half x minus 3x equal to 0. Then you input the values of x. One of them turns out to be positive, the other negative, and you get the result from that. The second part says, show that if the sequence of values given by this iterative formula converges, then it converges to alpha. Again, the same question. We have to show that this corresponds to that equation that we were given there. This was the equation. So we start from the iterative formula, try to rearrange this, and convert it to that form. The important point to remember here is tan inverse of x is not the same thing as cot x. These are two different things. Tan inverse is a different function. Tan of x whole power -1, that would be 1/tan x. And that can be written as cot x, but not tan inverse of x. Tan inverse of x is something totally different. That's a different function. That's the inverse function. Tan inverse is not the same as cot x. Tan of x power -1, if you had this, that can be written as cot x. So do not think that you want cot at the end. So just replace this tan inverse with cot. No, that's not correct. Cot will come when you have 1/tan somewhere. For example, here, if you have tan of this, you want to convert it to cot, you take reciprocal on both sides, and that gives you cot here and 3x here. And that proves that result that you wanted to find there. That's all that you need to know about iteration. I hope that was helpful. If you have any questions, you can let me know.